And now I launch onto another thing. Not a question of what's practical today, but what's in principle practical. It's already noticed, for instance, that if we were to try to make the wires about half as big or a third as big as the wires in that particular design, it's a strange thing that when wires carry electricity too long, they move, the matter moves. It doesn't move much. It doesn't make any difference there, but when the wires are very much thinner, it tears the wires apart. So you have a problem with wires, and everybody's worrying about that. But that's like the sound barrier. You may be all too young to have heard of the sound barrier, but there was once a time when it was said that no airplane can travel faster than the speed of sound. And the reason was, of course, that airplanes were designed considering, assuming that the air is essentially not very compressible. It's not easy to squeeze it into a small space because the airplanes went slow enough that there wasn't much force to squeeze it into a small space, so it always expanded. It was always not squeezed. And the theory and the analysis and the experiments all dealt with air that was not compressed. It was then realized that if you took into account the compression, that airplane wouldn't work with its propeller, and everything wouldn't work. The propeller would go too fast and it wouldn't pull. So there was a barrier. How are we going to go faster than the speed of sound? It just means there's no law of physics that says that you can't go faster than the speed of sound. It just requires a completely different design. So these limitations that you hear about mean only that you can't go on with the same design, but it doesn't mean that it's not possible in principle.
One person that's been looking at the miniaturization of computers over the last several decades has been Gordon Moore, and he's the co-founder of Intel back in the 1960s. And he noticed that the number of components on a silicon chip double roughly every 18 months to 2 years. Now, for this to happen, it means that the smallest feature size on a silicon chip has to decrease at the same rate. And he came up with something called Moore's law, and here it is represented on the screen. Now, this law has been going now for approximately 4 to 5 decades. And what started out as an observation by Gordon Moore has now become a law after his name, Moore's law. It's actually continued in time. The interesting thing is that the industry has now set this as their roadmap of how to make computers smaller and smaller and faster and faster. So you have multi-trillion-dollar industries, the semiconductor industries, pouring money in every year to try and beat that law. Until now it's become a self-fulfilling prophecy. So if we have a look at where we are at the moment, here is a cross-sectional scanning electron microscope image of a single transistor. Now the smallest feature size in this transistor is the distance here between the source and the drain. It's about 30 nanometers. It's 5,000 times smaller than the width of a human hair. What's amazing about that is if you look around you now, we all carry around our personal electronics. And within one silicon chip, you have over 3 billion of these transistors. And they all have to work reliably so that your computer, your mobile phone, or whatever you've got with you actually works. That's quite amazing. Just think about that now. Everybody in this audience has got billions of transistors. There are trillions of transistors in this room. Well, one of the nice things about Moore's law is you can actually predict with time what's going to happen. And eventually you'll see out here, in roughly 2020, less than 10 years away from where we are now, the size of a transistor will get down to the size where it's a single atom. That's the smallest component of nature.
And therefore I have considered the question, never mind about making it with wires. Let's make it a different way, make computers a different way, with atoms, with interactions, with certain kinds of connections. How small can it be made? Can it be made so that each one atom, in the state of one atom, tells you yes or no instead of gold and silver? And the answer is, of course, that the laws of physics that you have to use are very different than the laws here. They're called quantum mechanical laws. The scale is so small. We have to worry about the uncertainty principle and everything else. But just let me tell you that it turns out to be possible, according to the laws of physics, in principle, to build a computer in which each bit or each little piece of information is one atom large. And there's no problem in that. And that was something I had some fun working out.
So, the story that I wanted to tell you about today is a story that deals with mysteries that we have with some certain unusual materials. And I'm not a material scientist. I'm actually a cold atom physicist, so I don't really have anything to do with these materials and shouldn't be meddling around with them. But there's a new branch of cold atom physics that's called quantum simulations.
In the classical world, we understand how things work. So if I had a tennis ball now and I was to throw it at a wall, it would hit the wall and it would bounce back and I'd understand and I'd see it and be able to write equations of motions to describe that. But as I miniaturize things down, and you imagine that tennis ball being the electron in my transistor, if I made it very, very small and I threw that electron at the wall, instead of it bouncing back, it actually behaves more like a wave than a particle. And it can tunnel through the wall and it can come out the other side. Now that's something that's quite scary. As we make our devices smaller and smaller, the wonderful world of quantum mechanics comes in. Electrons behave like waves and they no longer go in the computer where we want them to go. So a lot of people have predicted that this would herald the end of Moore's law. But in reality, it's the start of something new. We're now transitioning to quantum mechanics. And if we control quantum physics, we could actually build computers in the quantum regime that are predicted to have exponential speed up over classical computers.
The term quantum simulations, we actually credit Richard Feynman with to have defined it about 30 years ago in a famous lecture that he gave on the physics of computation. And he summed up the motivation of why we would want to have something like this nicely in the end of that talk in the following way. He said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it a quantum mechanical one, and by golly, it's a wonderful problem because it doesn't look easy." All right, so it's not an easy problem. So
I've just put together a very short, brief introduction to what we're doing and some of the philosophy behind the approach that we've taken, especially coming from the condensed matter theory side. You see quantum mechanics everywhere, and in the world at large, and especially in biology, people ignore it, and I've never understood why. I mean, even this segregation between the seemingly trivial and the things that are a higher level expressions of quantum mechanics, I don't understand that division myself. Because if you ask the question, what about this thing could be the same if it was classical, the answer is nothing. Because electrons and matter, as we know, it doesn't exist. It's not quantum mechanical. There's some essence at the very bottom of all of this that you require as quantum mechanics. And I have never understood why people draw dividing lines between behavior at the electronic scale and behavior at the macro scale. Because, sure, there may be areas where a system may be modeled classically, but you can't pretend that the thing is classical. It's not. Nothing is classical. Under the hood, everything is quantum mechanical. And so you have to be open to the possibility that the things that you care about as a scientist or as a builder of things can be made better, more efficient, or you have to understand how these things work in order to make progress. So this theme is explicit in the exercise of trying to build quantum computers. Because in some ways, quantum computers are this idea made manifest, that you want to somehow amplify the behavior of the world from the electronic scale, or the scale of the very small and very cold, up to a level where large, hot, macroscopic things such as humans can play with these things and make them do things that we find interesting, like solve hard problems.
There are some problems out there that just cannot be solved efficiently using a classical computer. And one of those is something called the traveling salesman problem. So here we have a salesman. We want him to travel to lots of different cities, and we want to work out where the shortest possible route is. That sounds like an easy problem. But it's actually one of those intractable, exponentially hard problems. So here we have on the screen the number of possible routes that he can take as a function of the number of cities. It's something that grows very, very quickly. So by the time you have 14 different cities, there are now already 10 to the power of 11 possible routes that he can take. So if I take a classical computer, it works in the gigahertz regime, 10 to the 9 operations per second. And it can work out the shortest possible route in about 100 seconds. Well, that's no big deal. But now what happens when I go to 22 cities? There are now 10 to the 19 possible routes that salesman can take. And with that same classical computer, it would take 1,600 years. Now, this is amazing. And if you look, by 28 cities, it's longer than the lifetime of the universe to work out what the shortest possible route is. Now, I heard this problem many years ago, and I just couldn't quite believe it. But this is a real problem. It exists out there. So how can we make a computer that can somehow solve those kind of problems? Well, we have to look at how a classical computer works. A classical computer is very fast, but it searches through all the possibilities one after the other, rather like a recipe. So if I was to write down a telephone number on a piece of paper and I'd forgotten whose telephone number it is, I would get my classical computer to start looking through all the A's and then all the B's and then all the C's, and eventually it would find whose number it is and tell me. If I wanted to go faster, I could put two computers onto the problem. Get one searching between A to L, the other between M to Z, and it would go faster. Go faster, I have three computers. Well, that's the digital world. If you could make a quantum computer, the actual calculations are done in parallel. They're all done simultaneously.
Journalists beware, because this is something that almost every popular article about quantum computing ever written has gotten wrong. You know, every writer seems to want to describe a quantum computer as this massively parallel classical computer that could just sort of compute all of the possible answers in parallel and then instantly pick out the best one. Okay, you know, and in fact, just this week there's a whole long article about quantum computing in the New Yorker. Maybe some of you have seen it, but you know, it just repeats the same mistake that some of us have been trying to correct for 12 years.
Now, to try and understand this, I'm going to go back and describe what a classical computer looks like in my mind. So I'm imagining I'm sitting at the center of the Earth, and I'm pointing towards the North Pole. We've already heard a talk about the North Pole this morning. That's my 1 of digital information. I could also be pointing at the South Pole. That's the 0 of digital information. But in the quantum world, I can be pointing to anywhere on the surface of the Earth. I can be pointing to London, or I can be pointing to Tokyo. And as a consequence, I'm in what's called a superposition, partly up and partly down. And that's an electron wave function. That's the quantum world. I can be in both states at the same time. Well, how does that help me in calculations? Well, let's look what happens as I increase the number of quantum bits or qubits. That's what a transistor is called in the quantum regime. So with just one qubit, I'm in 2 possible states at the same time. If I now add another quantum bit, I can be in 4 possible states at the same time. If I add another quantum bit, I can be 8 possible states at the same time. So every time I add a quantum bit to a quantum computer, I double the computational power. So it's been predicted by having just a 30-qubit computer, I'll be more powerful than the world's most powerful supercomputer that exists. And if I could have 300 qubits, that would be more powerful than all the computers in the world connected together. Now just stand back for a second. 300 quantum bits or qubits compared to 3 billion conventional transistors. That's really the power of quantum computation. So let's consider some of the problems that quantum computers can solve for us.
What is the kind of materials that are giving us these problems, and what is the issue that Richard Feynman was talking about in this case? Let me give you an example of one of these materials, and you've all heard about it. It's called a high-temperature superconductor, and it's a material that's conducting electric power without any losses, so obviously it's very useful, and we're using it a lot on an everyday basis for technical applications. However, the embarrassing fact is that for high-temperature superconductors, even 25 years after we found them, we still don't really know how they work. And of course, we know a tremendous lot about them by now, after 25 years. So for example, we have taken them apart, and we do know what they look like on the inside, and this is what you can see in the bottom right. And they consist of a crystal structure of different types of atoms that are in some regular arrangement. All right, what's even worse, I can actually give you the formula that we think contains everything that we need to know about high-temperature superconductivity. And as you can see, it's not terribly complicated. It's just a bunch of letters. And it would seem that you could solve something like this. But in 25 years, unfortunately, we have not been able to. So what is inside this formula? It's actually quite simple. So what it's describing is simply this lattice that we've been talking about, this regular array of atoms. And on the sides of these lattices, there are electrons. And the electrons have a spin and an orientation which can rotate. And in addition, these electrons can actually move around the lattice by tunneling from one side to the next. That is all. All right. But we cannot solve this analytically. Today, we have very powerful computers. So why don't we do a computer simulation and put all of this into a computer and see where the high-temperature superconductivity comes out? Unfortunately, and this is the problem that Richard Feynman was talking about, this is also not possible as far as we know today. And the reason is that this is fundamentally a quantum mechanical problem. And in quantum mechanics, the electrons are not necessarily at one given location, for example, but they can be in several states in several locations at the same time. And this means that if you put several electrons, you have to take care, in the memory of this computer that you're using, take care of all of the possible combinations of positions that you can imagine at the same time. And this number of possible combinations is a number that increases very quickly when you increase the number of electrons that you're looking at. And in fact, that is so quickly that if you take the most powerful computers today that take the power of an entire small city, you cannot simulate a system that is larger, even in a simple case, than about 40 electrons, which is not enough for us. And if you want to do something that is only 300 electrons, so still really tiny, this computer would have to be larger than the size of the entire universe in order to store all this data. All right. So a problem that requires a computer that is larger than the universe, well, let's try to solve it anyway. That sounds like fun.
The machines that we've built are designed to solve something called an optimization problem. And the optimization has many uses, but the one that we're focused on primarily is its use in the course of doing something called machine learning. So machine learning is a subfield of artificial intelligence that's concerned with the question of how do you take an engineered system, a machine, and allow it to learn from its environment. So this could be learning from video cameras, it could be learning from microphones, it could be learning from touch, it could be learning from all of those things at once. We know that humans do this quite effectively, but teaching a machine to learn in the way that humans do has turned out to be a very difficult problem. But recently there have been advances in the science of learning that allow us a path to try to actually replicate human-type learning in engineered systems. And somewhat fortuitously, the underlying mathematics of those methods can be run on our hardware.
In our January 2010 report, we aimed one loser arrow that might have missed its mark. Here are the first 3 paragraphs. D-Wave Systems, a Canadian startup, recently booted up a custom-built, multi-million-dollar liquid helium-cooled beast of a computer that it says runs on quantum mechanics. That's right, D-Wave, a 55-person company operating out of an office park in Burnaby, British Columbia, claims to have built that almost mythical machine, that holy grail of computing, the stuff of sci-fi novels and techno-thrillers, the quantum computer. Such a system would exploit the bizarre physics that apply on ridiculously small scales to compute ridiculously fast, solving problems that could stymie today's supercomputers for the lifetime of the universe. Now, building a practical quantum computer has proved hard, really hard. Despite efforts by some of the world's top physicists and engineers and the likes of IBM, HP, and NEC, progress has been slow. Ask the experts and they'll tell you these systems are a decade or 5 away. Harsh words, and you can almost hear the gods of karma preparing their punishment. Sure enough, a couple of weeks ago, aerospace giant Lockheed Martin, maker of the F-22 Raptor fighter jet and the Mars Odyssey orbiter, bought a quantum computer from D-Wave for $10 million. So were we wrong to call D-Wave a loser? Are quantum computers really ready to make the leap from the laboratory to the commercial market? What is Lockheed Martin getting for its money that it can't get from a regular computer?
So D-Wave is a private company. It's been around for about 11 years. And we only do one thing, and that is build superconducting processors. So these are processors that are fabricated out of metals, in particular a metal called niobium, run at very cold temperatures, designed to embody a very specific quantum algorithm, which is this quantum annealing thing that Hartmut referred to earlier on. So these things are not universal quantum computers, for those of you who are familiar with the field. They're not gate model quantum computers, which is a particular type of quantum computer. They're another way of looking at how you would use quantum mechanics in order to compute something useful in the world. It's a fairly small effort as these things go, but we do have some unique infrastructure, including what's commonly believed to be the most advanced superconducting chip fabrication effort in the world, which is run by Eric, who's sitting back there. So if you want to know anything about superconducting chip fab, he's arguably the world-leading expert in all of this. And there was something like the crown jewel in our efforts. Our ability to fabricate these things efficiently and quickly has differentiated this effort from a lot of others. So the implementation that we use requires cryogenic temperatures, and that's millikelvin. So we use machines that are called pulse tube dilution refrigerators. So these are machines that allow you to cool a very substantial block of stuff down to close to absolute zero, in our case somewhere around 10 millikelvin. The inside of this metal cylinder contains an insert which looks like this, where these circular plates exist at different colder and colder temperatures, from the top being room temperature down to the bottom being near the base temperature of the fridge. And at the bottom of this, you see an assembly, which is a bunch of filters and shielding elements, and the chip itself resides right down at the bottom. Now, for us, there are two very difficult to meet environmental constraints. One is the temperature. The other is that the processor type that we build is very sensitive to magnetic fields, and they can't be anywhere near the chip. So people get amazed at the fact that you can attempt to build a computer that runs at millikelvin, but that's really not the hard part here. It's much harder to make these low magnetic fields than it is to make the low temperatures for a variety of reasons. So we've done a lot of work on magnetic shielding. That thing at the bottom there, if you look a little closer, has something that's very much like a motherboard, upon which is mounted the actual chip itself. And remember, these are superconducting chips, so they're very much like your standard CMOS-based device, except that now we're talking about metals instead of semiconductors. And it exists right at the middle there. So this see if I can bring this thing here, is one of the chips.
Basically, I've read a whole load of information about quantum computing, and there's lots of conflicting information out there. So what I really wanted to do was just to have a chat and ask you a few questions about some of the things I've read. So the D-Wave quantum computer is truly quantum. Is that right?
Yes, it is. It uses quantum mechanics in its operation. We built a mathematical model that was quantum mechanical. We took data, and it fits very perfectly to that model. And then we tried as hard as we could to build a model using classical physics to do the same thing. And we found that no matter what we did with classical physics, we could not get it to fit the data that we got from the D-Wave chips.
So that's compelling evidence that it's quantum mechanical.
I think if you have data that fits to a mathematical quantum mechanical model, then science tells us that that system is behaving quantum mechanically and not classically.
While the gains aren't automatic, they certainly can, when you wrap up all of the details, they can be quite significant.
So what problems are Lockheed Martin trying to solve here? What are they getting for their money that they can't get from a regular computer?
What our system does is solve optimization problems.
So optimization, you have an objective function and you want to find the minimum of this function. That's an optimization problem. And this was the picture from this morning. Here I have this video, and I apologize, several people here have seen this already many times, and I keep showing it again to give people who are not familiar with it, the basic idea of a quantum resource that can help you better with finding the global minimum here. Classically, you could only have, this ball could have only rolled down and would have been stuck in a local minimum. If you have a second resource, tunneling, then, of course, if this barrier would have been too fat, the tunneling amplitude would have been very small and probably the advantage would have been tiny. But it's actually the beauty of the adiabatic quantum algorithm that it forms this landscape slowly, and hence at any point in time you have a good chance of having a reasonable tunneling amplitude. And overall, of course, physics determines what optimization problems you can solve, and bringing in this additional resource of quantum tunneling expands the reach quality of your optimization algorithms.
For example, you might want to know, what is the biggest financial return that I could get on any set of 100 financial instruments? And I have the freedom to choose any 100 I like, and maybe the freedom to choose the time scale and all this. So you can imagine that if I had to choose 100 financial instruments, there are lots of different combinatorial possibilities, many, 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 more than I could ever enumerate.
And so what we are doing on the application side is trying to understand the power of the state-of-the-art machine learning techniques when they're run in our systems in the service of building complete engineered systems that behave or mimic human-level intelligence. And not just intelligence in the sense of being able to do things faster, but mimicking human creativity, judgment, and so on. For the first time in history, I believe that the frameworks for understanding how to do this are in place, and our hardware is ideally suited to attacking one of the hard bottleneck problems that underlies this type of approach.
So just using the square laws, we had done in winter an experiment trying to classify cars. So we tried to build a car detector, and we used actually the D-Wave hardware. At the time it had 52 variables to train or use our training objective and solve the training objective on the D-Wave hardware. And we used the 20,000 images from Street View scenes. And at the time, the chip was supposed to look like this with 128 qubits, but this was a very early one, so not all chips were functional and also not all the connections existed. So on this somewhat beaten up graph, we trained our classifier, and to our delight, we found if we compared this hardware solver to heuristic solver that would run taboo search, which would run, let's say, on a conventional machine, we were able to eke out not a tremendous, but nevertheless a small advantage.
So what these optimization problems end up being is both foundational to many of the problems that current computers are bad at. So what Lockheed wants to do with this particular system is see if we can recast a particular type of problem, which is called verification and validation, in optimization language, and then use our systems to make inroads into this problem. So verification and validation is, given a big complex system, of which there are many nowadays, and the aerospace industry is rife with them, large machines that have many, many parts, lots of different software of a variety of different types from different vendors, lots of different very complex hardware pieces. They all have to work together, and they can't fail for unintended reasons. They can't have behavior that wasn't in the spec.
What you saw so far, what we're able to do is that it seems to us that the quantum optimization is a useful new resource for intelligent systems. And between the older work and the newer one, I think we were able to show that training maps well to quantum optimization. We found that we get lower generalization error. We get more compact classifiers. That means it would execute faster. We could train it faster by using less training cycles. And here's a new result, new achievement was that we can better cope with outliers.
How much customization is involved with a customer like Lockheed Martin? I mean, I'm just wondering if, anybody with an optimization problem and an extra $10 million lying around, should just buy a D-Wave computer, or is there more involved than that?
There's quite a bit more involved. We partner with that organization, supply them with all of our technical know-how on the hardware side, including machines, and then work together with them on the software side to marry their problem into algorithms and procedures that will run efficiently on this new type of machine. So this is typically viewed as a multi-year procedure where it's a learning exercise for a lot of it, where we teach the organization how to do this. We help them along the way. We scratch our heads and think about their hard problems. And then the intent is that at the end of the relationship, we'll have demonstrated significant progress into this very hard problem, which will then, cascade onwards and eventually, hopefully, solve the problem, or at least part of the problem for the customer organization.
That actually leads directly to my next question, which is, when will we know whether Lockheed Martin made a wise purchase here?
Well, as the CTO of D-Wave, I would say that they've made a wise purchase regardless of the outcome, because this new type of technology is it's like an entirely new branch of technology. So there are things about what we do that are really quite different than the approaches that people take nowadays. And it's showing a lot of promise. So even the results that we've gotten now on these early stage chips, they're dramatically different than conventional processors. Just as an example, the chips are superconducting, and we operate them at very low temperatures. And at those temperatures, these metals don't generate heat when they when the processors are operating. So the power profile of these types of things is ridiculously low. In fact, the energy consumption of one of these chips compared to a CMOS chip is something like 10 to the 10 times less. So we're talking about like 10 orders of magnitude less energy generated during a computation. So I think that they made a wise decision to look at it. Whether or not it actually pays off in the problem that they're trying to solve, I'd say we're looking at something between, say, 3 to 7 years, because the technology now is not mature enough to actually directly target the core hard problem that they've got. Their problem is so big that you need to have much larger scale systems than what we've built today. But, we have a roadmap, and we'll get there. So I think that as the technology matures together with the understanding of how to solve the problem from the software algorithmic side, you're going to see a win or not somewhere in the 3 to 7 year time frame, I would think. Oh,
fair enough. Well, congratulations on the sale, and thanks for not rubbing our noses in our loser label.
You're welcome.
My name is Jordy Rose. I'm the Chief Technology Officer and one of the founders of D-Wave Systems.
My name is Michael Hayden. I'm the Director of the Center for Molecular Medicine and Therapeutics and a Killam Professor in Medical Genetics at UBC.
So I have a little bit of a futurist bent. I like to think about things that might become true that aren't incompatible with the laws of physics. And there are a large number of possibilities of really grand challenge problems that might break during our lifetimes. And I find that extremely exciting.
The exciting part for us right now is we're in our golden age. We have the ability through other advances in technology to know our whole human genome sequence. 3 billion little letters of our alphabet. We understand, and this has made us both human, unique, and linked. Our DNA alphabet has linked us to everybody on mankind.
So things like the development of truly intelligent machines, which is something that I've been thinking about quite a lot over the last few years, given the work that I do. But there are also things that are more biological in nature that touch on this, which is questions about what it means to be human.
The challenges are in how to incorporate this information, how to interpret it, how to predict, and this is where we need your help in terms of how to predict the changes in structure, what's deleterious, what's not, and also what we desperately need of our translators, people who can act between the science and the person in the community to translate this information. We have to make sure this information is not lost in translation.
We sit in these physical bodies, where for a physicist these are collections of bits that store the states of the variety of things that we hold dear. all of our emotions and dreams somehow resolve down to the states of memory registers somewhere in our consciousness or in our brains and our bodies. It's intriguing to me the possibility that you might be able to replicate that in a different substrate.
This is leading, and the advances in technology is leading to a whole rewriting of medicine. We used to think about cancer as one disease. We now know that breast cancer is 25 diseases, not so much defined by what you see under a microscope, but rather what you see by the layers of changes of DNA and RNA expressed in different ways at different types of disease. And the exciting part of that is that this leads to approaches to therapy. We're now beginning to understand why it is that some people respond well to a drug and other people don't, and yet the cancer looks the same. It's a certain cancer. Or why certain people have certain genetic traits that lead them to have an adverse event to a drug. And we're beginning to understand that.
So these things 10 years ago, maybe even to a certain extent today, sound like that they might be the realm of strange science fiction, but I don't think they are anymore. So as we learn more and more about the science of biological systems, I think that the mysteries start to become not exactly stripped away, but much more precise. So you can put your fingers on exactly what's happening in all of these different things. The more we understand about that, the more we'll be able to affect it and remove things like disease and ultimately things that are even at a meta level from disease, things like aging, and then ultimately maybe conquer those things at some point.
So the title of this talk is Quantum Life. It's about how quantum mechanics plays an unexpectedly important role in living systems. Of course, everything is quantum mechanical. Quantum mechanics is the theory of physics that describes things at their most fundamental level. So we're all quantum mechanical. Living things, dead things, everythings. But until very recently, it was thought that, well, okay, chemistry is quantum mechanical, but living things are big, hot, wet, inimical environments to quantum mechanics. And, we have these molecules, we can describe them pretty classically, like balls on springs bouncing around or like locking into each other and stuff like that. So it was thought until quite recently that the kind of like quantum weirdness, which plays an important role in things like quantum computing, which is my own field, played very little role in actual living systems. Then, about 3.5 years ago, a very beautiful experiment done by the Fleming group, Graham Fleming's group in Berkeley, showed that quantum mechanics and quantum coherence and quantum entanglement and wacky stuff like that was playing a very important role in photosynthesis. In fact, it was important for, it was what caused photosynthesis to be so efficient, the collection of light.
Since this is a quantum biology workshop, I thought I'd motivate a little bit and give, start at the beginning and talk about quantum biology and what it should mean or what it does mean. And the way I like to think about it, I like to classify it into 3 levels of quantum influence in biological systems. So going down the list here, the first one is the trivial. Since we believe quantum mechanics is the theory of microscopic systems, then everything is quantum mechanical at some level, right? But that's at this level of reductionism, you can't really add much to knowledge. Quantum mechanics dictates energy levels, molecular orbitals, and so on. But does that really tell us anything new? The next level up, which is more interesting, is the level of molecular dynamics and chemical kinetics. So, for the vast majority of systems of biological interest, you can describe chemical kinetics, molecular dynamics by just classical physics, right? But in a few cases, there are quantum corrections which turn out to be significant. And then the next level, which is maybe the most tantalizing, is where quantum mechanics becomes a functional necessity. Okay, the division between these two is kind of hazy. Where you throw one and where you throw the other is not clear. But at least the third class of quantum influence, you should be able to make a connection between if the quantum mechanics wasn't there, if the system was entirely classical, the organism wouldn't be able to survive, right? And I've listed some examples or some potential examples from this class. the way geckos hold on to things is maybe through van der Waals forces, magnetoreception on birds, olfaction, and finally photosynthetic light harvesting, which is what I'm going to focus on.
And so I'm going to tell you a bit about that, so about photosynthesis in bacteria. I'll tell you how quantum mechanics plays this funky role. Then, if I may not have time to cover all these things, but there's also a case where there's strong evidence that certain birds, in fact many birds, when they navigate, are using quantum effects in order to detect the orientation of the Earth's magnetic field. So this is called the avian compass, but I'm going to call it quantum bird brains for this. And then the final one, which I think for which there's indirect evidence where quantum mechanics is playing some funky role, is in the sense of smell.
These are the 5 atoms from which just about everything you're going to smell in real life, from coffee to fragrance, are made of. The top note that you smelled at the very beginning, this sort of cut grass green, what we call in perfumery, they're weird terms, and this would be called a green note because it smells of something green like cut grass. This is cis-3-hexenol. This has 6 carbon atoms, so hexenol. It has 1 double bond. It has an alcohol on the end, so it's all, and that's why they call it cis-3-hexenol. Once you figure this out, you can really impress people at parties. This smells of cut grass. Now, this is the skeleton of the molecule. If you dress it up with atoms, hydrogen atoms, that's what it looks like when you have it on your computer. But actually, it's sort of more like this in the sense the atoms have a certain sphere that you cannot penetrate. They repel. Okay. Now, why does this thing smell of cut grass? Okay. Why doesn't it smell of potatoes or violets? Well, there are really 2 theories. The first theory is it must be the shape. And that's a perfectly reasonable theory in the sense that almost everything else in biology works by shape. Enzymes that chew things up, antibodies, it's all, the fit between a protein and whatever it is grabbing, in this case a smell. And I will try and explain to you what's wrong with this notion. And the other theory is that we smell molecular vibrations. Now, this is a totally insane idea. And when I first came across it in the early 90s, I thought my predecessor, Malcolm Dyson and Bob Wright, had really taken leave of their senses. And I'll explain to you why this was the case. However, I gradually came to realize they may be right. And I have to convince all my colleagues that this is so, but I'm working on it. Here's how shape works in normal receptors. You have a molecule coming in, it gets into the protein, which is schematic here, and it causes this thing to switch, to turn, to move in some way by binding in certain parts. And the attraction, the forces between the molecule and the protein cause the motion. This is a shape-based idea. Now, what's wrong with shape is summarized in this slide. The way, I expect everybody to memorize these compounds. This is 1 page of work from a chemist's workbook, okay? Working for a fragrance company. He's making 45 molecules, and he's looking for a sandalwood, something that smells of sandalwood, because there's a lot of money in sandalwoods. And of these 45 molecules, only 4629 actually smells of sandalwood, and he puts an exclamation mark, okay? This is an awful lot of work. This actually is roughly a man-year's of work, $200,000 roughly if you keep them on low salaries with no benefits. So this is a profoundly inefficient process. And my definition of a theory is not just something that you teach people, it's labor saving. A theory is something that enables you to do less work. I love the idea of doing less work. So let me explain to you a very simple fact that tells you why this shape theory really does not work very well. This is cis-3-hexenol. It smells of cut grass. This is cis-3-hexenethiol, and this smells of rotten eggs. Okay? Now, you will have noticed that vodka never smells of rotten eggs. Okay? If it does, you put the glass down, you go to a different bar. In other words, we never get the OH, we never mistake it for an SH. Okay, like at no concentration, even pure. You know, if you smell pure ethanol, it doesn't smell of rotten eggs. Conversely, there is no concentration at which the sulfur compound will smell like vodka. It's very hard to explain this by molecular recognition. Now, I showed this to a physicist friend of mine who has a profound distaste for biology. He says, that's easy, the things are a different color. And, but we have to go a little beyond that. Now, let me explain why vibrational theory has some sort of interest in it. These molecules, as you saw in the beginning, the building blocks had springs connecting them to each other. In fact, molecules are able to vibrate at a set of frequencies which are very specific for each molecule and for the bonds connecting them. So this is the sound of the OH stretch translated into the audible range. SH, quite a different frequency. Now, this is kind of interesting because it tells you that you should be looking for a particular fact, which is this. Nothing in the world smells like rotten eggs except SH. Okay? Now, fact B. Nothing in the world has that frequency except SH. If you look on this imaginary piano keyboard, the SH stretch is in the middle of a part of the keyboard that has been, so to speak, damaged, and there are no neighboring notes. Nothing is close to it. You have a unique smell, a unique vibration. So I went searching when I started in this game to convince myself that there was any degree of plausibility to this whole crazy story. I went searching for a type of molecule, any molecule, that would have that vibration, and the obvious prediction was that it should absolutely smell of sulfur. If it didn't, the whole idea was toast, and I might as well move on to other things. Now, after searching high and low for several months, I discovered that there was a type of molecule called a borane, which has exactly the same vibration. Now, the good news is boranes you can get hold of. The bad news is they're rocket fuels. Most of them explode spontaneously in contact with air. And when you call up the companies, they only give you minimum 10 tons. Okay? So this was not what they call a laboratory scale experiment, and they wouldn't have liked it at my college. However, I managed to get a hold of a borane eventually, and here is the beast. And it really does have the same, if you calculate or if you measure the vibrational frequencies, they are the same as SH. Now, does it smell of sulfur? Well, if you go back in the literature, there's a man who knew more about boranes than anyone alive then or since, Alfred Stock. He synthesized all of them. And in an enormous 40-page paper in German, he says, at one point, and my wife is German, she translated it for me, and at one point he says, ganz widerlich Geruch, an absolutely repulsive smell, which is good, reminiscent of hydrogen sulfide. So this fact that boranes smell of sulfur had been known since 1910 and utterly forgotten until 1997, 98. Now, the slight fly in the ointment is this, that if we smell molecular vibrations, we must have a spectroscope in our nose. Now, this is a spectroscope, okay, on my laboratory bench. And it's fair to say that if you look up somebody's nose, you're unlikely to see anything resembling this. And this was the main objection to the theory. Okay, great, we smell vibrations. How? All right? Now, when people ask this kind of question, they neglect something, which is that physicists are really clever, unlike biologists. And two of them, this is a joke. I'm a biologist, okay? So it's a joke against myself. Bob Jaklovich and John Lamb at Ford Motor Company, in the days when Ford Motor was spending vast amounts of money on fundamental research, discovered a way to build a spectroscope that was intrinsically nanoscale. In other words, no mirrors, no lasers, no prisms, no nonsense, just a tiny device. And they built this device. And this device uses electron tunneling. Now, I could do the dance of electron tunneling, but I've done a video instead. It's much more interesting. Here's how it works. Electrons are fuzzy creatures, and they can jump across gaps, but only at equal energy. If the energy differs, they can't jump. Unlike us, they won't fall off the cliff. Okay. Now, if something absorbs the energy, the electron can travel. So here you have a system, you have something, and there's plenty of that stuff in biology, some substance giving an electron, and the electron tries to jump, and only when a molecule comes along that has the right vibration does the reaction happen. Okay? This is the basis for the device that these two guys at Ford built. And every single part of this mechanism is actually plausible in biology. In other words, I've taken off-the-shelf components and I've made a spectroscope. What's nice about this idea, if you have a philosophical bent of mind, is that then it tells you that the nose, the ear, and the eye are all vibrational senses. Of course, it doesn't matter because it could also be that they're not. But it has a certain it has a certain ring to it, which is attractive to people who read too much 19th century German literature. And then a magnificent thing happened. I left academia and joined the real world of business. And a company was created around my ideas to make new molecules using my method, along the lines of, let's put someone else's money where your mouth is. And one of the first things that happened was we started going around the fragrance companies asking for what they needed, because, of course, if you can calculate smell, you don't need chemists. You need a computer. A Mac will do it if you know how to program the thing right, okay? So you can try 1,000 molecules. You can try 10,000 molecules in a weekend, and then you only tell a chemist to make the right one. And so that's a direct path to making new odorants. And one of the first things that happened was we went to see some perfumers in France, and here's where I do my Charles Fleischer impression. And one of them says, "You cannot make a coumarine," he says to me. "I bet you cannot make a coumarine." Now, coumarin is a very common thing, a material in fragrance, which is derived from a bean that comes from South America. And it is the classic synthetic aroma chemical. Okay? It's the molecule that has made men's fragrances smell the way they do since 1881, to be exact. And the problem is, it's a carcinogen. So nobody likes particularly to, aftershave with carcinogens. There are some reckless people, but it's not worth it. Okay? So they asked us to make a new coumarin. And so we started doing calculations. And the first thing you do is you calculate the vibrational spectrum of coumarin, and you smooth it out so that you have a nice picture of what the sort of chord, so to speak, of coumarin is. And then you start cranking the computer to find other molecules, related or unrelated, that have the same vibrations. And we actually, in this case, I'm sorry to say, it was serendipitous, because I got a phone call from our chief chemist, and he said, "Look, I just found this such a beautiful reaction that even if this compound doesn't smell of coumarin, I want to do it. It's just such a nifty one step." I mean, chemists have weird minds. One step, 90% yield, and you get this lovely crystalline compound. Let us try it. And I said, well, first of all, let me do the calculation. On that compound, bottom right, which is related to coumarin but has an extra pentagon inserted into the molecule. Calculate the vibrations. The purple spectrum is that new fella. The white one is the old one. And prediction is it should smell of coumarin. They made it, and it smelled exactly like coumarin. And this is our new baby called Tonkin. You see, when you're a scientist, you're always selling ideas. And people are very resistant to ideas. And rightly so. Why should new ideas be accepted? But when you put a little 10-gram vial on the table in front of perfumers, and it smells like coumarin, and it isn't coumarin, and you found it in 3 weeks, this focuses everybody's mind wonderfully. Okay?
This is really actually quite hard to believe, but it is nonetheless the case. And the primary proponent of this theory is a wonderful fellow named Luca Turin. He was giving a talk at a recent conference on quantum biology that we organized at Harvard, and the title of the talk was "Is Smell Quantum?" But when the chair got up to announce the talk, he said, "Luca Turin will now talk about I smell a quantum." So that's the topic of the 3 topics I'm going to cover. I'm going to spend most of my time on photosynthesis, maybe a brief time on quantum bird brains, and then because I smell a quantum is just such a fun thing to talk about, I'll talk about quantum mechanics of smell. And all of these things in life, when quantum living systems are using quantum mechanics, they're basically using it for what all living systems use stuff for, which is to have more sex, right? Or at least have more offspring, okay? So when you're using quantum mechanics to improve your ability to reproduce, I call this quantum hanky-panky. Quantum hanky-panky occurs when things are using quantum mechanics to get an edge up on their fellow living things. All right? And in fact, you can kind of see, before I describe why quantum hanky-panky is out there, and it's probably in many more places than we know, in retrospect, it's sort of weird that people didn't think that things like bacteria might be using quantum mechanics. Because, you know, if you're an organism that's reproducing, you know, and you can decrease your doubling time or increase your efficiency of reproduction by even 1%, then after 100 generations, you're the king of the heap or the queen of the heap, assuming bacteria come in heaps. And in fact, these bacteria that I'm going to talk about are sulfur-breathing bacteria that live on the bottom of the ocean in hot water vents, where a photon comes by only about every half hour or so. So you can see the strong evolutionary pressure towards efficiency in these bacteria, because, you know, here's you know, the bacteria. Bacteria is like, I caught a photon. Thank God that finally the children will eat. Oh, shoot, I dropped it. Oh, no. Oh, you idiot. Oh, the children, you dropped the photon. The children will starve, right? So simply for, you know, for spousal relations amongst bacteria, it's extremely important to use any bit of efficiency that you possibly can. And as it turns out, these bacteria have become extremely sophisticated at developing quantum mechanical techniques.
We were motivated to look at this by statements like this that came out right after the experiments were done in 2007. So people made the analogy to quantum computation in these systems, saying that, well, plants are actually performing a quantum computation in the process of absorbing energy. And for anyone who works in quantum computing, that's my background, this is a very striking statement. If you're talking to experimentalists, they've spent years and years, you know, building up a single qubit to do virtually nothing. And so, you know, it's very kind of I mean, almost insulting if you talk to a quantum computing experimentalist to say that such a messy system is performing quantum computation.
So now let's look at photosynthesis. And let me describe to you how it works. I have a nice green pen here. Photosynthesis is a process whereby plants and animals like bacteria take light from the sun and turn it into usable chemical energy. It's a pretty amazing process. You know, there's sunlight coming in, it's got a lot of energy, and somehow this sunlight has to be turned into chemical bonds and things like sugars. How does that work? That's pretty remarkable. So what happens is photosynthetic complexes are called complexes for a reason, that they're complex. A typical one, and this is the one for, maybe I should draw it. This is for purple sulfur bacteria, so I'll draw it in purple. So it's got all these weird ring-shaped molecules these are called LH2. And, you know, they're in some kind of they're embedded in a membrane in some funny way, not in a very regular way. And then there's a big set of rings in the middle. In the middle of this is some funny set of stuff. And in here is what's called the reaction center. And this is where this action is going to take place. This is where the chemical bonds are going to be made. So, but let me ask you a question. So why are purple bacteria purple? What color light do they absorb? I'm sorry? Not purple. That's right. That's the answer. They absorb stuff like, let's say, they absorb things that are, let's say, like bluish or reddish light that is not purple. So let's draw the right color, because they're purple because they reflect the purple light, right? Okay. So in comes a photon. This is a particle of light, a photon. And the photon creates a nice little exciton. So an exciton, I'm going to draw it. It's an exciton. I mean, it's kind of a cool name, right? You know, anything that has an "on" at the end, that's like a quantum particle. You know, photon, phonon, electron, proton. So an exciton is a little particle of excitement. Very, very, very apropos for quantum hanky-panky, if you think about it. So it creates this exciton, and the exciton is actually a little bound electron hole pair. So it takes an electron, it pops it out of where it's sitting. The electron goes over here and it leaves a hole. The electron is negatively charged, the hole is positively charged. And these have a lot of energy, a substantial fraction of the energy in the original photon. Okay? They're actually, when I say they're about this far apart, it's not true. These are a few angstroms apart. All right? But this exciton somehow has to make it through this whole complex and get somehow eventually to here and get to the reaction center where it can be turned into chemical energy. Now, this process of hopping hither and thither through this complex, well, I don't know if you'll be able to see this. So this process is, the hopping process is 99+% efficient. Now, not all photons are absorbed. Not all of the energy in the photon can make it into the exciton. Typically, about 80 or 90% of it, maybe a bit more, actually. And actually, the reaction center is very inefficient, so the actual fabrication of chemical bonds from the energy in the excitons is only like 3 to 7% efficient, maybe 3 to 5% efficient. This, by the way, if you think that we're going to grow our way out of our energy crisis using biofuels, should make you think twice. Because, photocells, even like commercial photocells are already like, 12 to 15% efficient in taking energy. And so even if you just get the biomass alone, you've already lost more than 95% of the energy. I know that this is a place around here that they grow lots of wheat and stuff like that, or corn, but I'm sorry, you've got to be careful about that. So, but this process, this transport process, is 99+% efficient. And that's kind of weird, because if you just think, first of all, I actually even drawn this correctly because these excitons, I should say, each of these rings contains they contain 27 places where the exciton could be. These are called chromophores, which is Greek for something that carries color. So 27 places where the exciton could live. And then there are many tens of rings. So there are hundreds and hundreds of places that this exciton can hop through here. And if you just ask, if this exciton were kind of like to wander around randomly, jiggle around in this ring right here, sloshing back and forth, and then hop over this other one and slosh back and forth here, hop over here and slosh back and forth, it wouldn't have time to make it to this reaction center. It would decay. And then you get back to these, bacterial spousal relation problems, you're losing the energy that comes in. This has, for many decades, been a big mystery about photosynthesis. How can this be so efficient? Can this transfer process be so efficient? I bet you know the answer. Well, the answer is, of course, quantum hanky-panky, right? Quantum hanky-panky. So, in fact, the answer lies in what we in quantum computation call a quantum algorithm, a way of processing information in a coherent fashion. So what the Fleming group claimed is that these bacteria were performing what's called a quantum search algorithm. Now, how does quantum search work?
So this talk is going to require like a 5-minute crash course in some of the fundamental concepts of my own field of computational complexity theory. Okay, so I'll go quickly through this. Okay, but basically in theoretical computer science, in the field of complexity theory, we're interested in problems and in how fast you can solve them or what kind of resources you need to solve them. Okay, now what do we mean by a problem? Well, the standard example would be just some infinite sequence of yes or no questions. Okay, so for example, I would give you a flight map, and I would ask you, is every airport reachable from every other one in 5 flights or less? Okay, so, a simple question. Now, an important point, any particular map is just an instance of the general problem. Okay, the set of all possible maps, now that's a problem. Okay, computer scientists are a little bit, snobbish about this. Okay, give me an infinite family of things. Okay, that's a problem. Okay, and so, what you'd like is some general method or algorithm or procedure that solves any given instance of the problem. Of course, for this or that particular instance, you may find some clever way. Maybe you can even do it on pencil and paper. But, you want a general procedure that you could feed to your computer that always works. Okay, now, the size of an instance usually just means the number of bits needed to write it down. Okay, or you can think interchangeably, like in this example, the size of the instance is going to be roughly the number of cities. Okay, and now we would like algorithms that solve these problems, and usually, there's some trivial way to solve it, which is that you could just enumerate all of the possibilities. Okay, but we don't want that. We want some way to solve the problem efficiently. Okay, now, so what do we mean by efficient? We have this notion called polynomial time. An algorithm is polynomial time if it uses a number of steps that grows basically like the size of the instance to some fixed power. Okay, so it could grow like n or like n squared. That's also okay. It could even grow like n to the 100, which doesn't sound very efficient, but it doesn't tend to come up very often in practice. Okay, what it shouldn't do is grow like 2 to the n. Okay, that's exponential growth, and that's what we don't want. Okay, so now, Fred mentioned this complexity zoo. It has about 500 different classes of problems solvable with different resources, but maybe the most fundamental one that started it all is called P. Okay, it's polynomial time. And this is simply the class of all problems for which there's a deterministic polynomial time algorithm on a conventional computer that solves every instance.
Polynomial time means there's an algorithm where the problem comes in, you measure the size, for example, by the number of bits required to describe the... Have you already had all this material? You're shaking your head. Okay, fine, okay. Because then I could be way fast. So you measure by the number of bits required to describe the data. And then you look at the number of operations you have to do, and if you can bound that by a polynomial, then you'd say, well, that's polynomial time. Now, bear in mind, I'm compressing a 10-week course to about 14 seconds, so that means some of the details I'm going to have to gloss over.
NP is basically just the class of all problems for which you can efficiently recognize an answer if it's given to you. Okay, so if the answer is yes, there should be a short proof that it's yes, which can be checked in polynomial time. Okay, so it might be very hard to solve the problem, but at least you can recognize the answer. A classic example of an NP problem would be factoring a giant integer, like that one here. Okay, so I could ask you some yes or no question, like does this number have a prime, or have any factor, let's say, ending in 7? Okay, and now, if I gave you this problem and asked you to solve it, it might take an astronomical amount of time. You could say, well, does 3 go into it? No. Does 5 go in? No. Does, you'll be doing that for a while. Okay, but on the other hand, if I gave you the factors, then, you could multiply them together and say, oh, well, I guess it did have a factor ending in 7. Okay, that wouldn't be as hard of a computation. Certainly not for a computer. It can multiply numbers pretty quickly.
If we say some quantity is divisible by 4, then it implies that we can form 4 equal size pieces. Now, in order to hunt successfully, our ancestors needed a way to predict animal migration patterns and plan future hunts. How could they predict the most successful times to hunt? This question leads to one of the oldest and most powerful human technologies, the clock. All clocks are based on some repetitive pattern which divides the flow of time into segments. To find repetitive patterns, they look towards the heavens. The most obvious cycle is the rising and the falling of the sun each day. However, they would have required longer cycles to track longer periods of time. For this, they look to the moon, which seemed to gradually grow and shrink over many days. And every so often, a beautiful event would occur, a full moon. But was the period between one full moon to the next constant? To answer this, they needed a method of counting. Ancient artifacts show they counted this pattern using notches, or numerals. Each numeral would represent one unit, such as one day. Grouping these units together allowed them to build numbers. Numbers allowed our ancestors to calculate exactly 29 days between each full moon. This is the origin of a month. However, when they tried to divide 29 into equal parts, they ran into a problem. It was impossible. No matter how hard you try, you could not split 29 into equal pieces. We could say that 29 is unbreakable. Unbreakable numbers are known as prime numbers. Imagine that our hunter was mathematically curious. As he continued his day, he couldn't stop thinking about these prime numbers. How many other numbers are prime? How big do they get? First, he tries dividing all numbers into two categories. He lists prime numbers on the left and other numbers on the right. The first thing a mathematician would do is look for patterns. At first, they seemed to dance back and forth in a strange pattern. He was onto something. Now, let's do a modern trick to see the bigger picture. The trick is to use a spiral. First, we list all possible numbers in a growing spiral. Then we color all the prime numbers blue. Finally, we zoom out to see millions of numbers. Here is one of the great examples of true mathematical beauty. This is a pattern of primes, which goes on and on forever. Incredibly, the structure of this pattern is still unsolved today. This idea was finally advanced sometime around 300 BC in ancient Greece with a philosopher known as Euclid of Alexandria. Euclid understood that all numbers split into two distinct categories: prime numbers, which we cannot share equally, and composite numbers, which we can. He begins by realizing that any number can be divided down until you reach a group of smallest equal numbers. And by definition, these smallest numbers are always prime numbers. To be clear, imagine the universe of all possible numbers and ignore the primes. Now, pick any composite number and break it down. You are always left with prime numbers. Euclid knew that every number could be expressed using a group of smaller primes, or building blocks. No matter what number you choose, it can always be built with addition of smaller primes. This is the root of his discovery, known as the fundamental theorem of arithmetic. As follows: take any number, say 30, and find all the prime numbers it divides into equally. This is known as factorization. This will give us the prime factors. In this case, 2, 3, and 5 are the prime factors of 30. Euclid realized that you could then multiply these prime factors a specific number of times to build the original number. In this case, you simply multiply each factor once to build 30. 2 times 3 times 5 can be thought of as a special key or combination for 30. So every possible number has one, and only one, prime factorization. A good analogy is to imagine each number as a different lock. The unique key for each lock would be its prime factorization. No two locks share a key. No two numbers share a prime factorization.
All right, so now there's this concept of an NP-hard problem. A problem is called NP-hard, basically if it captures the difficulty of every NP problem. So basically these are the problems that if you had a way to solve them, then you could use that to solve all of the NP problems.
So there were a bunch of problems where people just didn't, like the famous one would be traveling salesman problem. Okay, and no one had found a polynomial time method. Okay, so someone said, well, I don't know, a guy named Cook maybe, or I don't know the history, because anyway. So did the following. He actually cataloged like a whole bunch of problems and said, look, you know what? If you can solve sort of any of these, then if you make a method for solving that, I can make a reduction. I can take your problem and map it to this, and with that I could solve, for example, the traveling salesman problem. Okay? So then you could have had an intelligent way of saying two problems are just one is as hard as the other, or one is more hard. Okay. NP hard means, and this is really, people are going to cringe if they actually have a background in this. It means it's at least as hard as a whole bunch, a catalog of very hard, of problems thought to be very hard, because there's an asterisk, which I have to give. Okay, so
the traffic is like your prototypical.
that's a prototype. That's your prototype. So basically, and I mean, what I'm saying is actually not true, but as a working definition of what it means, for your purposes, this is going to be fine. It means the problem is at least as hard as, for example, traveling salesman. And let's just leave it that way.
Okay, now the final concept is a problem is called NP complete if it's both NP hard and it's in NP. Okay, so basically the NP complete problems are the hardest problems for which it's easy to check the solution. Okay? So, you know, you have to think about that for a bit. But this sounds like just playing around with words. But the profound discovery that people made in the 1970s that really started this whole field of complexity theory, in its sort of modern incarnation, was that a huge number of practical problems that people care about, actually belong to this NP complete class. Okay, so. Problems from physics, from economics, from biology, from, all kinds of fields. Now one famous example is what's called the Hamilton cycle problem. Okay, so here I would show you a map like this with a bunch of cities, the yellow dots, and some are connected to each other. And I would ask you, is there a tour that visits each city exactly once? Okay, now in this case there is one. It's that. Okay, and if I show it to you, then it's not hard to check it and say, yes, indeed, it solves the problem. Okay, but if I don't show you the tour, then you may have to think about it. And as the number of cities increases, the difficulty of the problem may increase a lot. Okay, it's like, or think of solving a jigsaw puzzle. That's another example of an NP complete problem. Okay, or Sudoku is another. Okay, and also, many other problems of more economic importance.
After World War II, with most of Europe in ruins, tensions grew between the Soviet Union and the United States. It was clear that the next global superpower required the ability to both launch and successfully defend nuclear attacks from intercontinental ballistic missiles. The United States' most vulnerable point of attack was over the North Pole. So, in 1958, a joint effort between United States and Canada was established, NORAD, the North American Aerospace Defense Command. An important line of defense was the semi-automatic ground environment. It was an automated system of over 100 long-distance radars scattered across North America. They were connected to computerized radar systems that transmitted tracking data using telephone lines or radio waves. All this information was fed into the primary warning center buried deep inside Cheyenne Mountain in Colorado. This application of machine-to-machine communication allowed operators to make split-second decisions using the information transmitted and processed automatically by computers. This idea of being online was quickly adapted and advanced by universities in the following years, as they understood the potential of computer networking.
The thing that makes the computer communication network special is that it puts the workers, the team members who are geographically distributed, in touch not only with one another, but with the information base with which they work all the time. And this is obviously going to make a tremendous difference in how we plan, organize, and execute almost everything of any intellectual consequence. If we get into a mode in which everything is handled electronically and your only identification is some little plastic thing you stick into the machinery, then I can imagine that they want to get that settled up with your bank account just right now and put it through all the checks, and that would require a network.
Money transfers were just one of a growing number of applications which require encryption to remain secure. As the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required two parties to first share a secret random number, known as a key. How could two people who have never met agree on a key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. 1. It's easy to mix two colors together to make a third color. And 2. Given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now the solution works as follows. First, they agree publicly on a starting color. Let's say yellow. Next, Alice and Bob both randomly select private colors and mix them into public yellow in order to disguise their private color. Now Alice keeps her private color and sends her mixture to Bob. And Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrive at a shared secret color. Notice how Eve is unable to determine this color, since she needs one of the private colors to do so. And that's the trick. Now to do this with numbers, we need a numerical procedure which is easy in one direction and hard in the other. This brings us to modular arithmetic, which is also known as clock arithmetic. For example, to find 46 mod 12, we take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus. And where the rope ends is the solution. So we say 46 mod 12 is congruent to 10. Easy. Now to make this work, we need a prime modulus such as 17 instead of 12. Then we find a primitive root of 17, in this case 3, which has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. So if we raise 3 to any exponent x, the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function. Easy to perform, but hard to reverse. Given 12, we would have to resort to trial and error to find the matching exponent. How hard is this? With small numbers, it's easy. But if we use a prime modulus, which is hundreds of digits long, it gets seriously hard. Even if you had access to all computational power on Earth, it could take thousands of years to go through all possibilities. So the strength of a one-way function is based on time needed to reverse it. Now this is our solution. First, Alice and Bob agree publicly on a prime modulus and a generator, in this case 3 and 17. Then Alice selects a private random number, say 15, and calculates 3 to the power of 15 mod 17 and sends the result publicly to Bob. Then Bob selects his private random number, 13, and calculates 3 to the power of 13 mod 17 and sends the result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number to obtain the shared secret, which in this case is 10. Bob takes Alice's public result and raises it to the power of his private number, resulting in the same shared secret. Now notice they did the same calculation, though it may not look like it at first. First, look at Alice. The 12 she received from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power of 13 to the power of 15 mod 17. Now look at Bob. The 6 he received from Alice was calculated as 3 to the power of 15 mod 17. So his calculation was the same as 3 to the power of 15 to the power of 13 mod 17. Notice they did the same calculation with the exponents in a different order. They both end up with 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve will not be able to find the solution. This is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers we can say it's practically impossible for her to break the encryption.
So, what kinds of things can you do with this kind of quantum computation? Well, a famous example of this is Peter Shor's algorithm for factoring large numbers, which would allow you to break all the codes that people use to send information over the internet, which would be kind of a bummer because you couldn't buy stuff from Amazon.com any longer. So this is what would be a disruptive technology. But another famous algorithm is quantum search algorithm. And the idea is like this. It's like, I forget which pocket I put my wallet in. Is it there, 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 there? If you try and look for your wallet, then the classical search method is you look around till you find it. And if there are 10 pockets it could be in, then you have to look on average 5 different places where it's going to before you find it. Now, if you use this funky quantum mechanical ability to search in different places simultaneously, then you can actually find it much faster. So if you have 100 pockets, classically it takes 50 tries, quantum mechanically it takes something like 8 or 9. And if you have 1,000,000 pockets, quantum mechanically it takes 1,000 tries. It goes as the square root of the number of pockets, which is a pretty cool thing. Can't possibly do this classically. So these guys, the Fleming group said, the bacteria, this exciton, when it's trying to go from here to there, is doing quantum search. It's like this is where the pocket where the wallet is, and it looks at all these pockets simultaneously to find that there. Now, this is actually a very cool idea, that bacteria are performing quantum search. And the problem is that it's incorrect. This is not what bacteria are doing to get this exciton from here to there. But as soon as Alan Asper-Gusick and I looked at the problem, we realized that the bacteria are actually performing what's called a quantum walk. This is another kind of algorithm. And let me describe to you how it works. This should be more visual. So in a way, I already described to you what is a classical walk or a classical random walk. So if we have a random walk, I already described to you this picture that this exciton might be doing a classical random walk through this complex. And how does a classical random walk work? Well, it's like, like imagine that you've had too many Molsons, and you're trying to find your apartment door, and it's like, but you are not very clear on where it is, and you kind of are wandering around left to right at random, and then it's like, oh, there it is, thank goodness, right? It takes a long time. Right? Because, in fact, you're going this way as often as you're going that way, and you're gradually spreading out. But, in fact, it turns out you're only spreading out as the square root of the number of steps that you're going. So if your apartment is a long way away, you might never get there. Now, so a classical random walk, you take one random path, and it takes you a while to get where you're going. And I already told you that in the case of photosynthesis, that this is not good enough. So what about a quantum walk? Or a quantum random walk? In a quantum random walk, what happens is you don't just take one path, you take all possible paths at once through this complex. So you're not just taking one path, but many, many, many paths. But each of these paths can affect where you come. So the actual probability of ending up at your destination is kind of a quantum sum of all the probabilities or probability amplitudes for all the different paths. Now, it turns out that these quantum random walks a quantum random walk is much more efficient than a classical one. Indeed, under the assumption that I could drink some quantum Molsons, all right, so I could take, in my drunken state, I could take all possible paths in some quantum mechanical sense from here to my apartment. I would just go like that. There it is. In you go. So quantum random walks have this feature that even though they look random, they're actually very efficient at getting from one place to another. Let me turn to this original paper, which is about green sulfur bacteria. And let me actually tell you what we did and what the experiment was. So in these green sulfur bacteria, by the way, in case you think these things are rare, green sulfur bacteria and purple sulfur bacteria make up something like 40% of the biomass on the planet. So, and all that green stuff out there is also doing very similar kinds of things. So it's not just like, they're just like a few of these dudes hanging out at hot sea bents looking for some action. So the way this works is up here, there's a huge cylinder. Well, it's not huge. It's like a micron in size, but huge compared with this other stuff. There's this thing called the chlorosome, which is the antenna where the exciton, the photon is absorbed and the exciton is created. And the reaction center is down here. And then there's this thing called, you can see, if you want a better picture, go to Google Images. The FMO complex, or Fenner-Myers-Olsen complex. And what the Fleming group had observed was coherent sloshing back and forth, a so-called quantum tunneling or quantum beating of an exciton moving back and forth between these two sites right here. So each of these is a place where an exciton can live. There's 7 of them. And somehow the exciton has got to get for this, this E plus minus has got from up here through the center and down to the reaction center. Okay? So it's kind of a communications channel for sending. This big, huge thing up here is huge. These things are 1,000 times smaller. There's a lot of them and a lot of reaction centers. So the energies of the excitons, as they sit on these different chromophores, color-carrying or exciton-carrying systems, the energies of these excitons is known to a high degree of accuracy. The rate at which an exciton can hop coherently from one place to another is known very accurately. And the structure of the environment, these things are actually embedded in some protein skeleton, the structure of this environment is also known to a high degree of accuracy. So we were able to make a quantum mechanical model that used no free parameters. So all the parameters in the model were taken from experiment. And then we investigated the behavior of this model. The only parameter that we could vary was the temperature. Okay? So we investigated so this is exactly the kind of model where things will take these quantum walks. And the quantum walk can be helped or destroyed. It can be destroyed by the presence of disorder in the system and also destroyed by environmental interactions. So we did a 0 free parameter calculation, and we looked at the following graph. So as a function of temperature, this is 0 down here, we looked at the efficiency. And then we also looked at the time it took to traverse this, okay? So I'm going to make efficiency in blue and time in red. Okay, so I predicted that because of disorder in the energies of the molecules, these excitons would undergo something that's called localization, which is that these paths, instead of interfering positively to get them to the end, would interfere destructively and they just get stuck. So for low temperatures, my prediction was this wouldn't be very efficient. Then, as the environmental interactions kicked in, it would gradually destroy this process, and the system would be doing a semi-coherent quantum walk, kind of like mixing the regular Molson with the quantum Molson, semi-coherent quantum walk through this structure, and then the efficiency would go up.
First of all, I would like to thank Google for organizing this really cool workshop. And yeah, I will talk a lot about information, and going to Google and talk about information feels very interesting. The main goal of DNA molecules is a long-term storage of information. So the last sentence, that sounds rather innocent, actually contains two very interesting concepts. So the first concept is information, and the other one is long-term storage. So what does it mean, long-term storage? It means that we have some information, whatever information is, in the past, and we would like to send this information into the future. That's long-term storage. And the way we send it from past to future can be described by a channel. And a channel is a very general description of whatever happens to your information. So, what is information?
Claude Shannon was a true maverick, and his desire to tackle unusual problems would lead to a revolutionary new idea, one that would uncover the fundamental nature of information and the process of communication in all its varied forms. This is Claude Shannon's paper, A Mathematical Theory of Communication. Now, the title may sound a bit dry, but trust me, it's one of the most important scientific papers of the 20th century. Not only did it lay the foundations for the modern world's communication network, it also gave us fresh insights into human language, into things we do intuitively, like speaking and writing. The paper was published in 1948, while Shannon was working at the Bell Labs in New Jersey, the research arm of the vast Bell telephone network. It was an institution famous for its forward-thinking, relaxed atmosphere.
The mathematicians were free to work on any problem that interested them. The only thing that the laboratory management required of them is that they keep an open door, and if anybody from any other department came with a problem, that they would at least think about it. Otherwise, they were absolutely free, and the atmosphere was incredible. People were playing and encouraged to play.
Hello, I'm Claude Shannon, a mathematician here at the Bell Telephone Laboratories.
Claude Shannon, in particular, was given free rein to do pretty much whatever he wanted.
This is Theseus. Theseus is an electrically controlled mouse.
Oh, they treated him as their darling. I never saw him juggle, but I certainly saw him ride his unicycle. He brought it to work one day, and he must have cost Bell Labs at least 100 man-hours of time.
But despite the frivolity, the Bell telephone network faced a huge problem. Every day, they transmitted vast amounts of electronic information all across the world. But they had no real idea of how to measure this information properly or how to quantify it. In short, their entire business was built on something they didn't actually understand. Amazingly, their superstar employee, Claude Shannon, would give them exactly what they needed. In this paper, Shannon did something absolutely incredible. He took the vague and mysterious concept of information and managed to pin it down. Now, he didn't do this using some cleverly worded philosophical definition. He actually found a way to measure the information contained in a message. Amazingly, Shannon realized that the quantity of information in a message had nothing to do with its meaning. Instead, he showed it was related solely to how unusual the message was.
Information is related to unexpectedness. So news is news because it's unexpected. And the more unexpected it is, the more newsworthy it is. So if today's news was the same as yesterday's news, there would be no news at all. And the information content would be zero. So suddenly you have a relationship between unexpectedness and information?
First of all, you can see it as negative entropy. So now I run into the problem that I have to explain you what is entropy.
Clausius realized that not only was there a fixed amount of energy in the universe, but that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction. This insight of his is in fact one of the most important ideas in the whole of science. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. This is a very intuitive idea. If left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand, and then again from my hand to my chest. This might seem completely obvious, but it was a crucial insight. The flow of heat was a one-way process that seemed to be built very fundamentally into the workings of the entire universe. Of course, objects can get hotter, but you always need to do something to them to make this happen. Left alone, energy seems to always go from being concentrated to being dispersed.
One of my favorite statements in science was made by the biochemist Albert St. George, who said that science is all about seeing what everyone else has seen, but thinking what no one else has thought. And he, Rudolf Clausius, looked at the everyday world and saw what everyone else had seen, that heat does not flow spontaneously from a cold body to a hot body. It always goes the other way. But he didn't just say, ah, I see that. He actually sat down and thought about it.
Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It could be summarized by this equation. Now, what Clausius did was introduce a new quantity he called entropy, this letter S. Basically, what it's saying in the context of this equation is that as heat is transferred from hotter to colder bodies, entropy always increases. Entropy seemed to be a measure of how heat dissipates or spreads out. As hot things cool, their entropy increases. It appeared to Clausius that in any isolated system, this process would be irreversible. Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos. He speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this. This idea became known as the second law of thermodynamics, and it turned out to be stranger and more beautiful, more universal than anything Clausius could have imagined. The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together. All things that gave off heat were part of an irreversible process that was happening everywhere. A process of spreading out and dispersing. A process of increasing entropy. It seemed that somehow the universe shared the same fate as a cup of tea.
The wonderful thing about the Victorian scientists is that they could make these great leaps, and that they could see that their study of a thermometer in a beaker actually could be extrapolated, could be enlarged to encompass the whole universe.
Despite the successes of thermodynamics, in the middle of the 19th century, There was great debate and confusion about the subject. What exactly was this strange thing called entropy? And why was it always increasing? Answering this question would take an incredible intellectual leap, but it would end up revealing the truth about energy and the many forms of order and disorder we see in the universe around us. Many scientists would tackle the mysterious concept of entropy, but one more than any other would shed light on the truth. He'd show what entropy really was and why, over time, it always must increase. His name was Ludwig Boltzmann. Boltzmann had been born in Vienna in 1844. It was a world of scientific and cultural certainty. But Boltzmann took little notice of the entrenched beliefs of his contemporaries. To him, the physical world was something best explored with an open mind. Boltzmann wasn't your stereotypical scientist. In fact, he had the kind of temperament that most people might associate with great artists. He was ruthlessly logical and analytical, yes, but while working, he'd go through periods of intense emotion, and these would be followed by terrible depressions, which would leave him completely unable to think clearly.
He had terrible sort of mental crises and breakdowns in which he really thought that the world was coming apart at the seams, and yet these were also accompanied by some of the most profound insights into the nature of our world.
Outside of mathematics, Boltzmann was passionate about music and was captivated by the grand and dramatic operas of Wagner and the raw emotion of Beethoven. He was a brilliant pianist and could lose himself for hours in the works of his favorite composers, just as he could lose himself in deep mathematical theories. Boltzmann was a scientist guided by his emotions and instinct, and also by his belief in the ability of mathematics to unlock the secrets of nature. It was these traits that would lead him to become one of the champions of a shocking and controversial new theory, one that would describe reality at the very smallest scales, far smaller than anything we could see with the naked eye. During the second half of the 19th century, a small group of scientists began speculating that at the smallest scales, the universe might operate very differently to our everyday experiences.
Entropy in general measures the ignorance you have about the system. If your system has zero entropy, you know everything about it. You have maximum information. If your entropy is large, there are certain things you do not know about it, and you have few information. And entropy is a well-established concept in information theory. So how do you use it? You choose an alphabet. That could be computational basis of 0 and 1 or anything else. Then in the next step, according to that alphabet, you count probabilities. And once you have that probability distribution, you can calculate the entropy of your choice. There's a whole family of it. Here I've shown you the Shannon entropy, which is widely used and very useful. But I'm a physicist. We can do the same in statistical physics. In that case, we choose our system of interest, and then we count the number of possible states, which is denoted by capital omega. And then we take the logarithm of that number, and kb is a constant. Don't care too much about the meaning. The massively interesting thing is that once all events are equally likely, those two definitions of entropy actually coincide. This is one of the many links between information theory and physics. So it's rather a combined science than something different. And in physics, we have the well-established second law of thermodynamics, And that tells you that in closed systems, entropy does not decrease. So if we translate that argument to information theory, we immediately know that in closed system, information cannot increase spontaneously. That's very important to know. Next thing I would like to point out that information is physical. Whenever you have a piece of information, it comes together with a physical carrier. That can be the piece of paper you are writing now at the moment, or it can be your hard drive on the computer. And for classical physics, for classical information, we know from everyday life, I can change that information carrier. I can write something on a piece of paper, I can scan it to my computer, and I can print it again. And if I didn't do obvious mistakes, I didn't lose any information. That's allowed by laws of classical physics. But as the information comes along with a physical carrier, the way I process information is bound to the laws of physics. So what happens if I choose my physical carrier to be smaller and smaller until I reach the quantum limit? Then the fascinating thing is that the way I process information changes according to the laws of quantum mechanics. So what does it mean? So one thing is that I cannot copy quantum information. I can only copy classical information. And whereas classical information reliably stores the information, in quantum mechanics I always have to find the coherence. It's always getting lost. So coming back to the problem of DNA to use a long-term storage, what I just told you, those 2 points would actually mean that quantum mechanics is not any good for DNA. And if you really want to store your genetic information safely, you should keep away from quantum mechanics. So what is a good point of it? Quantum mechanics allows you to do more. Classical mechanics is a special case and only has a certain set of manipulations, and quantum gives you more. So now the question is, does nature exploit this edge of being able to do more? So the conditional entropy measures how much uncertainty, how much ignorance you have about a combined system and observer, given that you have all the observer's knowledge. And for anything that we encounter in the real world, it's a fair assumption that this conditional entropy is bounded below by 0. So this quantity is actually, for quantum systems, this conditional entropy can actually be smaller than 0. And whenever something like this happens, we call it entanglement. So whatever physical meaning entanglement has, you can take it as very strange probability distributions which allow you to achieve correlations which are classically not possible. So one application. So let's suppose you have a system which is in a mixture of 0 and 1, and you would like to reset. That could be, for example, your memory, and you would like to reset that to state 0. And what is usually called Landauer's erasure principle states that a classical observer has to pay 1 unit of work to extract or to erase that information. Is it any difference if we are dealing with a quantum observer? Yes. It could be that the quantum observer actually has the other half of a maximally entangled state. And then the system has the same correlations. And as was shown recently, in that case, you can actually extract 1 unit of work and erase the information to reset it to 0. And now we are talking about biology. Whatever small enzymes, molecules, and other systems are wiggling around in your biological systems, it could be that they are small enough to be a quantum observer. So this DNA is this really thin and long molecule.
6 feet of this long molecule fits into the microscopic nucleus of every cell.
This is DNA in its classic double helix form, and it's from X-ray crystallography, so it's an accurate model of DNA. If we unwind the double helix and unzip the two strands, you see these things that look like teeth. Those are the letters of genetic code, the 25,000 genes you've got written in your DNA. This is what they typically talk about, the genetic code. This is what they're talking about. But I want to talk about a different aspect of DNA science, and that is the physical nature of DNA. And it's these two strands that run in opposite directions for reasons I can't go into right now, but they physically run in opposite directions, which creates a number of complications for your living cells, as you're about to see, most particularly when DNA is being copied.
And when I first looked at those molecules, I thought, well, they are pretty small compared to our computers, what we encode in a bit in a computer. And because here we have 4 different bases, each molecule encodes 2 bits.
Shannon showed that a single binary digit, one of these ones or zeros, is a fundamental unit of information. Think of it as an atom of information, the smallest possible piece. Then, having defined this basic unit, he even gave us a name for it, one we're all familiar with today. He used a shortening of the phrase binary digit, bit.
Then these 2 bits are arranged in a linear array, and so the 2 strands have opposite information. Now the interesting question is, how do you actually access that information? It's not enough to store it, you actually have to be able to read it out. How do you do that with these small systems?
And so what I'm about to show you is an accurate representation of the actual DNA replication machine that's occurring right now inside your body, at least 2002 biology. So DNA is entering the production line from the left-hand side, and it hits this collection, this miniature biochemical machines that are pulling apart the DNA strand and making an exact copy. So DNA comes in and hits this blue donut-shaped structure, and it's ripped apart into its 2 strands. One strand can be copied directly, and it can be seen spooling off down to the bottom there. But things aren't so simple for the other strand because it must be copied backwards. So it's thrown out repeatedly in these loops and copied one section at a time, creating 2 new DNA molecules. Now, you have billions of this machine right now whirring the right way inside you, copying your DNA with exquisite fidelity. It's an accurate representation, and it's pretty much at the correct speed for what it's occurring inside you. But I've left out error correction and a bunch of other things. This was work from a number of years ago. Thank you.
All these nucleic acids, they are more or less planar molecules being surrounded by electron clouds. And you actually need the coherence between neighboring sites to get the attractive part of the force. But now this also has non-trivial implications. So first of all, neighboring sites are entangled due to this continuous interactions.
So again, we begin with DNA, and it's jiggling and wiggling there because of the surrounding supermolecules, which I've stripped away so you can see something. DNA is about 2 nanometers across, which is really quite tiny. But in each one of your cells, each strand of DNA is about 30 to 40 million nanometers long. So to keep the DNA organized, to regulate access to the genetic code, it's wrapped around these purple proteins. I've labeled them purple here. It's packaged up and bundled up. All of its field of view is a single strand of DNA. This huge package of DNA is called a chromosome.
The process starts when DNA is wrapped around special protein molecules called histones. The combined loop of DNA and protein is called a nucleosome. Next, the nucleosomes are packaged into a thread. The end result is a fiber known as chromatin. This fiber is then looped and coiled yet again.
So here was a screenshot from a computer program where you do something with DNA. You've seen it many times before. And to sum it all up, what I told you in the previous slides, everything that you can see on this picture is classical information. The black stuff and the double helix that you cannot see, that's a quantum information. So I haven't discovered any good way how to picture correlations. Probably there is no way, so that's why nobody ever draws quantum information. But the next time you see such a double helix, you know, okay, all the stuff I do not see, that's a quantum information. So basically what happens, this classical information, which is usually drawn here, is embedded, is sandwiched into quantum information. And most likely, this classical information is never accessed. You can only, because it's inside all the quantum information.
We're zooming out through a nuclear pore, which is sort of the gateway to this compartment that holds all the DNA, called the nucleus. All of this field of view is about a semester's worth of biology, and I've got 7 minutes, so we're not going to be able to do that today. No, I'm being told no. This is the way a living cell looks down a light microscope, and it's been filmed under time-lapse, which is why you can see it moving. The nuclear envelope breaks down. These sausage-shaped things are the chromosomes, and we'll focus on them. They go through this very striking motion that is focused on these little red spots. When the cell feels it's ready to go, it rips apart the chromosome. One set of DNA goes to one side, the other side gets the other set of DNA, identical copies of DNA, and then the cell splits down the middle. And again, you have billions of cells undergoing this process right now inside of you. Now we're going to rewind and just focus on the chromosomes and look at its structure and describe it. So again, here we are at that equator moment. The chromosomes line up, and if we isolate just one chromosome, we're going to pull it out and have a look at its structure. So this is one of the biggest molecular structures that you have, at least as far as we've discovered so far, inside of us. So this is a single chromosome, and you have 2 strands of DNA in each chromosome. One is bundled up into one sausage, the other strand is bundled up into the other sausage. These things that look like whiskers that are sticking out from either side are the dynamic scaffolding of the cell. They're called microtubules.
The title of my talk is Clarifying the Tubulin Bit Qubit, Defending the Penrose-Hameroff orch-or model of quantum computation and microtubules. First, I'm going to give you a little bit of an overview about microtubules. We've heard quite a bit about some of the technical aspects, but I want to kind of back up and give you the big picture a little bit. Consider a single-cell paramecium, which can swim around, avoid obstacles, avoid predators, find food, learn. If you suck it into a capillary tube, it escapes. If you do it again, it escapes more quickly. It can find a mate, and it can have sex. This is actually a picture of 2 paramecium having sex. It's probably the only X-rated picture we'll see today. And it doesn't have any synapses. It doesn't have any nervous system per se. How does it do it? It uses structures called microtubules. And I often kid my AI friends they should worry about simulating a paramecium before worrying about a brain. So microtubules seem to be the nervous system of the cell. And here's a beautiful immunofluorescence micrograph of a double nucleated cell. The yellow is the microtubules, the red is the actin, and the microtubules form the kind of cytoskeletal architecture and bone-like support, but we also think they're the cell's onboard computer. In cell division, microtubules are in the red, the chromosomes are in the blue, and the yellow are centrioles, which anchor the mitotic spindles of microtubules and organize mitosis. And if this goes wrong, you can get cancer because you get an abnormal genotype. And the mechanism of this is still poorly understood. The centrioles are made up of 9 triplets of microtubules, so each of these would be a microtubule or part of a microtubule, and you get 9 of these and forms a megacylinder. And this is the same structure also found in cilia, the appendages that come out the end of the paramecium, and we also have them in our body. And they're found in the retina of the eye, and they're found all over the place. And in cell division, centrioles have 2 of these barrels in this odd perpendicular arrangement. They each replicate and separate, and the mitotic spindles anchor to them and pull apart the chromosomes. It's interesting, they're also optically sensitive. Albrecht Buehler, who was mentioned earlier, shown that these centrioles detect photons and orient the cell in a particular direction towards the light. And it's interesting that their shape and their geometry, their dimensions are could accommodate photons, and they could be some kind of quantum optical devices, or at least optical resonators of some sort. I just want to mention that. I'm not going to talk about it per se. So inside neurons, microtubules in dendrites are found in this interrupted type of network, interconnected by microtubule-associated proteins. So they form a sort of network, and we think a computational network inside cells, inside neurons of a neural network. So it's kind of a fractal subdimension inside neurons. Now, if your microtubules go bad, you get Alzheimer's disease. There's actually two lesions in Alzheimer's, amyloid plaques, which for some reason get most of the money in research, but the real damage is done by neurofibrillary tangles inside the neurons, which are due to tau proteins, which normally, here it says stabilize microtubules, but they do other things as well. When they get all screwed up, the microtubule disintegrates, the tau gets hyperphosphorylated, and the microtubule disintegrates literally. You get the kind of crinkly neuron, and you lose cognitive memory and eventually consciousness. So Alzheimer's is a disease of microtubules. Here's a close-up of disintegrating microtubules.
But name's not so important. But what we're going to focus on is this red region. I've labeled it red here. And it's the interface between the dynamic scaffolding and the chromosomes. It is obviously central to the movement of the chromosomes, but we have no idea, really, as to how it's achieving that movement. We've been studying this thing called the kinetic core for over 100 years with intense study, and we're still just beginning to discover what it's all about. It is made up of about 200 different types of proteins, thousands of proteins in total.
Proteins do all the work of the cell. They transduce light in the eye, make up and actuate our muscles, serve as messengers, and structure our cells. And just like the variety of functions they serve, they come in an enormous diversity of forms. But how these shapes arise out of linear strands of amino acids is a long-standing puzzle. I spoke with Kenneth Dill about our progress and the important consequences of the protein folding problem.
In the 1960s and 70s, many people thought this was going to be an unsolved problem for a very long time, and that maybe we were even missing many of the basic forces of nature that we needed in order to be able to understand it. In the meantime, what's happened is on many different fronts, people have built physics-based models and other kinds of models to try to understand the interactions. And it's now the case that within computer simulations, we have models that are pretty good.
It is a signal broadcasting system. It broadcasts through chemical signals, telling the rest of the cell when it's ready, when it feels that everything is aligned and ready to go for the separation of the chromosomes.
So let us suppose that each of these balls represents a site in your DNA. And what I do is I wiggle the one end of it. And then you can calculate what happens to it. Actually, after some time, you will get entanglement between the first side where you shake your end and the nth side, could be the 10th or 20th or 30th side along the chain. And suddenly, these two far apart sides show entanglement. And entanglement means that they have correlations. So the question is, can you use those correlations for communicating along this one-dimensional chain?
And you'll see that there's one little last bit that's still remaining red. And it's walked away down the microtubules. That is the signal broadcasting system sending out the stop signal, and it's walked away. I mean, it's that mechanical. It's molecular clockwork. This is how you work at the molecular scale. So with a little bit of molecular eye candy, we've got kinesins, which are the orange ones. They're little molecular courier molecules walking one way. And here are the dynein. They're carrying that broadcasting system, and they've got their long legs so they can step around obstacles and so on.
When I read up on the literature on how little motors go along the DNA and achieve things, I always wonder, how does it work? How do these motors actually know what they are supposed to do?
Now, the tau protein, which is thought previously just kind of hold the microtubule together, turns out that it does something more. It acts as a kind of a traffic signal for motor proteins, which transport synaptic materials. So if a synapse downstream in a dendrite, say, needs a particular enzyme or precursor or receptor, it's often synthesized more proximally and transported by these motor proteins, which carry it along as cargo. And they often have to jump tracks and switch microtubules in the branching dendrite. And it's been a mystery how they seem to know where to go. It turns out that the tau at specific locations on the microtubule kind of traffic signals and tell particular proteins like this guy right here where to jump off. And so their placement is critical. Now, how do they know where to be? Are they that smart, or is there some kind of encoding in the microtubule itself?
So again, this is all derived accurately from the science. The problem is we can't show it to you any other way. exploring at the frontier of science, at the frontier of human understanding is mind-blowing. Discovering this stuff is certainly a pleasurable incentive to work in science. But most medical researchers, this is just discovering this stuff is simply steps along the path to the big goals, which are to eradicate disease, to eliminate the suffering and the misery that disease causes, and to lift people out of poverty. Thank you.
And the next thing is something where my own ignorance comes up. I do not know too much about protein folding, but I have a background in information science, so I would like to ask a question to people who know more about biology.
You, yes you, are better at recognizing spatial relationships than computer programs whose job it is to recognize spatial relationships. Congratulations! And you know who's even better than normal people at this stuff? Video gamers. Okay, get out your phone real quick. I'm going to dictate a text message to your mom. Dear Mom, video games are too contributing to the well-being of society. You were wrong. Your adoring child, and then you can put your name. Because gamers are actually using their mad Super Mario Bros. Wii skills to recognize patterns in nature and to crack the codes of microscopic matter. Case in point, there's this organization called Foldit that puts gamers to work figuring out how proteins fold up into their most stable and most useful states. So you've probably heard of proteins, but usually in a dietary context. It's just like one of the things that we eat in the form of soy or cow, depending on your preference. But proteins are basically the stuff that makes us work. Proteins do tons of different jobs. They will, for example, help me digest this Hot Pocket. Also, the proteins, they'll digest the proteins in this Hot Pocket, which is just meta. You may be noticing that we build in lunch to my scripts. So some proteins help break down this Hot Pocket that I'm eating into useful energy. And some of them make up my fingernails, and some of them help the butts of fireflies glow. But proteins are actually really extremely complicated structures. They're made up of long chains of amino acids, and for the most part, it's those amino acids that define what their shape is going to be. But proteins don't exist as long chains. As soon as they're formed, they fold up into themselves into mysterious shapes. They fold up for stability, but the way that they fold defines how they operate and what they do. And it's really tough to figure out how a protein is going to fold up. And so we spend a lot of money and time trying to figure this out. One, by having computers do it. Two, by actually trying to look at the protein while it's functioning to see if we can actually see its shape, which turns out is very hard to do. Because understanding how a protein folds up is a key to understanding how that protein works. And if it's a disease protein, it's a key to understanding how to stop that protein. So scientists have been developing computer programs for years that try and figure out how proteins fold up in their most stable states. But it turns out computers are just bad at that kind of stuff. And people are really good at it, especially people who have developed their spatial reasoning skills through hours and hours of video game playing. And so the organization Foldit figured out that the best solution to this problem was to turn protein folding into a video game.
When you've got it right, you see your protein moving and changing shape, and your score rushes up, your own player name rushes up through the ranks, and yeah, your adrenaline starts.
It's like being a scientist when you get a paper published. That 10% of euphoria is supposed to take you through the 90% of banging your head against a brick wall. But
people put a huge amount of energy into playing games on computers, so I think projects like this can channel that energy into solving real-world problems, and that's a way in which everyone can contribute that really hasn't been there before.
I'm Suzanne Helitsky, and I'm an administrator in Manchester, and my folding gaming name is also Suzanne.
hello, I'm Charlie. I'm a bench technician, and in my spare time I play Foldit. I used to be number 2 in the world. My gaming tag is Charlie Fort's Conscience, and I'm a member of the Contenders. It's essentially a 3D jigsaw puzzle. You're given a protein which comprises of a backbone and individual side chains. And by moving these around, changing the interactions, your score either goes up or down.
Scientists are interested in working out the three-dimensional structures of proteins because they help understand how the proteins carry out their jobs, what they do inside cells. The principle behind the prediction of protein structures on a computer is that we've known for a long time that all the information needed to determine the structure of a protein is in the amino acid sequence of the protein.
So inside the computer, what you do is you build a model of the physics of how the amino acids interact with each other and just follow that protein molecule wiggling around as it would do in water by random thermal motions. And then the question is it able to find its native structure, and do we understand the physics well enough to be able to predict that structure? And I would say progress is quite remarkable. There are now a number of groups who are able to find the native structures of proteins, the folded structures of proteins in their computer simulations. And so huge progress relative to where we were 50 years ago.
Why is it so useful to be able to predict this with a computer rather than just observing how they fold?
The reason that we want to do this in the first place is because ever since the beginning of the folding problem, it's been clear that this could have a big impact on drug discovery.
Turns out that the structure that proteins fold to is almost always the lowest energy structure for that amino acid sequence. So the structure prediction problem then is finding the lowest energy structure for that amino acid sequence. And the reason it's hard is that there's so many different possible configurations.
We now know the structures of 80,000 proteins or so at atomic levels of detail. On the other hand, we have 1,000-fold more sequences than that. We have about 80 million sequences. And so what would be very powerful for drug discovery is if we, in the computer, could start with an amino acid sequence and figure out how to predict the three-dimensional structure, because that's really the working starting point for every drug discovery effort.
Folded is specifically looking at the proteins in disease-causing organisms like viruses and bacteria, because in order to stop a protein, you have to know how it works, and you have to have its structure before you can know how it works. In the video game, gamers play competitively to see who can fold the protein into the most stable state, and they're kicking ass at it.
A really good folded player, I think, needs a number of skills. Problem solving is obviously one of them. I think a slightly addictive personality, a little bit of stubbornness thrown in, and a little bit of luck on top. You don't necessarily need to have a scientific background to play, you just need to know what works and what doesn't. And you can learn that within the game itself.
I'm an administrative worker in the rehab team. I'm just answering telephones, working on bespoke computer programs, interacting with staff. It's very repetitive. When I go home, I become a different person. I just like to measure myself against something, and it's given me something that my everyday life hasn't given me. It's to just use abilities I didn't know I had.
For me, it's a guilty pleasure, and yet here I am involved in something that has real relevance in the scientific world. It makes you feel very proud of what you do, which is essentially a little hobby.
You can imagine where you come home in the evening and you can either stay up all night playing Halo, or you can be designing an HIV vaccine with people all around the world. I mean, which would you be happier saying you did when you went into work in the morning?
So for instance, there's this AIDS-related enzyme that scientists have been trying to figure out the structure of for about a decade. When all the normal computational methods for unlocking the structure of the enzyme failed, they gave it to folded gamers to figure out. And it took them about 3 weeks to figure it out. Scientists have since been able to completely determine the structure of the protein, and they now think that they understand enough about it to actually start developing drugs to turn it off. In the meantime, the paper that was published describing these findings listed the scientists and the gamers as co-authors, and that's pretty freaking cool. Humanity, for all of my hours and hours of video game playing, I say to you, you're welcome.
So when I would like to fold a protein, I start with my DNA, which is a one-dimensional sequence of information. So in order to fully describe the classical information in DNA, I only need to know this one-dimensional sequence. In the next step, I translate pairs of 3 of my RNA into an amino acid. Now there's some sort of code on code. You might argue that you lost some information. I'll ignore that effect for the moment. And then in the fourth step, this one-dimensional chain of amino acid actually folds into a three-dimensional structure.
But then, if the environmental is whacking at this thing too hard, then this evil thing, quantum thing called decoherence, where all your quantumness goes away, would kick in, and the efficiency would drop to 0. And that's exactly what happened. It starts off at around 3/4 at 0 temperature. It goes up and up and up and up and up. It reaches 100%. So 1. There's a rather broad plateau, which it stays in 1, and then it drops down to 0. And even more interesting than this was the time it took. I'll plot this on a different axis over here. At 0 degrees, the time was around 100 picoseconds, 100 trillionths of a second. These processes take very short time, which is why they can remain quantum mechanical even in these hot, wet conditions. The time started way up there, and then it dipped way down, and then it got down to 5 picoseconds. Actually, sorry, it was about roughly the same point, and then it goes up to infinity there. So the thing was stuck at low temperatures. Then this subtle interplay or interaction between environmental effects and coherent effects kicked in, and then it got extremely efficient and just zipped through this complex. And then when it got too hot, bad things started to happen again. And by the way, what do you think that this critical temperature is right here, where this is at a maximum? It's over a rather broad range of many tens of degrees, Kelvin or Celsius, right? But what do you think that temperature is? Somebody give me a guess. Come on. Yeah, it's like 290 Kelvin, which is room temperature.
Does this suggest another way of building a quantum computer?
Yeah, I mean, there are lots of these living systems. Have lots of lessons to teach us in quantum computation. So, in quantum computation, the interaction with the environment is a killer, and we have to go through extreme measures to get rid of it. But in these bacteria, the interaction with the environment, as you can see from this graph, is very well tuned to give you both high efficiencies at your operating temperatures and robustness, so a wide range of operating temperatures around there.
So let's look at it again. You start with DNA, messenger RNA, and this chain of amino acids. And because they are all linear arrangements, I would argue that roughly, up to small errors, they carry the same amount of classical information. And then you fold a protein, and it's getting a three-dimensional structure. And the shape is vital to its functioning. But now you need to store more information. In addition to the sequence, you have the position information. And in my opinion, that's actually an increase of information. But we also know from the second law that in closed systems, information cannot increase spontaneously. Now I know that creating a protein is far away from being a closed system. But my question to the biologists is actually, where does this additional information come from? If you think about it in detail, that's actually not that trivial. Does it come from the time sequence in which you assemble the protein? Does it come from some sort of laws of quantum mechanics? Do you have some sort of quantum information actually also taking place? If anybody can tell me, I'd be very happy.
So moving on to a third problem that you raise in your review is the idea that proteins fold very fast and that this is surprising and it's really hard to figure out how they do it.
Right. So the protein folding problem has been regarded as a needle in a haystack problem. The needle being the structure that we're trying to figure out, and the haystack being it tries out all these different string shapes to try to figure out what's the right one, and it has to do this all pretty randomly. There were estimates back in the early days that it should take proteins zillions of years to fold up, and yet, in reality, real proteins in real biological systems fold up often in microseconds or milliseconds. They're very fast.
In these bacteria, the interaction with the environment, as you can see from this graph, is very well tuned to give you both high efficiencies at your operating temperatures and robustness, so a wide range of operating temperatures around there. So these bacteria have done an excellent job at dealing with environmental interactions. Much better job than we do on quantum computers by and large. Of course, in some sense, it's actually for people who here do quantum computation, it's easier to protect energy from decaying than it is to protect quantum information from going away.
It's about energies, and it's about the fact that energies help point the protein in the right direction to fold up to its native structure.
So the native form is the low energy, one of the very low energy states for the molecule.
Exactly.
So I actually claim these purple bacteria are using a very sophisticated quantum coding scheme. The outer ring has, I won't be able to draw it right there, there are 18 of these. These are these chromophores where the energy can sit. The inner ring has 9. I'll tell you what these little X's look like just in a second. From the side, it looks kind of like a teeny nuclear power plant cooling tower, about 7 angstroms, 0.7 nanometers wide by, 7 nanometers wide by 6 nanometers tall. These things are all arranged in a big array. Now, if you look at one of these little X's right here, this is a chromophore. It's a funny kind of like square-shaped molecule, and it's got a kind of tails going off here, and it's got some other junk here, all of which can be varied by natural selection. And the exciton gets created basically, I think, along this axis. I can't remember exactly. And then it jiggles around, and it relaxes, so at the end, it's along this axis. So it starts along this axis, the diagonal one, it ends up along that axis. Now, this exciton is in an entangled state where the spins of the electron and hole are in opposite directions. And this entangled state, it's called a singlet state for those who are interested in that kind of thing. It has the feature that is effectively what's called in quantum mechanics a decoherence-free subspace, which is something that basically doesn't interact directly with the environment. It's what gives the exciton its really long lifetime. Now, if you don't like the words decoherence-free subspace, which I wouldn't blame you for not liking, you can just say, the bacteria don't give a damn what they call it, right? They found something that worked, and that something has worked is what eggheady people like me call a decoherence-free subspace.
You see, in the history of philosophy and poetry and art, we always find the interchange of two personality types, which I call prickles and goo. The prickly people are advocates of intellectual porcupinism. They want a rigor. They want precise statistics. And they have a certain clipped attitude in their voices. And you know this very well in academic circles, where there are people who are always edgy like that. And they accuse other people of being disgustingly vague and miasmic and mystical. But the vague, miasmic, and mystical people accuse the prickly people of being mere skeletons with no flesh on their bones. And they say to you, you just rattle. You're not really a human being. You know the words, but you don't know the music. And so, therefore, if you belong to the prickly type, you hope that the ultimate constituent of matter is particles. If you belong to the gooey type, you hope it's waves. If you are prickly, you're a classicist. And if you're gooey, you're a romanticist. And going back into medieval philosophy, if you're prickly, you're a nominalist. If you're gooey, you're a realist. But we know very well that this natural universe is neither prickles nor goo exclusively. It's gooey prickles and prickly goo. And you see, it all depends on your level of magnification. If you've got your magnification on something so that the focus is clear, you've got a prickly point of view. You've got structure, shape, clearly outlined, sharply defined. A little out of focus is going to go bleh, and you've got goo. But we're always playing with the two.
That complex systems generate unexpected connections and forms of order. The internet is the most complex, distributed, high-speed system ever put in place on this planet.
Descartes himself thought that what made human intellects human was their ability to think logically, clear and distinct ideas, essentially mathematical logic. But however, as we all know, by making that the essential characteristic of human beings, he made the rational intellect, what many people would call the left brain rational intellect, the sole definition of human beings.
The division of the brain is something neuroscientists don't like to talk about anymore. It enjoyed a sort of popularity in the 60s and 70s after the first split brain operations, and it led to a sort of popularization which has since been proved to be entirely false. It's not true that one part of the brain does reason and the other does emotion. Both are profoundly involved in both. It's not true that language resides only in the left hemisphere. It doesn't. Important aspects are in the right. It's not true that visual imagery is only in the right hemisphere. Lots of it is in the left. And so in a sort of fit of despair, people have given up talking about it. But the problem won't really go away, because this organ, which is all about making connection, is profoundly divided. It's there inside all of us, and it's got more divided over the course of human evolution, so that the ratio of the corpus callosum to the volume of the hemispheres has got smaller over evolution. And the plot thickens when you realize that one of the main, if not the main, function of the corpus callosum is in fact to inhibit the other hemisphere. So something very important is going on here about keeping things apart from one another. And not only that, the brain is profoundly asymmetric. It's broader at the back on the left and broader on the right at the front, and slightly juts forward and backward. And it's as though somebody got hold of the brain from underneath and given it a sort of sharp twist clockwise. What is all that about? If one just needed more brain space, one would do it symmetrically. The skull is symmetrical. The box in which all this is contained is symmetrical. Why go to trouble to expand some bits of one hemisphere and some bits of another, unless they were doing rather different things? What are they doing? Well, it's not just we who have these divided brains. Birds and animals have them as well. I think the simplest way to think of it is if you imagine a bird trying to feed on a seed against the background of grit or pebbles. It's got to focus very narrowly and clearly on that little seed and be able to pick it out against that background. But it's also, if it's going to stay alive, it's got to actually keep a quite different kind of attention open. It's got to be on the lookout for predators or for friends, for conspecifics, but for whatever else is going on. It seems that birds and animals quite reliably use their left hemisphere for this narrow focused attention to something it already knows is of importance to it. And they keep their right hemisphere vigilant broadly for whatever might be without any commitment as to what that might be. And they also use their right hemispheres for making connections with the world. So they approach their mates and bond with their mates more using the right hemisphere. But then you come to the humans. And it's true that actually in humans too, this kind of attention is one of the big differences. The right hemisphere gives sustained, broad, open vigilance, alertness, where the left hemisphere gives narrow, sharply focused attention to detail. And people who lose their right hemispheres have a pathological narrowing of the window of attention. But humans are different. The big thing about humans is their frontal lobes. And the purpose of that part of the brain? To inhibit the rest of the brain, to stop the immediate happening. So standing back in time and space from the immediacy of experience. And that enables us to do two things. It enables us to do what neuroscientists are always telling us we're very good at, which is outwitting the other party, being Machiavellian. And that's interesting to me, because that's absolutely right. We can read other people's minds and intentions, and if we so want to, we can deceive them. But the bit that's always curiously missed out here is that it also enables us to empathize for the first time, because there's a sort of necessary distance from the world. If you're right up against it, you just bite. But if you can stand back and see that other individual is an individual like me, who might have interests and values and feelings like mine, then you can make a bond. There's a sort of necessary distance, as there is in reading. Too close, you can't see anything. Too far, you can't read it. So the distance from the world that is provided is profoundly creative of all that is human, both the Machiavellian and the Erasmian. Now, to do the Machiavellian stuff, to manipulate the world, which is very important, we need to be able to interact with the world and use it for our benefit. Food is the starting point. But we also, with our left hemispheres, grasp, using our right hands, things and make tools. We also use that part of language to grasp things, as we say. It pins them down. So when we already know something's important and we want to be precise about it, we use our left hemispheres in that way. And to do that, we need a simplified version of reality. It's no good if you're fighting a campaign, having all the information on all the plant species that grow in the terrain of battle. What you need is to know the specifics of where certain things are that matter to you, and so you have a map and you have little flags. It's not reality, but it works better. The newness of the right hemisphere makes it a devil's advocate. It's always on the lookout for things that might be different from our expectations. It sees things in context. It understands implicit meaning, metaphor, body language, emotional expression in the face. It deals with an embodied world, in which we stand embodied in relation to a world that is concrete. It understands individuals, not just categories. It actually has a disposition for the living rather than the mechanical. And this is so marked that even in a left-hander who is actually using their right hemisphere in daily life to manipulate tools with their left hand, it is their left hemisphere, not their right hemisphere, in which tools and machines are coded. So this is very interesting. And it changes the view of the body. The body becomes an assemblage of parts in the left hemisphere. If I had to sum it all up, I would get away from all those things that we used to say, reason and imagination. Let me make it very clear. For imagination, you need both hemispheres. Let me make it very clear. For reason, you need both hemispheres. So if I had to sum it up, I'd say the world of the left hemisphere, dependent on denotative language and abstraction, yields clarity and power to manipulate things that are known, fixed, static, isolated, decontextualized, explicit, general in nature, but ultimately lifeless. The right hemisphere, by contrast, yields a world of individual, changing, evolving, interconnected, implicit, incarnate, living beings within the context of the lived world, but in the nature of things never fully graspable, never perfectly known. And to this world it exists in a certain relationship. The knowledge that's mediated by the left hemisphere is, however, within a closed system. It has the advantage of perfection, but the perfection is bought ultimately at the price of emptiness. There's a problem here about the nature of the two worlds. They offer us two versions of the world, and obviously we combine them in different ways all the time. We need to rely on certain things to manipulate the world, but for a broad understanding of it, we need to use knowledge that comes from the right hemisphere. And it's my suggestion to you that in the history of Western culture, things started in the 6th century BC, in the Augustan era, and in the 15th, 16th century in Europe, with a wonderful balancing of these hemispheres. But in each case, it drifted further to the left hemisphere's point of view. Nowadays, we live in a world which is paradoxical. We pursue happiness, and it leads to resentment, and it leads to unhappiness, and it leads, in fact, to an explosion of mental illness. We've pursued freedom, but we now live in a world which is more monitored by CCTV cameras, and in which our daily lives are more subjected to what de Tocqueville called a network of small, complicated rules that cover the surface of life and strangle freedom. More information, we have it in spades, but we get less and less able to use it, to understand it, to be wise. There's a paradoxical relationship, as I know as a psychiatrist, between adversity and fulfillment, between restraint and freedom, between the knowledge of the parts and wisdom about the whole. It's that machine model again that is supposed to answer everything, but it doesn't. Think about this. Even rationality is grounded in a leap of intuition. There is no way you can rationally prove that rationality is a good way to look at the world. We intuit that it is very helpful. And this is not new. At the other end of the process, rationality we know from Gödel's theorem, we know from what Pascal was saying hundreds of years before Gödel, that the end point of rationality is to demonstrate the limits to rationality. In our modern world, we've developed something that looks awfully like the left hemisphere's world. We prioritize the virtual over the real. The technical becomes important. Bureaucracy flourishes. The picture, however, is fragmented. There's a loss of uniqueness. The how has become subsumed in what. And the need for control leads to a paranoia in society that we need to govern and control everything. Why this shift? I think there are three reasons. One is the left hemisphere's talk is very convincing because it shaved everything that it doesn't find fits with its model off and cut it out. So this particular model is entirely self-consistent, largely because it's made itself so. I also call the left hemisphere the Berlusconi of the brain, because it controls the media. It's the one with which it's very vocal on its own behalf. The right hemisphere doesn't have a voice, and it can't construct these same arguments. And I also think, rather more importantly, there's a sort of hall of mirrors effect. The more we get trapped into this, the more we undercut and ironize things that might have led us out of it. And we just get reflected back into more of what we know about what we know about what we know. And I just want to make it clear, I'm not against whatever it is the left hemisphere has to offer. Nobody could be more passionate in an age in which we neglect reason and we neglect careful use of language. Nobody could be more passionate than myself about language and about reason. It's just that I'm even more passionate about the right hemisphere and the need to return what that knows to a broader context. It turned out that Einstein's thinking somehow presaged this thing about the structure of the brain. He said, the intuitive mind is a sacred gift, and the rational mind is a faithful servant. We have created a society that honors the servant, but has forgotten the gift.
So this whole premise on which your whole thing's based is taking that particular model of cognitive, logical, mathematical processing as being the essence of intelligence. Now, there are many people who would disagree with that, including me. It leaves out art, it leaves out ethics, religion, and essentially it leaves out the body and everything to do with body and participation and the senses.
Something very large like this is happening to us. Perhaps we're going to form a symbiotic relationship with solid-state machinery of some sort. Lots of people are cheering that on.
Now, run that one by me again. It means like humans and computers will get married and have kids or something? Or?
No, it means you won't be able to tell where your body stops and the internet begins.
The emphasis that life depends on DNA information, the DNA code is just a program.
Charles Darwin started evolution off, he and Alfred Wallace, with the bifurcating tree. A bifurcating tree starts from one organism to make 2, and 2 to 4, and 4 to 8, and so forth. Meanwhile, these organisms start to compete with each other. Okay? So he liked to call it the survival of the fittest. And that's an interesting metaphor that's existed. But there's another type of evolution that we need to know about and that's starting to become more important.
The last point I want to make is one about how evolution occurs. It isn't that a mutation happens and it confers greater adaptability upon an individual, and therefore that individual and his offspring numerically gain over competitor individuals of the same species. This is not how it works.
More than 500 million years ago, a new material appeared on Earth. Clumps of cells that adhered to each other, sometimes acting like a liquid and other times like a solid. The physical properties of this new substance set the stage for the physical forms of multicellular organisms. I spoke with Stuart Newman about how the properties and forces inherent in this material still hold sway in patterns of animal development.
In all of the different types of animals, there is development from a cluster of cells of layers of tissue, and these layers are generally non-intermixing. We also generate interior spaces, cavities, and when the embryo organizes itself, it elongates, often not always. It generates appendages from the surface, and there are segments that form in many different types of animals that are not directly related to each other. And what I mean by that is that sometimes you see segmented forms in disparate phyla that don't have a common ancestor that was segmented. So I call these different forms and structures morphological motifs, and not every one of them is present in every type of animal, but there's a limited number of them,
and every type of animal is organized with at least several of these motifs.
This is an animal, and this is also an animal. An animal, animal, animal carcass, animal, animal, animal carcass, again, animal. The thing that all of these other things have in common is that they're made out of the same basic building block, the animal cell. Animals are made up of your run-of-the-mill eukaryotic cells, and these are called eukaryotic because they have a true kernel in the Greek, a good nucleus, and that contains the DNA and calls the shots for the rest of the cell, also containing a bunch of organelles. There's a bunch of different kinds of organelles, and they all have very specific functions, and all of this is surrounded by the cell membrane. Of course, plants are eukaryotic cells too, but they're set up a little bit differently. Of course, they have organelles that allow them to make their own food, which is super nice. We don't have those.
With the first eukaryogenic event that occurred dating back to as far back as 2.5 billion years ago, or as recently as 0.9 billion years ago, a single cell free-living bacterium that consumed oxygen was fused with a archaebacterium.
And that is convergence, where two organisms come together to make one.
But maybe the coolest thing about mitochondria is that long ago, animal cells didn't have them, but they existed as their own sort of bacterial cell. And one day, one of these things ended up inside of an animal cell, probably because the animal cell was trying to eat it. But instead of eating it, it realized that this thing was really super smart and good at turning food into energy, and it just kept it. It stayed around. And to this day, they sort of act like their own separate organisms, like they do their own thing within the cell, they replicate themselves, they even contain a small amount of DNA. Now, what may be even more awesome, if that's possible, is that mitochondria are in the egg cell when an egg gets fertilized. And those mitochondria have DNA. But because mitochondria replicate themselves in a separate fashion, it doesn't get mixed with the DNA of the father. It's just the mother's mitochondrial DNA. That means that your and my mitochondrial DNA is exactly the same as the mitochondrial DNA of our mothers. And because this special DNA is isolated in this way, scientists can actually track back and back and back and back to a single mitochondrial Eve who lived about 200,000 years ago in Africa. All of that complication and mystery and beauty in one of the cells of your body. It's complicated, yes, but worth understanding.
And of course, in a sense, we're an example of a convergence. I mean, we had the sperm from our father and the egg from our mother, and we're the descendants, so we really have to have genomes coming together to make a new type of individual.
And so what are some ideas about how these shared motifs might have arisen from our single-celled ancestors?
There was several billion years of evolution that led to the single-celled ancestors of the animals. So these cells were quite sophisticated and adapted to their own single-cell life. Then something happened that allowed cells to cluster.
For single cells can do just fine on glycolysis. They don't need mitochondria for energy production. Okay? You just don't need it. It's, really you need mitochondria for energy production when you start putting multiple cells together to make, animals and plants. Okay?
But this is done time and time again in evolution, but it's not studied. The reason is that it's very complex.
And what we know is that the genes that mediate clustering of cells in all of the modern animals, they're called cadherins, or at least cadherins are the major group of such proteins. Mm-hmm. They existed in these single-celled organisms, and they were used for single-cell functions, for perhaps capturing prey or adhering to the substratum, but they weren't used to coordinate multicellular development because there were no multicellular organisms.
There are two types of organisms. There are prokaryotes and eukaryotes. Prokaryotes are the organisms that are present earliest in the fossil record. They're very small, single-cell organisms. They don't have a nucleus. They can photosynthesize. They were on the Earth, as people like Bill Schaap from UCLA have shown, for very long periods of life, and they are extremely important. They've changed the way the Earth is. The eukaryotes are like us, like Chancellor Bloch referred to. We're different, you know. We have big cells, we have a nucleus, and in addition to that, we have organelles, like the mitochondrion and the chloroplast. Now, the chloroplast is the organism shown in these is the organelle shown in these slides. It's in red. These are plant cells. And these chloroplasts are busy taking the light in, and they make food for the cell from the sunlight. It's absolutely remarkable, because without plants, we would never have had animals, because animals have to eat this food that's made from the sunlight, and none of us would be here. So thank a plant today. Anyway, eukaryotes like us also have organelles, because we learned a trick. Well, we didn't learn it. We stole it from the prokaryotes, the trick of how to breathe oxygen and how to thereby enable us to get more than, maybe 10 times more energy out of the foods that we eat. So this happens to be the two tails of a bat sperm. So this is one single cell. Now, the bat sperm has one main thing to do, and it is to move as fast as it can to try to find the egg and against all the competition and fertilize the egg. So these little things in it, and remember, this is all just one cell, are mitochondria. So they're making the energy, and if you wanted to go the fastest, you've got to make the most fuel. And that's why they have evolved to just be totally filled with mitochondria to succeed.
So with the Cambrian explosion, that's when the real hidden value of mitochondria really became apparent, and it was so powerful. It is now its remnants are all everything that we see today in this in our living world.
And then you had basically a form of matter that previously didn't exist in the biological world, because you have these subunits that are independently mobile. They're not fixed in their position, but they are also cohesive. So in a sense, this new type of material is like a liquid, because a liquid is defined by subunits, molecules in the case of non-living liquids, that are mobile but nonetheless cohesive.
As these ants navigate a jagged surface, some of them move to fill in the gaps, while others use these ants as a bridge to help their exploration. The ants move over each other like the flow of a viscous liquid. Single ants crawl along the surface. But in a large group, those close to the solid surface remain stationary and mimic the way fluids behave. The group of ants in this funnel are sufficiently strong to cling on inside, but when they become restless, they flow out like a viscous fluid. This group of ants starts out shaped like a ball, but over time it loses its shape and the ants disperse. And here they use adhesion to build a structure. The research is helping to reveal how masses of insects move and survive.
So when you have this new type of living matter, then it can do things that liquids do. So for example, if you have populations of cells that have different amounts or different types of these surface proteins, they can separate out like oil and water, and then you can have multiple layers. That's a morphological step that can just take place because of some mutational change in the expression of these molecules.
But when the selective parameters change suddenly, these individuals who were previously masked in the general population, the selective advantage that they have now comes immediately to the fore, and they act very quickly and critically to send the evolution of a given species off in a different direction.
Every cell, bacteria and in unicellular eukaryotic cells, they have oscillators within them. That is, they have biochemical networks that change periodically with time. It seems to be just a spontaneous property of complex networks that you often get oscillations. But we know from the study of coupling of oscillators in non-living systems that oscillators don't have to be specifically interacting with each other. They can be just non-specifically interacting, and they come into synchrony. But when it happens in a cluster of cells, then the cells achieve a uniform state across fairly large distances, or distances of many cells. So if you have oscillations and coordination like this, the oscillations could also locally come out of phase with each other, and you can get segmentation to occur. Again, these are manifestations of material properties of clusters of cells that give rise to forms based on physical processes that are applied to the non-living and living world. But these forms then can exist in the biosphere and find appropriate niches. Maybe segmentation is useful for something.
I want to start my story in Germany in 1877, the mathematician named George Cantor. And Cantor decided he was going to take a line and erase the middle third of the line, and then take those two resulting lines and bring them back into the same process, a recursive process. So he starts out with one line, and then two, and then four, and then 16, and so on. And if he does this an infinite number of times, which you can do in mathematics, he ends up with an infinite number of lines, each of which has an infinite number of points in it. So he realized he had a set whose number of elements was larger than infinity. And this blew his mind, literally. He checked in the sanitarium. And when he came out of the sanitarium, he was convinced that he had been put on Earth to found transfinite set theory because the largest set of infinity would be God himself. He was a very religious man. He's a mathematician on a mission. And other mathematicians did the same sort of thing. Swedish mathematician von Koch decided that instead of subtracting lines, he would add them. And so he came up with this beautiful curve. And there's no particular reason why we have to start with this seed shape. We can use any seed shape we like. And I'll rearrange this, and I'll stick this somewhere down there. Okay. And now upon iteration, that seed shape sort of unfolds into a very different looking structure. So these all have the property of self-similarity. The part looks like the whole. It's the same pattern at many different scales. Now, mathematicians thought this was very strange because as you shrink a ruler down, you measure a longer and longer length. And since they went through the iterations an infinite number of times, as the ruler shrinks down to infinity, the length goes to infinity. This made no sense at all. So they consigned these curves to the back of the math books. They said, these are pathological curves, and we don't have to discuss them. And that worked for 100 years. And then in 1977, Benoit Mandelbrot, a French mathematician, realized that if you do computer graphics and use these shapes he called fractals, you get the shapes of nature. You get the human lungs, you get acacia trees, you get ferns, you get these beautiful natural forms. If you take your thumb and your index finger and look right where they meet, go ahead and do that now, and relax your hand, you'll see a crinkle, and then a wrinkle within the crinkle, and a crinkle within the wrinkle within, right? Your body is covered with fractals. The mathematicians who were saying these are pathological, useless shapes, they were breathing those words with fractal lungs. It's very ironic. And I'll show you a little natural recursion here. Again, we just take these lines and recursively replace them with the whole shape. So here's the second iteration, third, fourth, and so on. So nature has this self-similar structure. Nature uses self-organizing systems. Now, in the 1980s, I happened to notice that if you look at an aerial photograph of an African village, you see fractals. And I thought, this is fabulous. I wonder why. And of course, I had to go to Africa and ask folks why. So I got a Fulbright scholarship to just travel around Africa for a year asking people why they were building fractals, which is a great job if you can get it. And so I finally got to this city, and I'd done a little fractal model for the city just to see how it would sort of unfold. But when I got there, I got to this palace of the chief, and my French is not very good. I said something like, I'm a mathematician and I would like to stand on your roof. But he was really cool about it. He took me up there and we talked about fractals. And he said, oh yeah, we know a rectangle within a rectangle within a rectangle. We know all about that. And it turns out the royal insignia has a rectangle within a rectangle within a rectangle. And the path through that palace is actually this spiral here. And as you go through the paths, you have to get more and more polite. So they're mapping the social scaling onto the geometric scale. It's a conscious pattern. It is not unconscious like a termite mound fractal. This is a village in southern Zambia. The Baila built this village. It's about 400 meters in diameter. You have a huge ring. The rings that represent the family enclosures get larger and larger as you go towards the back. And then you have the chief's ring here towards the back, and then the chief's immediate family in that ring. So here's a little fractal model for it. Here's one house with the sacred altar. Here's the house of houses, the family enclosure, with the humans here where the sacred altar would be. And then here's the village as a whole, a ring of rings, with the chief's extended family here, the chief's immediate family here. And then here, there's a tiny village, only this big. Now you might wonder, how can people fit in a tiny village only this big? That's because they're spirit people. It's the ancestors. And of course, the spirit people have a little miniature village in their village, right? So it's just like George Cantor said, the recursion continues forever. The most complex example of an algorithmic approach to fractals that I found was actually not in geometry. It was in a symbolic code. And this was Bamana sand divination. And the same divination system is found all over Africa. You can find on the East Coast as well as the West Coast. And often the symbols are very well preserved. So each of these symbols has 4 bits. It's a 4-bit binary word. You draw these lines in the sand randomly, and then you count off. And if it's an odd number, you put down 1 stroke. And if it's an even number, you put down 2 stroke. And they did this very rapidly. And I couldn't understand where they were getting, they only did the randomness 4 times. I couldn't understand where they were getting the other 12 symbols. And they wouldn't tell me. They said, no, I can't tell you about this. I said, well, look, I'll pay you. You can be my teacher, and I'll come each day and pay you. I said, it's not a matter of money. This is a religious matter. And finally, out of desperation, I said, well, let me explain George Cantor in 1877. And I started explaining, why I was there in Africa. And they got very excited when they saw the Cantor set. And one of them said, come here, I think I can help you out here. And so he took me through the initiation ritual for a Bamana priest. And of course, I was only interested in the math, so the whole time he kept shaking his head going, I didn't learn it this way. But I had to sleep with a kola nut next to my bed, buried in sand, and give 7 coins to 7 lepers, and so on. And finally, he revealed the truth of the matter. And it turns out it's a pseudo-random number generator. They're using deterministic chaos. When you have a 4-bit symbol, you then put it together with another one sideways. So even plus odd gives you odd. Odd plus even gives you odd. Even plus even gives you even. Odd plus odd gives you even. So it's addition modulo 2, just like in the parity bit check on your computer. And then you take this symbol and you put it back in, so it's a self-generating diversity of symbols. They're truly using a kind of deterministic chaos in doing this. Now, because it's a binary code, you can actually implement this in hardware. What a fantastic teaching tool that should be in African engineering schools. And the most interesting thing I found out about it was historical. In the 12th century, Hugo of Santillana brought it from Islamic mystics into Spain. And there it entered into the alchemy community as geomancy, the divination through the earth. This is a geomantic chart drawn by for King Richard II in 1390. Leibniz, the German mathematician, talked about geomancy in his dissertation called De Combinatoria. And he said, well, instead of using 1 stroke and 2 strokes, let's use a 1 and a 0. And we can count by powers of 2, right? 1s and 0s, the binary code. George Boole took Leibniz's binary code and created Boolean algebra, and John von Neumann took Boolean algebra and created the digital computer. So all these little PDAs and laptops, every digital circuit in the world, started in Africa. This is in the Mandara Mountains near the Nigerian border in Cameroon, Mukulek. I saw this diagram drawn by a French architect, and I thought, wow, what a beautiful fractal. So I tried to come up with a seed shape, which upon iteration would unfold into this thing. I came up with this structure here. Let's see, first iteration, second, third, fourth. Now, after I did the simulation, I realized the whole village kind of spirals around just like this, and here's that replicating line, self-replicating line that unfolds into the fractal. Well, I noticed that line is about where the only square building in the village is at. So when I got to the village, I said, can you take me to the square building? I think, something's going on there. And they said, well, we can take you there, but you can't go inside because that's the sacred altar where we do sacrifices every year to keep up those annual cycles of fertility from the fields. And I started to realize that the cycles of fertility were just like the recursive cycles in the geometric algorithm.
It's a way of bringing cells into biochemical coordination. Now, if the cells receive some kind of external signal or some signal within the mass, they're all at the same state and they can all react in concert. And this is very interesting because it's a purely physical effect, but it creates what embryologists in the past called developmental fields, or embryonic fields. A field is a system of cells that are coordinated with one another across distances within the embryo.
This is why the fossil record progresses in fits and starts, because sudden shifts of environment cause the apparent emergence of new types. It isn't that they cause it, it's that the new types were always there, but not with any advantage. It's that the new situation has conferred a sudden advantage on them.
So segmented forms will find the niche where they can exist.
Well, let's come at this from a different angle. We've talked a little bit about why these things are held in common, but where is the novelty? Why haven't we seen new patterns of development arise?
Every material has its inherent properties, and although those properties may not always be manifested, when they are manifested, there's a limit to how many different types of things you can get out of it. And similarly with clusters of animal cells, they can manifest a number of different motifs, but it's not unlimited as to what they can form. So in a way, this potential was exhausted early on. If physical forces characteristic of this kind of, it's called the mesoscale materials, it's middle scale, it's not microscopic or molecular, and it's not cosmological, but it's in the middle scale. These middle scale processes can give rise to layers, to interior spaces, to segments. They can elongate if the subunits have certain properties. It turns out that among the genes that were present in the single-celled ancestors, there were a number of genes that were capable of mobilizing these physical forces of the middle scale when the cells found themselves in clusters. Before that, that kind of physics was irrelevant to the individual cell, but in the cluster it became relevant.
In teenage in particular, but almost all throughout life for certain people, there is this tension. On the one hand, you want to belong. You want to be a part of the tribe. You want to be, enclosed in a community and feel the friendship and all the fellowship of being connected. And another part of one wants to stand alone and be an individual who is utterly different from everyone else. They're the tribe.
And by highly social means simply the capacity to live together in groups?
It means living together in groups. We use a special term, eusocial.
Here's an example of our kind of eusociality. This picture would be more at home from a kind of wasp's nest or beehive. You can imagine if this were 100,000 hyenas or 100,000 dogs, they wouldn't be so well behaved. We're capable of extreme acts of coordination and precision. I don't think you could find chimpanzees doing this, even though you can teach them to drink tea.
And that's what the ants and bees, wasps, and humans, and a couple of other mammals do. Right. And that's a very interesting phenomenon, because it raises the question, if high social organization, which we manifest more than anything else, is so successful, why isn't it more common? So I've raised the question as in that form, and I've also said, why did it take so long to evolve? It took humans most of the history of life, which is over billions of years before we appeared.
And it was very slow in coming throughout the Paleozoic era up until about 250 million years ago. There was not a single case, even though there were large populations and faunas of insects of all kinds in the coal forest. And then when we got in the age of dinosaurs, there was nothing that we can see any sign of for a good long while. And finally, we got things like termites and ants appearing, and in good time, when they appeared, these rarities on the Earth, on the land part of the Earth, took over the world. They took over the invertebrate world. Ants alone outweigh vertebrates in most habitats. All the vertebrates on the land, mammals, birds, reptiles, and amphibians, outweigh them 4 to 1. That's an amazing fact. And of all the vast insect mass, biomass, the weight of insects, the ants alone make up, even though they only have a tiny fraction of the species, about 1/3 of all the insect biomass. That's ecological dominance.
So the question is, what took so long? And that has led me then to a whole new layer of investigation in which I set out to find out, how did it happen, this thing that took so long?
And?
And?
How did it happen?
Well, it turns out that we just haven't been looking in all of our arguments about what's the main force, what's the main circumstance that preoccupies anthropologists about humans and the like. We should have been looking more carefully, first of all, at all the social organisms in the world to see if there's a general law, just the way we look at gut bacteria.
Right.
To find out the basic of molecular genetics, just as we look at these little roundworms to figure out how nerve cells put together in a brain, we should be looking at all of the different species of animals that have made this huge leap up in evolution to find out what they held in common. And in a nutshell, it is this, and it explains the rarity and why it took so long. They have to go through a series of steps leading up to the threshold before they go from solitary to advanced social behavior. And these steps include one common feature for all of them, and that is the final step is, and it's a solitary species, individuals that are solitary, live together, forms or creates an expensive and valuable nest from which it forages out, gets prey and other food, and brings it back, feeds the young until they mature. Everyone, without exception, of these species that made the jump over into sociality, including human beings, had to go through that process.
In a mere 15,000 years, humans went from hunting and gathering to creating such improbabilities as the airplane, the internet, and the 99-cent double cheeseburger. It's an extraordinary journey, one that I will now symbolize by embarking upon a journey of my own. Over to camera 2. Hi there, camera 2. It's me, John Green. Let's start with that double cheeseburger. Oh, food photography. So this hot hunk of meat contains 490 calories. To get this cheeseburger, you have to feed, raise, and slaughter cows, then grind their meat, then freeze it and ship it to its destination. You also gotta grow some wheat and then process the living crap out of it until it's whiter than Queen Elizabeth I. Then you gotta milk some cows and turn their milk into cheese. And that's not even to mention the growing and pickling of cucumbers, or the sweetening of tomatoes, or the grinding of mustard seeds, etc. How in the sweet name of everything holy did we ever come to live in a world in which such a thing can even be created? And how is it possible that those 490 calories can be served to me for an amount of money that if I make the minimum wage here in the US, I can earn in 11 minutes? And most importantly, should I be delighted or alarmed to live in this strange world of relative abundance? Well, to answer that question, we're not going to be able to look strictly at history because there isn't a written record about a lot of these things, but thanks to archaeology and paleobiology, we can look deep into the past. So 15,000 years ago, humans were foragers and hunters. Foraging meant gathering fruits, nuts, also wild grains and grasses. Hunting allowed for a more protein-rich diet, so long as you could find something with meat to kill. By far the best hunting gig in the prehistoric world, incidentally, was fishing, which is one of the reasons that if you look at the history of people populating the planet, we tended to run for the shore and then stay there. Marine life was A, abundant, and B, relatively unlikely to eat you. While we tend to think that the lives of foragers were nasty, brutish, and short, fossil evidence suggests that they actually had it pretty good. Their bones and teeth are healthier than those of agriculturalists, and anthropologists who've studied the remaining forager peoples have noted that they actually spend a lot fewer hours working than the rest of us, and they spend more time on art, music, and storytelling. Also, if you believe the classic of anthropology, Nisa, they also have a lot more time for scoodly pooping. What? I call it scoodly pooping. I'm not going to apologize. It's worth noting that cultivation of crops seems to have arisen independently over the course of millennia in a number of places, from Africa to China to the Americas, using crops that naturally grew nearby: rice in Southeast Asia, maize in Mexico, potatoes in the Andes, wheat in the Fertile Crescent, yams in West Africa. People around the world began to abandon their foraging for agriculture. And since so many communities made this choice independently, it must have been a good choice, right?
10,000 years ago, okay, people start farming. Why does this matter for evolution? Because some people would say, well, evolution just stopped because it's not like nature red in tooth and claw and all that stuff, you know, all against all. Like, we have complex societies and all that.
Yeah, they've said that. I've never understood why.
Okay.
Almost any given trait you can think of, any sort of complex ability or something, I mean, one of the things that, you know, it's maintained by stabilizing selection. It has costs and benefits, and it has to be worth having, or it would, for example, resources that go to it would be reallocated to some other thing. I mean, if you didn't need to be strong, then energy could be used for something else, etc. So if you have any kind of major change, you're automatically going to change selection pressures.
Yeah.
If you eliminated a major problem, that changes selection pressures.
Sure. Sure.
I mean, we know certain examples which appear to be close to that. For example, colorblindness. Colorblindness is a lot more common among people who farmed a long time than among people who never farmed at all. By a lot, I mean 8 times.
Yeah. Yeah.
Now that's unusual because it has a very high mutation rate.
Yeah. The options,
but,
right?
You know, without something constantly, you know, purging,
purifying,
purifying it, it gets worse. But other things have changed that probably are not caused by high mutation rates. They've just, you know, things have changed in terms of teeth size, skull morphology. Again, I'm talking about the things we can be sure of from the skeletons.
Yeah. Like, people have become way more gracile in the last 10,000 years.
And I mean, people are more gracile than they were 3,000 years ago in Europe.
Okay, yeah, there was that, the British data, that's what you're referring to, right?
Not just that. Again, John was looking at some skulls in Croatia, medieval skulls, which I believe there's going to be a big increase in demand for moderately old skulls in Europe, which are probably in the back of the museum right now. But for ancient DNA work, people are going to want them.
Yeah.
But he was looking at skulls that were 3,000 years old in Croatia, and you know, maybe 5 or 10% had brow ridges.
Okay.
Nobody has brow ridges in Europe now.
Andre the Giant.
If they're there, they're extremely rare.
There's a few people, yeah.
But these are not exactly like Neanderthals. They're more like Australian Aborigines.
Okay.
But these used to be common, say 20 or 30,000 years ago.
Yeah.
Skulls have changed, and they were continuing to change in historical times.
So why? I mean, like, why does agriculture, why does, you know, quote, modern civilization, like, why would people become more gracile?
To answer that question, let's take a look at the advantages and disadvantages of agriculture. Advantage, controllable food supply. You might have droughts or floods, but if you're growing the crops and breeding them to be hardier, you have a better chance of not starving. Disadvantage, in order to keep feeding people as the population grows, you have to radically change the environment of the planet. Advantage, especially if you grow grain, you can create a food surplus, which makes cities possible, and also the specialization of labor. Like, in the days before agriculture, everybody's job was foraging, and it took about 1,000 calories of work to create 1,000 calories of food. And it was impossible to create large population centers. But if you have a surplus, agriculture can support people not directly involved in the production of food. Like, for instance, tradespeople who can devote their lives to better farming equipment, which in turn makes it easier to produce more food more efficiently, which in time makes it possible for a corporation to turn a profit on this 99-cent double cheeseburger. This is delicious, by the way. It's actually terrible, and it's very cold, and I wish that I had not eaten it. I mean, can we just compare what I was promised to what I was delivered? Yeah, thank you. Yeah, this is not that. Some would say that large and complex agricultural communities that can support cities and eventually inexpensive meat sandwiches are not necessarily beneficial to the planet or even to its human inhabitants. Although that's a bit of a tough argument to make, coming to you as I am in a series of ones and zeros. Disadvantage, farming is hard.
I was wondering if there might be a difference between mortality and morbidity between agricultural and pre-agricultural people. I think I talked to Henry Arpending's wife, Renee Pennington, about this. She was skeptical. But my model is agricultural people, they reduce mortality but increase morbidity, which means that they're sicker, but they don't die off as much because they're more cultural dampening. Like, say, like, cultivating wheat or something. Maybe it's somewhat less, it fluctuates less year to year than relying on animals or something like that.
I'll bet it fluctuates more.
If you think it fluctuates more, okay.
Because you're switching, you're becoming more and more dependent on a very small suite.
Yeah, all the eggs are in one basket, yeah. Okay.
And the other thing is, I think after a while, people, you know, let's suppose there's a carrying capacity. There's a certain total amount of food you can grow with the techniques you have.
Yeah.
I think that in agriculture, at least after a while, people got closer to that capacity at least a lot of the time, because they weren't killing each other as much.
And we have to be less violent in order to coexist in cities or nations or now in the United Nations, bigger and bigger groups. So that violence is no longer very useful. And there's some evidence that there's been a selection that just like dogs aren't as violent as wolves. That
because they don't need to be.
Yes.
It's natural selection.
Yeah.
Everyone without exception of these species that made the jump over into sociality, including human beings, had to go through that process. And that takes a long time.
And so how do you determine who does it and who doesn't do it?
That's the accidents of evolutionary history. We should look at evolution sort of like a maze. You start, say, as solitary, and you evolve. Your species, you evolve. And at some point, the environment is changing or opportunities arise, and you take a turn. You move in a certain direction in evolution. And that might bring you to a dead end insofar as going on to something like advanced social behavior. Or you may, as going through a maze, take the right turn. But only a very few make that right turn.
Then I took a very close look at the evolution of humanity. And an enormous amount has come out in the last 10 and 20 years about the evolution of the human line.
For the first time ever, researchers have presented the gene sequence of an extinct prehistoric human. The geneticist Svante Pääbo, one of the directors of the Institute, has been working on decoding the Neanderthal genome since 1997. Finally, he and his team have achieved their goal, and their findings have caused a worldwide sensation. The Neanderthal has actually left traces in the genome of modern humans, of between 2 and 4%.
The fascinating thing is that we're a mosaic. Our genome is a kind of mosaic. When I go across a chromosome, I'm in one part more closely related to you than to another person. Then, as we go further, I'm perhaps more closely related to some other person than to you. And then, more related to someone in Africa than to you, and now and again, more closely related to a Neanderthal than to you. So what these results actually show is that this large mosaic, this great big puzzle, contains parts which are from the Neanderthal.
My idea, from before we had Neanderthal genetics, was that it was likely that we would get genes from Neanderthals just as a function of them being relatively closely related to us and the possibility of interbreeding happening. And it turns out that that idea has been carried out. We did get something from Neanderthals. But when we look at the way that this transfer of genes has been studied in the history of biology, it's a process called introgression. You're getting genes from one population and introgressing them into another population. This was studied during the 1940s and 50s in great detail by looking at plant breeding. And the idea was that there were traits in plants that might be adaptive, that were spreading from one population to another. Edgar Anderson, the botanist who studied this in the most detail, said that introgression from one population to another is something of a paradox. It's a paradox because the more important it is, the less likely you are to notice it. And if you think of this, if you were looking at two kinds of plants and you could really differentiate them very clearly, but you noticed that once in a while there was a flower color in this population of plants that was actually from the other population, or that there was a seed shape that had transferred, you would notice it because it sticks out. It doesn't belong there. But when you look at things that are much more widespread across the genome, introgression might be more important, but it wouldn't be nearly as noticeable to you.
So then, because these molecules were already there, they didn't have to newly evolve. You have this explosive diversification of body plans and forms when this first happened, and then you really can't get much more after that. But what you can do is you can stick with those forms, and you can reinforce them by further genetic evolution. You can integrate them with one another. There are many things that have happened in the last 500 million years, but among the things that have happened is not the production of new forms, because the era of morphological diversification basically has passed, and now we're just building on those templates.
Your article is actually part of a special issue on how forces work in development. Can you talk a bit about how tension and adhesion play a role in development?
In individual single cells, you might have adhesion molecules on their surfaces, and you also have tension in individual cells because every cell has a cytoskeleton that tugs from the inside on its surface. Now, if you have a cluster of cells, the basis of a clustering is adhesion. You can get separation into different layers because of differential adhesion, but you can also get cells kind of tugging from the inside and pulling away from each other, and that basically complicates things. In a non-living liquid, nothing is tugging from inside the molecule to pull the individual molecules away from each other. So this is basically a unique characteristic of the kinds of liquid-like materials that a cluster of cells represent, because it has this internal tugging that can change the balance of forces.
Natural selection, that's the action in the environment that allows some genes to succeed more than others, really is acting at two levels. It's acting at the level of the individuals competing with one another within a society, for the most part, and it's acting at the level of group versus group. And we know now, looking at it a little more with clearer eyes, that group versus group is an absolutely fundamental and overpowering phenomenon in human behavior.
How would we study altruism and compassion from a evolutionary perspective? And one thing that means is that for anything that you might want to study, there's actually not one but four questions that you need to ask. The first question is, why does this thing exist compared to the many other things that could exist? And often based on its contribution to survival and reproduction. And in the case of altruism and compassion, that actually turns out to be a very fundamental puzzle. So imagine the altruistic and compassionate individual, okay? What would be the purest form of altruist and compassion? How would such an individual behave? Such an individual would be very other-oriented. They would always be doing things for others, even at the expense of themselves. Well, that's a puzzle because evolution is all about favoring traits that cause individuals to survive and reproduce better than other individuals. It seems that the altruist is at a disadvantage. So altruism, there's something about altruism that's vulnerable to exploitation by that which we call selfish. And so just explaining how altruism can survive in a Darwinian world is a puzzle that was a puzzle to Darwin. And he had a solution, which is actually a very simple solution, is that the altruist can actually thrive in a Darwinian world to the extent that they interact with other altruists. Groups of altruists do well compared to groups of non-altruists, even though the individual altruist might not do well compared to a selfish individual within his own group. And so that's the concept of multi-level selection. Natural selection is operating at more than one level. At the most local scale, altruism is not advantageous, but if we go up in the scale, then groups of altruists are more fit. And so we actually, if we want to know the distribution and abundance of these nice traits in the real world, we have to ask, how often is it the case that this clustering takes place? And so there's a whole line of research which has nothing to do with how do we train individuals to be altruistic. It's what happens to the altruistic individual when they go out into the world. Do they find each other and so on? And one of the fascinating things about this, which is part of being an evolutionist, is that it just widens your frame of comparison. So in this talk, which is mostly about humans, I also talked about insects. And there's a species of insect called the water strider, which is a wonderful insect that skates on the surface of pools and in streams. And it turns out that in water striders, there's enormous individual differences among males in their aggressiveness towards females. And some males are sexual predators. They're just hunting for females. And when they find one, they attack them, and frankly, they rape them. Or at least they attempt to. At the opposite end of the continuum, there's males that are gentlemen. They're docile towards female, and they wait to be asked to perform their manly duty. Okay? So why do we get these individual differences in males? My graduate student, former graduate student, Omar Eldakar, did experiments in which he formed groups of males. Each group was a pool, had 6 males and 6 females, and these males were composed to be everything. Some pools had 6 psychopaths, some pools had 6 gentlemen, and some pools had mixes of the two. And then you watch them, and you ask who gets the girls, okay? And it turns out that in these pools, whenever there's both types of psychopaths and gentlemen, it's the aggressive ones that win. It's always the aggressive ones that do better than the non-aggressive ones. And so at that scale, there's everything is favoring the aggressive individuals. So that's part of the story. The other part is that pools in which everyone is a gentleman, the females are 3 times more productive. They have 3 times more children than the pools in which everyone is a psychopath. Because the psychopaths are terrorizing the females. They can't eat, and therefore they can't lay eggs. And so you have this huge difference at the group level. And it's the combination of those 2 things which keep both types in the population. Okay? Now we go from insects to people. And my work, a lot of my work is in my city of Binghamton. I study my city the way Omar Eldakar studies his water striders. And so we measure individual differences among people and how pro-social they are. We might give them a survey, we might measure it in another way, but the fact is that there's huge differences among people, men and women, just the way there is in male water striders, in how nice they are. So basically, we measure these individual differences, and then we know where they live. So we know that their residential location in the city of Binghamton, plus much else. And when you map, you create maps of the city. They're called GIS maps, for Geographic Information Systems, which look like topographic maps. They have hills and valleys. But those hills and valleys are not geographical hills and valleys. They're hills and valleys of pro-sociality. And it's a very rugged landscape. It looks a bit like the Himalayas. And what that means is that there's neighborhoods in which the average person is much nicer, more pro-social than other neighborhoods. And when you look at social networks more generally, which might or might not be spatial, what you find is that the clustering that we've been talking about, the fact that the high pros, as we call them, the highly pro-social individuals, that if you're a teenager in the city of Binghamton and if you're highly pro-social, then you have a lot of social support. So there's a strong correlation between your pro-sociality and the pro-sociality of those with whom you interact. And it comes from multiple sources. You have a more supportive family, a more supportive neighborhood. You feel that school is more supportive. You're more likely to belong to a religion. You're more likely to engage in extracurricular activities. And so those who give get. And that's the fundamental requirement for pro-sociality to win at the Darwinian contest. So now, if you're not pro-social, why are you not pro-social? Is it because you were born selfish? Or is it because you have lived in such an unsupportive world that the only way for you to survive in that world is to turn off your pro-sociality? One way I often put it is, imagine that you're a highly pro-social individual, but unluckily for you, you find yourself in a really mean social environment where nobody's being nice back to you. So what are you going to do? What are your options? Here are your options. There's 4. 1, you can leave. 2, you can try to change those around you and get them to be more pro-social. 3, you can turn off your prosociality defensively. 4, you can remain prosocial and suffer the consequences. That's all you can do. And so who would counsel such a person to remain prosocial in that situation? Now, right away, that tells you something a little bit counterintuitive. That if you think that compassion and altruism is such a great thing, and you think we should all be compassionate and altruistic, and let's say that I were able to take you and succeed at that, so I make you more compassionate, and then you go off and live your life, maybe I didn't do the right thing. It all depends on what kind of environment that you inhabit. And so when we see things we don't like in society or other people who are behaving in a way which is not pro-social, or perhaps they themselves are suffering as individuals, often it looks pathological. It looks like something broken that we might want to fix. But what it really is, it's a survival strategy.
There are a lot of people that believe that we're stuck with, many of us are stuck with mediocre genes and therefore a mediocre mind. And this was actually embodied in a book about 15 years ago called The Bell Curve. And the message of the bell curve, one of the messages was, sorry to say, but there are people with good genes for intelligence, there are people with bad genes for intelligence, and this is just the way it is. We can't do anything about it. They called it genetic separation. And here's a quote from the book. The irony is that as America equalizes the environmental circumstances of people's lives, the remaining differences in intelligence are increasingly determined by differences in genes. Putting it all together, success and failure in the American economy and all that goes with it are increasingly a matter of the genes that people inherit. Now, they did have science to back this argument up. I strongly dispute that science, but I don't view these guys as racist, actually. I think they were arguing what they thought science was telling them. And it's a pretty depressing message when you think about it. You don't even have to think about it. It's right there. Only some of us are capable of extraordinary success. Well, I spent the last several years researching for a book that was just mentioned about the science of human potential. And I'm going to spend the next 14 or 15 minutes explaining why I think that these authors of the Bell Curve actually got it dead wrong. So we're going to start with a story about rats from 1958. You got your rat dopes. I didn't think this was a funny slide when I made it. Wait till you see the cat. If you think this is funny. You've got your rat dopes and your rat Einsteins. These are two different breeds of rat that were actually genetically partitioned, just as the Bell Curve authors warned people would eventually be. They're genetically partitioned for intelligence. So over several generations, these rats, these two different breeds, were raised for two different kinds of intelligence. And this is the running of the maze that shows how reliable this was. This is after many generations. They ran these two different breeds through a maze. And so you can see the rat dopes are making many more maze errors than the rat Einsteins. So what these researchers did at the University of Manitoba in 1958, they took the same two groups and they wanted to see how environment affected the outcome. So they raised new generations from each breed in a rat slum. Imagine, a rat cage is already kind of a slum, but imagine it much, much worse. Very little light. Again, this is not, I'm glad that you're finding this funny. It's true. Very little light, no way for these rats to exercise their brains or their minds in any way. They raised these two breeds in this slum, and then they ran the new generations through the mazes, and look what happened. The genetic differences, the apparent genetic differences that had been around for many generations between these two breeds, basically disappeared. The rat Einsteins made just as many mistakes. Then they did the opposite. They tried the opposite environment. They made what I call the rat Four Seasons Maui, which is lots of light and lots of patterns on the wall and every possible rat exercise machine you could imagine. And except for the freedom part, it was like a rat's paradise. And they raised new generations of each breed in that, and they ran it through the maze, and almost the same result as with the slums. The genetic differences all but disappear here. There is a slight difference, as you can see. The rat Einsteins made slightly few errors, but that was deemed statistically insignificant. So again, basically the message is this reliable genetic difference between these two breeds disappeared. How could that be? This really defied understanding in the 1950s, because that's not how they thought of genes. They had a certain way of thinking about genes, a certain model. We can call it the blueprint model. This is like this blueprint of the Eiffel Tower, in that genes, and this is still the way that most people in the general public think about genes, genes have very specific information for what your traits are supposed to look like. They have instructions that are right inside the gene that says that you're supposed to get a certain eye color. There's an instruction inside a certain gene or set of genes that says what your height is supposed to be. There are instructions inside genes that say how athletic you're going to be or how musical, and so on and so forth. The blueprint model. Well, what happened was, over the ensuing decades, a whole new understanding of genes came to be, and it's what I call the mixing board model. It's the genes don't have that information about what finished traits are supposed to look like. Instead, genes do have instructions, but they're more like knobs and switches. They get turned on and off all the time. Scientists call it gene expression. So genes do have instructions, but how those instructions are carried out actually depends very much on other genes and also signals from the environment. So you can never say that a certain gene is going to absolutely produce this certain outcome. I shouldn't say never. Very, very rarely can you say that. It's really, and what we've come to understand in the last 20 or 30 years is that really everything about genes is about gene expression, or epigenetics is another way to say that.
So say you have a clone or a secret identical twin, because you know that a twin or a clone is a genetically identical person to you, which is crazy, but it's true. Anyway, so you have this clone or your twin or what have you, and your parents decide that it's too much trouble to keep both of you. And so they give your clone to a kind of sketchy traveling circus. Now, I know your parents probably wouldn't actually do this, but just roll with me for a minute. So for the purposes of this example, let's just say that you grew up living a normal suburban American life, while your clone grew up with less stability and less access to nutritious food and less education, but more exercise and more access to sword swallowers and bearded ladies. And let's say you guys are 50 years old or whatever, you get together and have some lunch. So you're sitting there across the table from your clone. What do you think you see? Well, for starters, clone probably has a tattoo on its face. And if clone had stayed in the circus, clone probably, professionally rides a unicycle over a tightrope, so clone is probably in pretty good shape. But then again, clone probably smokes cigarettes and probably was malnourished as a child, so might be slightly shorter than you. By the same token, let's say that you've been eating Sonic tater tots 5 days a week since 1992, so you're looking a little bit tubby. Plus, you spent the last 20 years at a really stressful job that puts you at risk for all kinds of weird health complications. So, at 50, you and clone would probably look pretty different from one another. But it turns out, you don't just look different, you actually have become different. Now, if some scientists looked at your genetic code, they would say that your DNA was still exactly the same as that other person. That is to say, if your genome is a paragraph, all of the letters would be in the exact same order. But on another level, there would be a huge difference, and if we extend this metaphor, we can say that the letters are in the same order, but the spaces and the punctuation are all in different places. Of course, completely, potentially changing the message of that paragraph. The study of this genetic punctuation that I'm talking about is called epigenetics, which literally means
above genetics. The epigenome doesn't change your DNA, but it decides how much or whether some genes are expressed in different cells in your body. Epigenetics looks at what happens to your genes over the course of your life and whether those changes could be passed down to your children or even your grandchildren. So here's the way epigenetics works. You have billions of cells in your body, and they each contain your DNA, the same exact blueprint of your genetic code. But just because they have the DNA doesn't mean that they know what to do with it. They need outside instruction from these little carbon and hydrogen compounds called methyl groups. The way these methyl groups control the genome is by binding to a gene and saying, do not express this gene. The methyl groups bind differently to your genome in a skin cell versus, say, a tongue cell or an eyeball cell. And that is one of the ways that a cell knows that, hey, I'm a skin cell, or hey, I'm an eyeball cell, or hey, I'm a muscle cell. In addition to methyl groups, epigenetics is also controlled by histones, which are proteins that are basically the spools that DNA winds itself around. Histones can change how tightly or loosely the DNA is wound around them. If they're more loosely wound, the genes can express more, and if they're more tightly wound, then they express less. So whereas the methyl groups are more like a switch, the histones are more like a knob. Every cell in your body has a distinct methylation and histone pattern. And that is what gives every cell its marching orders. Think of your genome, the DNA, as the actual hardware of the computer, while the epigenome is more like the software, which tells the hardware what to do. The genome is what's going to be doing all the work, but the epigenome is going to be telling it what to do. So the hardware of your DNA is going to be the same throughout your entire life. But these epigenetic tags do change throughout your life, and they decide what genes get expressed or not. Now, epigenetic information in a cell isn't permanent. It can change throughout your life, and it can be hereditary. And it can change over time, especially when your body is going through a lot of changes, like, say, during puberty. A bunch of methyl groups kick in and they're like, okay, so you guys over here, you're gonna have to start growing hair, and you guys over here, I really need you guys to get behind giving this guy some really horrible acne. Or like when you get pregnant, which hopefully I won't, but when you do, your epigenome has to be like, all right, guys, everything's about to get a whole lot bigger in here, and we're gonna have to pass something the size of like a Merriam-Webster's dictionary through that little pipe over there, so let's get this thing done. But it's not just these dramatic times when the epigenome is changing. It changes subtly throughout our entire lives. And it changes based on a lot of environmental factors, like what we do, what we eat, what we smoke, and how stressed out we are on a daily basis. Scientists have found that things like a bad diet can actually lead to methyl groups binding to the wrong place and making mistakes. And with those bad instructions, cells become abnormal and become a disease. And then basically all hell breaks loose and you get cancer or something. Epigenetics is a very young science, though we've known about the epigenome since the 1970s. It's only in the last 20 years that we've even known what effect these epigenetic tags are having on our DNA. And even after they got all that business straight, scientists still thought that all of our epigenetic tags were stripped off of our genome before they were passed on to our children. So if you started smoking 10 packs a day when you were 10 years old, that would certainly be a horrible health decision for you, but you wouldn't necessarily be harming your unborn children in any measurable way. However, the thinking on that is changing pretty rapidly. Because it's true that a lot, even most of the epigenetic information from a parent is stripped off of the embryo's genome in the first few days, and fresh ones are created specifically for this new person. However, some of these tags get stuck on the genome and are passed down from generation to generation. And it just so happens that the more they study this, the more it looks like bad epigenetic information is being passed from generation to generation. And this is a whole new way to think about how we pass information between generations. Your grandmother was making dietary decisions that affect you today. As we experience all of these new strange epidemics, diabetes, autoimmune disorders, cancers, that weren't appearing in previous generations, it's starting to look like these may be caused by epigenetic information passed down from our parents. I know! It's such an unbelievable buzzkill! There is no point in our lives when we can do anything without guilt anymore. The discovery that the environmental factors a parent experiences can be passed down from generation to generation was sparked in the 1980s. And this happened when some scientists were looking at the birth and death records of some people who lived in 19th century Sweden. This is a weird place to find a genetic revolution, but there it is. It wasn't just any place in Sweden. It was in Norrbotten, which is the northernmost county in Sweden, which is literally in the Arctic Circle. And despite the fact that Norrbotten was literally the worst place you could possibly choose to live in Sweden, there were some people living there in the 1800s. And they were completely cut off from the rest of the world. Let me clarify. These people were isolated. Like, if they didn't have a good crop year, people died. No, it wasn't ideal, but, you know, they didn't ask me my opinion, so I'm not giving it. So anyway, these people subsisted entirely on what they grew and the animals that they raised. And like I said, sometimes they starved. But sometimes they had huge, bountiful years of plenty. And when that happened, people totally went ape crackers. I mean, of course they did, because they were so freaking hungry, and then all of a sudden there was all this damn food everywhere. Anyway, there was a public health specialist who was looking at the effects of the people who grew up in the really bad starving periods of time versus the people who grew up in the eat all you can at the smorgasbord years. And you might already be guessing what they found out. People who went from relatively slim pickings to feed your face until you have to barf and then do it all over again in a single season, those people died an average of 6 years sooner than their starved out counterparts. And you know what sucks? So do their kids. And so do their kids' kids. Boo epigenetics. So, of course, now we all know, and we're all going to stop doing unhealthy things starting today. Unless the damage is already done. The damage is almost certainly already done. But hey, epigenetics brings good tidings along with the bad ones. For instance, we now know that certain types of cancer are caused by misplaced epigenetic tags. And scientists are now developing drugs that can silence the bad genes that were supposed to be turned off in the first place.
And you've probably read that having the sequence of the human genome available was crucial to the discovery of unmistakable traces of Neanderthal DNA mixed into some modern human populations. So what percent of genomic DNA in people from Eurasia and the southwestern Pacific was inherited in the Neanderthals, from Neanderthals? Between 1 and 4%. But did you actually know that this inherited material is not concentrated in genes? Instead, it's spread somewhat randomly in the non-coding portions of the modern human genomes. And doesn't it make you wonder what it contributes?
Could you say a little bit more about this idea of neural diversity and how it relates to Neanderthals?
We have in our own population a variety of individuals who cover a spectrum of neurodiversity, meaning that they're high-functioning autistics, dyslexics, even bipolar have been major world leaders and thought leaders despite or possibly because of their neurodiversity.
The Neanderthal has actually left traces in the genome of modern humans.
There are several areas related to mental development, for example, mutations which lead to autism or schizophrenia.
We might find additional highly optimal, these are not like these are mutants.
We see that autistics are not only intact, but they happen to be superior.
Some of the ways in which autistics are superior to normal people would be useful for science.
Considered autistics as perceptual experts.
So they're perceptual experts?
They are perceptual experts.
And the face is also stuck forward really far relative to the brain case.
When comparing boys with autism to typically developing boys, she found significant differences in face shape.
They have a broader mouth. The divot above the upper lip seems to be broader, as well as sort of the mid-face region.
The brains of children with autism are actually larger.
The brain development of modern human babies differs significantly from that of the Neanderthals.
Neanderthals did have bigger brains than us, but they didn't have bigger brains than the people who followed them in Europe. Those people's brains were expanding.
The modern human with a Neanderthal, this Neanderthal skull just goes back and back on the occipital cortex, the part that's related to vision.
And I used to joke around about having a gigantic internet trunk line going deep into my visual cortex.
Being attracted by symmetry is something that has been commented a lot about Neanderthals.
It appears that they were made by Neanderthal as opposed to Homo sapiens. We didn't really think that Neanderthal made art. And so, yes, we're not sure, but this is also 10,000 years older than the other oldest pieces of art we knew about.
Since he was a toddler, Dane has been able to draw with extraordinary precision.
When he was 11, he drew a perfect aerial view of London, after only one helicopter ride. Even the number of windows in all the major buildings in his drawing was correct.
This, of course, implies that they probably did swim. They probably had some pretty sophisticated boats to get there.
People have described this object for the production of music by Neanderthals.
What about YMCA? Let's switch to a Russian dance.
different populations of people, for example, Europeans and Chinese people, have different Neanderthal genes. There are a number of things that I have that came from Neanderthals. One of the things is a part of the androgen receptor, increases the likelihood of baldness.
Published this year, the androgen receptor gene associated with autism.
Now, there's a psychologist at Cambridge University, Simon Baron-Cohen. He writes of the male mind and the female mind.
Children with autism show faster brain development, and when you actually compare different parts of the brain, some structures fit this extreme male pattern.
And at first, the only language that I had for it was gender. But then I started to notice that some men had these traits and some women did not at all. That's when I realized it was actually introversion and extroversion, and that there was no real language for talking about questions of identity.
More autistic children are born to MIT graduates. There's more autism here in Silicon Valley. The sort of nasty conclusion from this is that too much mathematical ability is bad for your children.
Creatures on Earth who reached a very high level of social organization.
That'd be us.
That's us. The social insects.
Right. That'd be ants.
You find it not only in people, but you find it in simple animals, some of which, like ants, build complex society.
Through their work with diverse ant species, Albuhaif and his team reveal that super soldier-like traits can lay dormant and be induced by exposing larvae to an overdose of a naturally occurring hormone.
Simon Baron-Cohen has pretty good data that it's the fetal testosterone.
Testosterone seems to have organizational effects on brain development.
There are 8 species known as super soldiers because they're much larger and they even have larger heads and a larger body. They use their large heads to block the nest entrance when attacked by army ants. Phenotypes that get induced in populations that reflect these kind of ancestral traits. Previously, evolutionary biologists had treated them as sort of the Barnum and Bailey of evolution, or some kind of slips of a developmental system. And what we're showing here is that no, the fact that we can induce it reflects some deep underlying potential that goes back to the ancestor. So the ancestor must have had this trait. It lost the expression of the trait, but it retained this genetic potential. When a queen lays an egg, if it receives the right temperature cues, it becomes a queen. If not, that egg develops into a worker. If it gets the proper nutrition, it develops into a soldier. And these switches during development are governed by a hormone called juvenile hormone.
In humans, as well as other animals, the hormone does its work by binding to androgen receptors, which are all over the body, but are also found in the brain.
Parts of the motor systems are committed to social behavior. They are mirroring your behavior.
Suggesting possibly autism may have something to do with mirror neurons.
In fact, in our hominid ancestry, males and females occupied very different niches, with females taking much more of a social role, and with males having a much more of a solitary role.
There would be very little point in having a mirror system if you lived on your own. There'd be a lot of point in having a digestive system, having a movement system, having a visual system if you lived on your own, but there'd be no point in having a mirror system.
How do you determine who does it and who doesn't do it?
That's the accidents of evolutionary history.
There's another type of evolution where two organisms come together to make one.
It's a process called introgression. We have more than a dozen Neanderthals from whom we've got complete mitochondrial DNA sequences.
But because mitochondria replicate themselves in a separate fashion, it doesn't get mixed with the DNA of the father. It's just the mother's mitochondrial DNA.
Their mitochondrial sequences are all distinct from ours.
Because after all, when two groups meet each other and there's some social inequality, one almost always mixes, but the offspring will generally stay with one or the other group.
This is a rapidly evolving field. It also seems to be why a number of hybrid crosses, for example, between a horse and a donkey, give rise to a mule that is sterile because of the incompatibility of the mitochondria with the nuclear DNA.
The mitochondrial DNA must itself have been affected in its evolution by its function.
In the first committed steps of innate immunity,
they found that the Neanderthals had particular gene variants that play a big role in immune defense.
It looked as though there were alleles that came into the modern human population
The downside was that it gave a greater risk of not being able to control the end of the response to infection and leading to autoimmunity.
He says that could explain the increasing prevalence of diseases like lupus, celiac disease and autoimmune hepatitis.
Children with mothers who had celiac disease were nearly 3 times as likely to be diagnosed with autism. Juvenile diabetes was also associated with a higher risk of autism, and children with mothers who had rheumatoid arthritis were also at a 70% increased risk for autism.
And so now we're having to readapt to this changing environment.
Well, this architecture creates problems for our genome.
We and many other people around the world are onto something by looking at these copy number variants.
There may have been a copy number difference between the Neanderthal and the reference human genome sequence.
They're going to be in these parts of the genome that used to be called junk DNA.
We have the genes that once enabled our ancestors to have as good a sense of smell as dogs, but the genes have mostly been turned off.
Isn't that the premise of X-Men?
It was analyzed as a Tourette's and Asperger's, which I still have a little bit today.
In hunter-gatherers, they don't have bosses. When somebody tries to be a boss, they make merciless fun of you.
In mutual knowledge, A knows X, B knows X, A knows that B knows X, B knows that A knows X, A knows that B knows. When the little boy said the emperor is naked, he wasn't telling anyone anything that they didn't already know. He was nonetheless changing the state of their knowledge, because everyone now knew that everyone else knew that everyone else knew, and that gave them the collective power to challenge the dominance of the emperor through their laughter.
Kids with autism produce pretty much only one kind of laugh. Like in our conversation right now, if I say something dumb, you might kind of... And you don't really feel good inside, but you've learned to sort of grease the social wheels in this context. Kids with autism, I don't think that they're probably picking up on those subtle social cues. They're genuine, so they just laugh when they feel good. Kids are producing these sounds that may actually influence others positively.
So you want to be a part of the tribe and you want to be a part from the tribe. And it's that pull that I think gives an enormous creative tension that allows people, it's that spark of electricity, if you like, that makes people creative. It's their desire to be absolutely unique, but also their desire to belong. That sense of, so they understand other people and what it is to be part of the community, but they also understand the sense of the status of an alien and an outsider.
Humans were quite consistent with the rule of reaching eusociality in advanced culture, advanced society, quite consistent with all the rest of the animal kingdom. And of course we were different in that we developed culture along the way, but our culture is very much influenced by the instincts that evolved in our pre-human ancestors. Okay.
So in this, in the kind of the theory you lay out, in the picture you lay out, you talk a bit about this idea of, again, building a nest, and this idea of the fire, the idea of having campsites. In a sense, the technology, in a sense, is the precursor or a needed step to this other larger social evolution.
Yeah, the chimps have culture. They have technology.
Technology is like a mirror. If an idiot looks in, you can't expect an apostle to look out. You know, I remember when I first saw some Photoshop, the very first version of it was called Pixel, in fact. It was a very early version. And I saw some of the things that it could do, and I couldn't wait to put it on little floppy disks onto my computer. And I raised my fingers and then thought, oh, I don't have any artistic talent. What's the point? It's like you get a great keyboard, but you've got nothing to express musically. It doesn't matter how good MIDI is and how many synthesized, sampled instruments you have. It facilitates. The great thing about social networking, which at the time we're talking, of course, is still growing at what seems an exponential rate, just all the time, the upward curve of it, is that everybody has a talent to interact with other people, short of being on the autistic spectrum, of course, which is something that many people are in very small ways or in greater ways. But even that can be helped by the interactions of the internet.
In school, the way of conveying ideas is through words. A teacher walks up to the board, writes words, says words. Students receive books with words and are expected to respond to questions with words. The vast majority of teaching is done through words. But let's look at who we're trying to teach. Focusing on California, 25% of students are English language learners. Another 15% have language-based learning difficulties, such as dyslexia. An additional 20% fail language comprehension tests. And a large portion of the remaining students characterize themselves as visual learners. Left over, there's only a tiny little segment of students for whom current teaching methods are a good fit. And I was one of those students way down there. I have dyslexia. And for me, words were really big learning barriers. I mean, I didn't even learn to read until I was in 5th grade. Years later, I read a biography of Albert Einstein, and I discovered that he was dyslexic too. And one quote from him really struck me. He said, "The words or the language as they are written or spoken don't play any role in my mechanism of thought." Wow. So if words are not needed for great math and science thinking, then maybe words aren't needed for great math and science teaching. And so when I started investigating how we might be able to teach without words, I was shocked at how language-heavy even preschool materials are. I mean, look at this worksheet I ran across. Color the shape that is the same as the first shape in each row. They even have it in Spanish. So I wondered, what would happen if we remove all those words and hand this over to some 4-year-olds along with some crayons and don't say anything? This is what happens. We didn't tell them what to do, and so they did whatever they wanted. But how do we tell students what to do without words? Here's one way. Interactive software with informative feedback. If you click on the wrong thing, it shows you why you were wrong. And when you click on the right thing, it shows you why you were right. And you can help a little penguin across the screen. Okay, so this works for shapes, but what about things like word problems? I mean, how can we do those without words? Well, here's a typical word problem from a 2nd grade textbook. Ostriches have 2 legs. How many legs does a group of 3 ostriches have altogether? We can translate this into a completely word-free problem. Again, if you don't know what to do and you get it wrong, say you pick 8 legs, it shows you why that's wrong. We picked too many. And when you get it right, it shows you why it's right. The feedback teaches the students. It doesn't just replace the words. It provides more instruction than the words ever did. And this visual feedback is so powerful that we can use it to teach really sophisticated subjects. This is pretty sophisticated. This is a page from an Algebra 1 textbook. A very language-heavy approach. And here's what it does to our kids. Over 70% of students fail to learn this stuff. Now here's a visual game teaching that very same content. Here students are learning to factor and solve quadratic equations, all done visually with informative feedback. And because these games allow students to touch, feel, see, and interact with the math, it's able to clear up many of the mysteries about how and why math works. For instance, when only done through words, students often find it mysterious why multiplying 2 negative numbers produces a positive number. But when done visually, like in this block stretching game, students can see how multiplying by a negative number not only stretches, but also flips the block in the opposite direction. And then when you multiply by a negative number again, it ends up flipping it again back to positive. It's not mysterious anymore. It's fascinating. And so we've created hundreds of these games to teach all the math concepts from pre-K through Algebra 1. Here are some exponents and some fractions we're basically able to boil all math down to how do you help a little penguin across the screen? But does it work? UC Irvine recently conducted a study where they put these visual games into 106 schools in Orange County. And after 1 year, we're able to triple the rate of growth in math proficiency. And last year, we replicated this result in Silicon Valley, Las Vegas, Chicago, and Houston. This simple innovation of removing the language barriers is able to elevate math proficiency everywhere we put it. And of course, increasing standardized test scores is great, but we will also want to make sure we increase real mathematical thinking. And we definitely see that too. Because instead of just throwing a bunch of words at students, we create rich opportunities for them to connect their own dots in their own heads about how math works. And when students play an active role in figuring things out, they want to talk about it. It sparks mathematical talk. And in this way, a language-free approach can actually improve language skills. A striking example of this is a young autistic student named Omar, shown here with his dad. Omar had such difficulty with language that he only spoke in single words, never in full sentences, not even to his parents. And when Omar's school started using our program, his teachers were astonished at how gifted Omar was in math. They never knew. But more amazingly, Omar started talking. And the first full sentences he ever spoke were about these mathematical ideas he was experiencing in these visual games. And he's now excelling in school in both math and English, and it has completely changed his life. And so all of us familiar with TED understand the importance of saying a lot in a few words. And I think the idea we're spreading here is that all students, not just students like me and Omar, but all students can benefit profoundly from some opportunities to learn without any words at all. Thank you.
You know, you once wrote, I like this quote, "If by some magic autism had been eradicated from the face of the earth, then men would still be socializing in front of a wood fire at the entrance to a cave."
Because who do you think made the first stone spear? It was the Asperger guy, and if you were to get rid of all the autism genetics, there'd be no more Silicon Valley, and the energy crisis would not be solved.
So I want to ask you a couple other questions, and you know, if any of these feel inappropriate, it's okay just to say next question. But if there's someone here who has an autistic child or knows an autistic child and feels kind of cut off from them, what advice would you give them?
Well, first of all, we got to look at age. If you have a 2-, 3-, or 4-year-old, you know, no speech, no social interaction, I can't emphasize enough, don't wait. You need at least 20 hours a week of one-to-one teaching. You know, the thing is, autism comes in different degrees. There's going to be about half the people on the spectrum that are not going to learn to talk, and they're not going to be working in Silicon Valley. That would not be a reasonable thing for them to do. But then you got these smart, geeky kids, you know, the touch of autism.
So I was a really terrible student when I was a kid. My GPA was consistently in the low 2s. And I think the reason that I was such a terrible student is that I felt like education was just a series of hurdles that had been erected before me and that I had to jump over in order to achieve adulthood. And I didn't really want to jump over these hurdles because they seemed completely arbitrary, so I often wouldn't. And then people would threaten me, you know, they'd threaten me with this going on my permanent record, or you'll never get a good job. I didn't want a good job. As far as I could tell, at 11 or 12 years old, like, people with good jobs woke up very early in the morning. And the men who had good jobs, one of the first things they did was tie a strangulation item of clothing around their necks. They literally put nooses on themselves, and then they went off to their jobs, whatever they were. That's not a recipe for a happy life. these people, in my symbol-obsessed 12-year-old imagination, these people who are strangling themselves as one of the first things they do each morning, they can't possibly be happy. Why would I want to jump over all of these hurdles and have that be the end? That's a terrible end. And then, when I was in 10th grade, I went to this school, Indian Springs School, a small boarding school outside of Birmingham, Alabama. And all at once, I became a learner. And I became a learner because I found myself in a community of learners. I found myself surrounded by people who celebrated intellectualism and engagement and who thought that my ironic, oh-so-cool disengagement wasn't clever or funny, but like it was a simple and unspectacular response to very complicated and compelling problems.
And youth cultures that old people stupidly mock because they say, "Oh, you're trying to be different, but you all dress the same." Oh, ho, ho, ho! You just don't get it. That's not the point. You really do hear adults say that and think they're being clever. Huh, you all have the same rings and gothic whatevers, and now you say you just want to be different. Well, you're not. No, it's not. That's what they're doing. Is what I'm describing is they're belonging, but they're outside.
It's a survival strategy. It's the way they must be in order to survive in the world where they're at. And that's true not just for pro-social behaviors, it's true for such things as risky adolescent behavior. When teenagers do things that seem self-destructive, even for themselves, that actually is often a survival strategy. And if we want to change it, we can't just tell them to stop doing it. We have to actually provide them with another strategy or to alter their social environment so that something else might work.
I got social interaction through shared interests. I rode horses with other kids, I made model rockets with other kids, did electronics lab.
And so I started to learn because learning was cool. I learned that some infinite sets are bigger than other infinite sets, and I learned what iambic pentameter is and why it sounds so good to human ears. I learned that the Civil War was a nationalizing conflict. I learned some physics. I learned that correlation shouldn't be confused with causation. All of these things, by the way, enrich my life on a literally daily basis. And it's true that I don't use most of them for my job. But that's not what it's about for me. It's about cartography. What is the process of cartography? It's, sailing upon some land and thinking, I think I'll draw that bit of land. And then wondering, maybe there's some more land to draw. And that's where learning really began for me. It's true that I had teachers that didn't give up on me, and I was very fortunate to have those teachers because I often gave them cause to think there was no reason to invest in me. But a lot of the learning that I did in high school wasn't about what happened inside the classroom. It was about what happened outside of the classroom. For instance, I can tell you that there's a certain slant of light winter afternoons that oppresses like the heft of cathedral tunes, not because I memorized Emily Dickinson in school when I was in high school, but because there was a girl when I was in high school, and her name was Amanda, and I had a crush on her, and she liked Emily Dickinson poetry. The reason I can tell you what opportunity cost is because one day when I was playing Super Mario Kart on my couch, my friend Emmett walked in and he said, "How long have you been playing Super Mario Kart?" And I said, "I don't know, like 6 hours?" And he said, "You realize that if you'd worked at Baskin-Robbins those 6 hours, you could have made $30. So in some ways, you just paid $30 to play Super Mario Kart." And I was like, "I'll take that deal."
So most people, if you ask them what are they most passionate about, they'd say things like, my kids or my lover, or what are you most passionate about?
I'm passionate about that the things I do are going to make the world a better place. When I have a mother of an autistic child say, my kid went to college because of your book or something, or one of your lectures, that makes me happy.
So this is a map of New York State that was made in 1937 by the General Drafting Company. It's an extremely famous map among cartography nerds, because down here at the bottom of the Catskill Mountains, there is a little town called Roscoe that's, actually this will go easier if I just put it up here. There's Roscoe, and then right above Roscoe is Rockland, New York, and then right above that is the tiny town of Agloe, New York. Agloe, New York is very famous to cartographers because it's a paper town. It's also known as a copyright trap. Map makers, because my map of New York and your map of New York are going to look very similar on account of the shape of New York, Often, map makers will insert fake places onto their maps in order to protect their copyright, because then, if my fake place shows up on your map, I can be well and truly sure that you have robbed me. Aglo is a Scrabbleization of the initials of the two guys who made this map, Ernest G. Alpers and Otto Lindbergh, and they released this map in 1937. Decades later, Rand McNally releases a map with Aglo, New York on it, at the same exact intersection of two dirt roads in the middle of nowhere. Well, you can imagine the delight over at General Drafting. They immediately call Rand McNally, and they say, "We've caught you. We made Aglo, New York up. It is a fake place. It's a paper town. We're going to sue your pants off." And Rand McNally says, no. Aglo is real. Because people kept going to that intersection of two dirt roads in the middle of nowhere, expecting there to be a place called Aglo, someone built a place called Aglo, New York. It had a gas station, a general store, 2 houses at its peak. And this is, of course, a completely irresistible metaphor to a novelist, because we would all like to believe that the stuff that we write down on paper can change the actual world in which we're actually living, which is why my third book is called Paper Towns. But what interests me ultimately more than the medium in which this happened is the phenomenon itself. It's easy enough to say that the world shapes our maps of the world, right? Like the overall shape of the world is obviously going to affect our maps. But what I find a lot more interesting is the way that the manner in which we map the world changes the world. Because the world would truly be a different place if north were down. And the world would be a truly different place if Alaska and Russia weren't on opposite sides of the map. And the world would be a different place if we projected Europe to show it in its actual size. The world is changed by our maps of the world. The way that we choose to sort of our personal cartographic enterprise also shapes the map of our lives, and that in turn shapes our lives. I believe that what we map changes the life we lead. And I don't mean that in some like secret-y Oprah's Angels network, like you can think your way out of cancer sense. But I do believe that while maps don't show you where you will go in your life, they show you where you might go. You very rarely go to a place that isn't on your personal map.
One of the things that I was able to do in my design work is I could actually test run a piece of equipment in my mind, just like a virtual reality computer system. And this is an aerial view of a recreation of one of my projects that was used in the movie. That was like just so super cool. And there were a lot of kind of Asperger types and autism types working out there on the movie set too. But one of the things that really worries me is where's the younger version of those kids going today? They're not ending up in Silicon Valley where they belong.
At that end of the spectrum, where kids are able to begin to work and to become very involved in the things that they may be most passionate about, we have lots of hope, and we should be particularly positive. There is something about the way the brain is wired in children with autism that's different. And so at one point we used to think that these repetitive movements or the fascination with repetitive activities was a way of sort of channeling the chaos and making perceptions a little more tolerable because they are so chaotic for some people. It's not clear, actually, that that's entirely the case. There is something about the way these kids process the world that's different and can be, as Amy was just saying, extraordinarily creative and interesting.
Penrose Hameroff orch-or, orchestrated objective reduction, is a theory of consciousness based on quantum computations in microtubules. OR is Penrose's mechanism for self-collapse of the wave function. Orch is orchestration, which is my biological contribution to how this could happen and both be isolated and interact with the environment. So I'm going to briefly talk about a little bit about memory, some recent evidence about memory that Travis Craddock, Jack Tusinski, and I have done. In long-term potentiation, calcium comes in through the cell and activates CAMK2, calcium calmodulin kinase 2, which then rapidly distributes throughout dendrites and actually throughout many parts of the neuron or groups of neurons quite rapidly. And they're associated with microtubules. And they phosphorylate something in the cell which stores memory. Now, synapses are credited with memory, but the proteins of synapses are very transient, last hours to days, but memories can last a lifetime. So the question is where memories may be stored. And the CAMK2 is a very interesting molecule. It's a snowflake-shaped holoenzyme, which, when activated and phosphorylated by calcium coming in, transforms into this sort of insect-like nanopoodle, we like to call it, with 6 legs extending up and 6 legs extending down, each of which can phosphorylate a substrate. So the question is, what's the target for phosphorylation, which memory can be stored? Well, being microtubule fanatics, we thought it might have something to do with microtubules. And so here's a microtubule in 2 different scales. The microtubule, then the close-up of the tubulin subunit, showing the phosphorylation sites on tubulin with the C-terminal tails. And so the question is, how does the CAMK2 relate to this microtubule? And it turns out it matches perfectly. Here's the CAMK2 here with the top set of legs taken off, and you overlying the A lattice and B lattice, and Anirban talked about the different lattices. You can see here that they match up perfectly. So each of these legs can either phosphorylate a substrate or not. Therefore, it conveys a bit of information. And 6 bits on an ordered array of bits is a byte. So basically the idea is that each of these can convey a byte of information onto the tubulin lattice. And sure enough, with a little flexibility in these extenders, the nanopoodle can deposit information on the microtubule and perhaps march along it by hydrophobic interactions and can convey synaptic information to the microtubule. And here are mechanisms at the level of individual amino acids. Now I want to talk a little bit about topological qubits. Anirban gave some very elegant results, and I'm not sure my understanding is up to, from the quantum computing point of view. So I'll just tell you my interpretation of topological qubits, which may not match, which may not be right or match what he said. But historically, how this got started for microtubules was that Roger Penrose invited me and Jack Jasinski to the 1998 meeting at the Royal Society in London of Quantum Information to talk about microtubules. And actually, Jack was the skeptic, and I was the proponent. And since he's kind of come over to our side, thank you. But afterwards, there was John Preskill gave a talk on topological quantum error correction and topological qubits, and relating to Kitaev's idea and so forth. And as I understand it, the idea is that if you have some kind of lattice and the information can flow through one pathway or another pathway, then the pathway itself can be the bit. So in the case of microtubules, they have this Fibonacci geometry. So you can follow this pathway, or you can follow this pathway, or this pathway, or this pathway, or a number of other pathways. And if each tubulin was a bit, if each one of these guys was a superposition and represented a quantum bit or qubit, then it would be susceptible to decoherence. Decoherence of any one subunit would mess up the whole quantum computation. However, if you make the pathway the bit or the qubit, then if one of these guys gets knocked out of whack, it's going to get pulled back in by its neighbors, and so it becomes resistant to decoherence. That's the whole point about topological qubits and also topological quantum error correction, which is a very similar idea. And these spiral pathways follow the Fibonacci geometry, 3, 5, 8, 13, 21.
Say you're in math class and your teacher's talking about, well, who knows what your teacher's talking about. Probably a good time to start doodling, and you're feeling spirally today, so yeah. Oh, and because of overcrowding in your school, your math class is taking place in greenhouse number 3, plants. Anyway, you've decided there's 3 basic types of spirals. There's the kind where as you spiral out you keep the same distance, or you could start big but make it tighter and tighter as you go around, in which case the spiral ends. Or you could start tight but make the spiral bigger as you go out. The first kind is good if you really want to fill up a page with lines, or if you want to draw curled up snakes. You can start with a wonky shape to spiral around, but you've noticed that as you spiral out it gets rounder and rounder. Probably something to do with how the ratio between 2 different numbers approaches one as you repeatedly add the same number to both, but you can bring the wonk back by exaggerating the bumps and it gets all optical illusion-y. Anyway, you're not sure what the second kind of spiral is good for, but I guess it's a good way to draw snuggled up slug cats, which are a species you've invented just to keep this kind of spiral from feeling useless. This third spiral, however, is good for all sorts of things. You could draw a snail or a nautilus shell, an elephant with a curled up trunk, the horns of a sheep, a fern frond, a cochlea, and an inner ear diagram, an ear itself. Those other spirals can't help but be jealous of this clearly superior kind of spiral. Better draw more slug cats. Here's one way to draw a really perfect spiral. Start with one square and draw another next to it that is the same height. Make the next square fit next to both together, that is, each side is length 2. The next square has length 3. The entire outside shape will always be a rectangle. Keep spiraling around, adding bigger and bigger squares. This one has side length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and now 21. Once you do that, you can add a curve going through each square, arcing from one corner to the opposite corner. Resist the urge to zip quickly across the diagonal if you want a nice smooth spiral. Have you ever looked at the spirally pattern on a pine cone and thought, hey, sure are spirals on this pine cone? I don't know why there's pine cones in your greenhouse. Maybe the greenhouse is in a forest. Anyway, there's spirals, and there's not just one either. There's 1, 2, 3, 4, 5, 6, 7, 8 going this way, or you could look at the spirals going the other way, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look familiar? 8 and 13 are both numbers in the Fibonacci series. That's the one where you start by adding 1 and 1 to get 2, then 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. Some people think that instead of starting with 1 plus 1, you should start with 0 and 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and it continues on the same way as starting with 1 and 1. Or I guess you could start with 1 plus 0, and that would work too. Or why not go back one more to -1, and so on. Anyway, if you're into the Fibonacci series, you probably have a bunch memorized. I mean, you've got to know 1, 1, 2, 3, 5. Finish off the single digits with 8, and ooh, 13, how spooky. And once you're memorizing double digits, you might as well know 21, 34, 55, 89, so that whenever someone turns a Fibonacci number, you can say, happy Fib birthday. And then, isn't it interesting that 144, 233, 377, but 610 breaks that pattern, so you'd better know that one too. And oh my goodness, 987 is a neat number, and well, you see how these things get out of hand. Anyway, 'tis the season for decorative scented pine cones, and if you're putting glitter glue spirals on your pine cones during math class, you might notice that the number of spirals are 5 and 8, or 3 and 5, or 3 and 5 again, 5 and 8. This one was 8 and 13, and one Fibonacci pine cone is one thing, but all of them? What is up with that? This pine cone has this wumpy, weird part. Maybe that messes it up. Let's count the top. 5 and 8. Now let's check out the bottom. 8 and 13. If you wanted to draw a mathematically realistic pine cone, you might start by drawing 5 spirals one way and 8 going the other. I'm going to mark out starting and ending points for my spirals first as a guide, and then draw the arms, 8 one way and 5 the other. Now I can fill in the little pine coney things. So there's Fibonacci numbers in pine cones, but are there Fibonacci numbers in other things that start with pine? Let's count the spirals on this thing. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The leaves are hard to keep track of, but they're in spirals too, of Fibonacci numbers. What if we looked at these really tight spirals going almost straight up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. A Fibonacci number. Can we find a third spiral on this pine cone? Sure, go down like this, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. But that's only a couple examples. How about this thing I found on the side of the road? I don't know what it is. It probably starts with pine, though. 5 and 8. Let's see how far the conspiracy goes. What else has spirals in it? This artichoke is 5 and 8. So does this artichoke-looking flower thing. And this cactus fruit does too. Here's an orange cauliflower with 5 and 8, and a green one with 5 and 8. I mean, 5 and 8. It's actually 5 and 8. Maybe plants just like these numbers, though. Doesn't mean it has anything to do with Fibonacci, does it? So let's go for some higher numbers. We're going to need some flowers. I think this is a flower. It's got 13 and 21. These daisies are hard to count, but they have 21 and 34. Now let's bring in the big guns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 20, 24, 42, 53, 54, 55. I promise this is a random flower and I didn't pick it out specially to trick you into thinking there's Fibonacci numbers and things, but you should really count for yourself next time you see something spirally. There's even Fibonacci numbers in how the leaves are arranged on this stalk, or this one, or the Brussels sprouts on this stalk are a beautiful, delicious 3 and 5. Fibonacci is even in the arrangement of the petals on this rose, and sunflowers have shown Fibonacci numbers as high as 144. It seems pretty cosmic and wondrous, but the cool thing about the Fibonacci series and spiral is not that it's this big, complicated, mystical, magical supermath thing beyond the comprehension of our puny human minds that shows up mysteriously everywhere. We'll find that these numbers aren't weird at all. In fact, it would be weird if they weren't there. The cool thing about it is that these incredibly intricate patterns can result from utterly simple beginnings.
So in the human body plan, we have about 500 terminally differentiated cell types. There is a different mitochondrion specialized for every one of those cells. Okay, so they are adapted to meet the metabolic demands of each individual cell type. So if I had a pointer, I'd point out some of these different mitochondria here that come from on the upper left. Oh yeah, this is another thing. When we crack open cells and pull out mitochondria, what happens? Mitochondria normally are present in filaments, but when we snap them apart, pull them out of the cell, they snap into like little spheres according to soap bubble physics. So you lose their normal configuration when you crack open the cell as well. And what we've learned is that actually dramatically influences their function. Their function when they're in long filaments and networks within a cell are very different from when they're just in little balls. And we are always measuring just the function in little balls.
It's reductionism. It's that all life's just DNA programs and code, and can therefore be modeled in this kind of programming code manner.
So when certain cells differentiate to become neurons or retinal cells or pancreatic beta islet cells, they give up certain metabolic reactions so that they can do others better.
Then there's the assumption that artificial intelligence used to be dismissed, but these criticisms have been overtaken. I don't think that's true of the most interesting ones, like Roger Penrose's criticism of artificial intelligence. Here's a quantum physicist who says that if the brain is a computer, then it's not going to be a regular digital computer, it's going to be a quantum computer. And all this kind of digital computing doesn't really take into account quantum logic. The computers of the future, people are already working on quantum computers, and if quantum computers are made, and if they work, they'll work in a completely different way. I think your case would be much stronger if there were quantum computers.
So, now the problem, as far as anyone knows, was sort of first asked actually in 1956 in a letter that Kurt Gödel, the incompleteness guy, wrote to John von Neumann. Von Neumann at the time was dying of cancer in the hospital, and Gödel wrote this letter that said, "My dear von Neumann, I hear that you're getting better," which he wasn't, "but since you are, let me take the liberty of troubling you with a mathematical problem." And he then asked a problem that today we would immediately recognize as the P versus NP problem. Okay, he asks sort of, is there a general decision procedure that, given a mathematical question, will tell you whether it has a proof of n symbols or less? Okay, we knew from the great work of Gödel and Alan Turing in the 1930s that there can be no general decision procedure for mathematics. It tells you whether a statement has a proof or not. What about just a proof of n symbols or less? Okay, this is clearly a finite problem. In principle, you could just enumerate every possible proof one after the other and see if any of them worked. Okay, but, is there actually an efficient procedure? One that takes a number of steps that grows like n or like n squared, let's say, instead of like 2 to the n power. Okay, that grows algebraically instead of geometrically. Okay? And he says, if such a procedure existed, it would have consequences of the greatest magnitude. It would mean that the mental effort of the mathematician could be completely replaced by machine. And then he has a little asterisk and he says, apart from the postulation of axioms. Okay, so basically, here's what he's saying. So P versus NP is recognized as one of the greatest unsolved problems in mathematics, right? It's one of these 7 Clay problems alongside the Riemann hypothesis, the Poincare conjecture, which was solved almost a decade ago by Grisha Perelman, and several others. Okay, but in my opinion, P versus NP is actually manifestly the most important of the 7 problems. It's the greatest mathematical problem. And the argument for this is simply that if P were equal to NP, then probably you could not only solve that one problem, but also the other 6. Okay? Because you would simply program your computer to find the proofs for you. Okay, so this is a math problem, but it's also a problem about the nature of mathematical reasoning itself. Okay, so this is the P versus NP problem, why it's important. Okay, but you know, people have been asking this question for you know, more than 40 years now. I should tell you that you know, I think a lot of, you know, there's been a lot of progress. You know, there have been some breakthroughs proving things that are, you know, nowhere near P not equal to NP, but some sort of baby results. People are, you know, we know more than people did in the 70s, right? But you know, it's a tremendously difficult problem. Now, because of this blog that I write, I get solutions to this problem in my inbox, I would say every other week or so. Either that they're equal or that they're not equal. You know, in a couple cases they were accompanied by death threats if I didn't publish them. Okay, but the most recent serious attempt, some of you may have seen, was this summer. A guy named Vinay Dialalkar, who had actually what looked like a serious attempt at a proof, and then, you know, I was on vacation at the time. People were flooding me with emails. Is this correct or not? I could tell that it almost certainly wasn't correct, but I didn't know where a mistake was, so I said, look, you know, if he gets this $1 million prize, so I'll supplement it by $200,000, okay? And I thought that couldn't possibly be controversial. I was wrong about that, but in any case, the long story short is that I didn't have to give up my house. The problem is still open, is still extremely difficult, and you know, we hope that someday mathematics will have advanced to the point where we can tackle questions like this one. But in the meantime, you know, we can continue to think about P versus NP as a purely mathematical question, which it is, and that's great. Okay, but there's also a different perspective that we can take on it. Okay, and that's that there's actually a very important presupposition that sort of underlies the P versus NP question, or, you know, why do we ask the question in this particular way and not some other way? Okay, and that presupposition is called the extended Church-Turing thesis. Basically, this is the thesis that this theoretical model of a computer that we've been working with since the 1930s, which is called the Turing machine, is really the right model for what can be computed in a reasonable amount of time in the physical universe. Okay, so you know, there was an original Church-Turing thesis which said that the Turing machine captures if something can be computed in any amount of time in the physical world, then it can also be computed by a Turing machine. Okay? And that, it's fair to say, I think that there's been no serious challenge to that thesis. Not even quantum computing does anything to challenge that. Okay, but then there's the extended version, which says that if something can be efficiently computed in polynomial time in the physical world, then it can also be computed in polynomial time by a Turing machine, either a deterministic or maybe a probabilistic one. Okay, and that thesis has always been on shakier ground. And in fact, you know, you're going to see shortly that quantum computing poses a serious challenge to it.
But you yourself are saying this is coming, and I agree.
I'm saying that if it comes, it will be quite different from anything that you've talked about.
I think it will answer your first objection, because the quantum computers will incorporate fuzzy logic, which will exemplify all these warm, fuzzy human qualities that you found so appealing.
No, I don't think it'll deal with the essential problem that this purely cognitive-based way of modeling intelligence is either an adequate model of human intelligence or of biological intelligence or of life. Or of a system that could actually achieve the power to control our existence. I think it's a very limited part of what a mind does. And I think, therefore, that the premises on which this whole, Ralph called it a fantasy, a paranoid fantasy, the premises on which this is based...
That helped.
I think the premises on which this are based are old paradigm premises, and they're ones that I think there are many reasons for thinking we need to go beyond. I think the Internet has achieved a great deal, but I just can't see that it's an adequate vehicle.
Imagine a computer network that is fed random information and spits that same random information out. Every time you read out a message, you won't be sure what you'll get. Even more confusing, to use this network, you aren't allowed to see the random messages you put into it. It might sound a bit pointless, but researchers see potential in just such a network, based on the principles of quantum mechanics. Stefan Ritter at the Max Planck Institute for Quantum Optics in Germany has developed a technique that could lead to quantum networking, and Jeff Brumfield called him on a regular phone network.
There are many applications for transmitting a quantum state, and one is that with a quantum computer, you'd build on these strange quantum states, and if you want distributed quantum computing, say, like one does with cloud computing all the time, then we might want to exchange quantum states. And exchanging classical states is just not enough. Another application is quantum cryptography. So quantum cryptography, also building on these superposition states and entanglement, allows you to exchange a secret key with, if you do everything correctly, absolute security. And to do so, you also need to exchange quantum states. But you can't copy a quantum state, and also if you measure it, you alter the quantum state. So say you have a quantum state and you don't know what it is and you want to send it to me, then you don't have the opportunity of measuring it and sending it to me via a classical channel. You have to send it by some means like we do.
You can't even read the information before you send it. This is just sounding like the weirdest network ever to me.
Well, I mean, if you prepare a quantum state and you know that state, then you could, of course, just call me and tell me, well, I have this quantum state, try to prepare it at your place, and then I have the same quantum state. But sometimes, say, some person in the future would do a quantum computation, and there's a quantum state that comes out as a result. Then if you measure that, you won't get the full quantum state, because, as you said, if you have these superpositions being 0 and 1 at the same time, then the measurement process will project the state onto either 0 or 1, and thereby destroy the quantum state that you initially had. So then measuring and sending is not an alternative in the quantum world.
So basically, this is a network that allows you to send multiple possible answers that you don't know before you send them.
That's correct, yes.
And so let's talk a little about how you actually did it, because it wasn't even clear that this could be done.
That's right. So when we talk about a quantum network, what we mean is that you have network nodes, and between those you transmit the information. So as a transmitter, single photons are ideally suited because they fly at the speed of light, and you can make them interact rather weakly with the environment, so they're great for transmitting information from A to B. But then they are not stationary, and so they are not suitable as network nodes. And so what we take as network nodes are single atoms. And now the task is to transfer quantum information from the stationary node, so from the single atom, onto a single photon, then transmit it via your quantum channel, which typically is an optical fiber, to the other network node, and there to convert it from the photon onto the other single atom that's at this second node, and then have it stored there.
You can do some really crazy things with this network. You're able to tweak one part of the network to actually manipulate a physically separated part of it instantly. Is that right?
That's right. So what we've done in the second experiment is that we've entangled the two network nodes. So what we do is we produce a single photon from one of the network nodes, and in such a way that the polarization of this photon is entangled with the atom or the internal atomic state. And then we send again the photon over and store it coherently in the second network node. And we achieve this in such a way that the two single atoms, even though they've never seen each other, they are entangled.
And it would work instantly between...
That's correct.
That's a really weird thing.
Yes.
I assume this network can't communicate faster than the speed of light.
No, it can't, because you always need a classical communication channel.
how sure are we of this thesis? What are the challenges to it that have been put forward over the years? All right, so let's start with sort of the challenges that have been to this extended charge Turing thesis that computer scientists have sort of kicked around since the 1970s or so. So my personal favorite is that you could violate the extended charge Turing thesis and exceed the computational capacity of a Turing machine using a tub of soapy water. Okay, so how exactly would that work? Okay, so what you would do is you would take two glass plates and you would put pegs between them, in whatever configuration you wanted. Okay, and then you would take this thing and dump it, just hold it into a tub of soapy water, and you would take it out, and what you see is some soap bubbles which will form. Okay, and in general, bubbles like to reach a minimum energy configuration, and this more or less corresponds to minimizing the total length of bubbles, connecting the pegs together. Okay, and so in other words, if the bubbles really relax into their lowest energy state, then they ought to relax into what computer scientists and mathematicians know as the minimum Steiner tree. Okay, so this is the minimum total length of line segments connecting a bunch of points in the Euclidean plane, where those segments could also meet at intermediate points. Okay, so I've shown an example here. Now, the interesting thing is that this minimum Steiner tree problem is known to be NP-hard. Okay, and yet nature seems to solve it. You just, dip these pegs in the soapy water, right, and just let nature find the lowest energy state. Okay, so there was a discussion of this on the internet some years ago, and people made the point that I think was important here, which is that, well, systems in nature, can be amazing in trying to find solutions to optimization problems, but we also know that they can get stuck in local minima. Okay, so for example, if you had a rock on some crevice on a mountainside, it could reach a lower state of potential energy by rolling up first and then rolling down, and yet it's rarely observed to do that. Okay, so why not? Why shouldn't things be the same with these pegs, right? There might be some, completely optimal way to connect the pegs together. But if you've, put together a system of pegs such that the minimum Steiner tree connecting them together encodes a proof of the Riemann hypothesis, which in principle one can do. That's what NP completeness tells you, right? Then, why on earth would you expect nature to find that optimal configuration instead of one of the thousands and thousands of suboptimal ones that it could happily, get to? Okay, and then, some other people were arguing with this, and they said, well, this is just really this academic computer science party line. I bet none of you who are saying this ever actually went and did the experiment. So this was my only foray in my life into experimental physics. So I went to the hardware store, did it. It looks it's very cool with like 5 or 6 pegs. You should actually try it. It's nice. But then, you start adding more pegs, 7 pegs, 8 pegs, and indeed you can find that sometimes it does not reach an optimal configuration, okay? Sometimes you even have cycles, which we know actually can't be optimal. It has to be a tree. Okay, so, all right, so much for this. There are other approaches that people have put forward for trying to solve NP-complete problems in nature. One is that if you look at proteins, proteins are really amazing. They somehow fold very quickly into some low energy state. And if you formalize this problem in the right way, you can actually show that the problem of finding the minimum energy folding configuration for a protein is, again, NP complete. Okay, and yet again, the proteins do it. Okay, but again, the resolution is that proteins are actually specifically evolved over billions of years so that the minimum energy configuration will be easy to find. Okay, so that it will be an easy computational problem. If you designed a protein where it's a hard computational problem, then there's sort of no very good reason to expect it to reach its minimum energy state. Okay, and in fact, even in nature, we do sometimes see proteins that fold into the quote-unquote wrong configuration. So these are like prions, for example, the agent of mad cow disease. Okay? People have also proposed using DNA computers, which would be this massively parallel, way of trying to solve these hard optimization problems. But from our perspective, DNA computer is really sort of a very, very parallel classical computer. So in other words, the amount of DNA that you need to put in your test tube will increase exponentially with the size of the problem that you're trying to solve until you have to convert the whole Earth into DNA or something. Okay, so this again is not a scalable solution. All right, but what about quantum computing? Okay, you knew it was coming at some point. Okay, so this is was an amazing new idea in I guess both in physics and in the theory of computation that got widespread attention starting around 17 years ago. And what's the idea? Well, the idea is to exploit sort of quantum mechanics, which has been our fundamental framework for almost all of physics for almost 90 years now. You hear a lot of things about quantum mechanics, that it's about light being both a particle and a wave, that it's about the hydrogen atom having these discrete energy levels, that it's about randomness, this and that. From a computer scientist perspective, quantum mechanics is simply a generalization of probability theory, okay, where instead of probabilities, which are non-negative real numbers, we replace them by these numbers called amplitudes, which can be complex numbers. And so in particular, they can have minus signs in them. Okay? And for whatever reason, nature seems to prefer things that way.
And these spiral pathways follow the Fibonacci geometry, 3, 5, 8, 13, 21. And this was one of the things that got Roger very interested in microtubules, because he's a geometer at heart, and that's one of the things that captivated him. And honor bonds now shown something like this in microtubules actually occur. So it's also might be something like the Aharonov-Bohm effect, where you have opposite pathways or alternative pathways, each of which can be a bit or qubit. And if you look at the multiple nonpolar hydrophobic pockets and line them up with a little imagination, you could see how their states of each one of them could influence conductivity of ballistic conductance or quantum coherence moving through the lattice along particular helical pathways in the microtubule.
Once all of the quantum phenomena that people talk about, like entanglement and interference, and so on, they're all logical consequences of this one change that you make to foundations of probability. Okay, so contrary to its reputation, quantum mechanics is actually unbelievably simple once you take the physics out. Okay. Okay, so in particular, this perspective lets us easily talk about what is the idea behind quantum computing. So in the 1980s, Richard Feynman and David Deutsch and several others noticed something very interesting, that if you have a quantum system with, let's say, n particles, then in order to describe the state that system is in at a given time, you seem to need not just n numbers or 2n or 3n, as in classical physics, but actually something like 2 to the n power, okay? Because you need to give one of these amplitudes, these, sort of minus sign probability things, to every possible configuration that all n of the particles could be in. Okay, and the number of such configurations increases exponentially with the number of particles. Okay, now this is a mind-boggling fact about physical reality. I mean, it took a while for this to really sink in, but I think in retrospect, this is really arguably the central or one of the central facts about quantum mechanics. And in particular, what it's a huge practical problem for people who try to simulate quantum physics on classical computers. It means you have an exponential slowdown. Okay, what Feynman, and Deutsch and the others noticed is, hey, maybe you could turn that around. Why not build your computer out of quantum mechanical elements? And then, you won't have that exponential slowdown problem. Okay, but then what you've really built is a fundamentally new kind of computer, one that could, in principle, solve some problems exponentially faster than any of the computers that we use today. So then you could ask, what else is it good for, besides, just the task of simulating quantum physics, which is sort of what it could do in its sleep. Okay. So yeah, I like to describe quantum computing as the power of 2 to the n complex numbers working for you. Okay, now as I guess is well known, actually building a scalable quantum computer turns out to be damn hard. And the basic reason is that once a quantum computer state is measured, then it reverts to being classical. Okay, you sort of, a quantum computer is in what's called this superposition with all of these different amplitudes for all the different possible states that it could be in. Okay, but once you measure it, you force it to make up its mind. Okay, and then it's just in one state. And you don't get to measure twice. Once you measure, you get an answer out, then it's gone. Okay, so and this applies not just for measurements that you would do, but for measurements that are implicitly performed by any stray particle that may happen to pass through your system. Okay, and so what this means is that to build a scalable quantum computer, you would have to keep it extremely well isolated from the rest of the world, but at the same time be able to go in and actually do the computation. Okay, so it's those twin requirements that are sort of the reason why we don't have scalable quantum computers yet. Okay, what's been done after sort of a decade of work and sort of more than $1 billion spent by research groups all over the world is that a quantum computer has, with high probability, shown that 15 equals 3 times 5. Okay, 21 might be next, but scaling it up is extremely hard because of this decoherence problem. Okay, but on the other hand, no one has been able to articulate any clear reason why it should not be possible in principle. Okay, some computer scientists will tell you that it must not be possible because if it were possible, then you could, quickly factor huge numbers and solve these hard problems. That's sort of a circular argument. Okay, but so I think that we're really in the situation maybe of Charles Babbage in the 1830s, right? We have the theory, it ought to work, but in his case, it took more than a century for the transistor to be, the vacuum tube or the transistor to be invented, and for the technology to catch up with the theory.
In other words, you'll say, gee, I wonder what they're serving at so-and-so's restaurant tonight, and the answer will be hanging there in space, because you will have automatically accessed the internet, been to their website, looked at the menu, and returned with the data. Mm-hmm. In other words, we are going to create, I think, a collective. What the internet is a nervous system. Mm-hmm. It's the collective mind of humanity being hardwired as an artifact that completely encloses the entire planet in a thought.
So, conclusions. The objections to orch-or by McCamish et al. And Reimers et al. Are invalid, as far as I can tell. They didn't lay a glove on us, as far as I can tell. Maybe I missed something, but they whiffed. There's nothing in there that's threatening in any way. Of course, I'm biased, but So orch-or remains viable, and finally, it is far better to be criticized than ignored. Thank you very much.
And I would like to say something that concerning schizophrenia, which somehow is connected with your work. A physician in our country measured immunoreaction by some special antigen and found that in illnesses that have disturbed somehow mitochondria function, there is special reaction. And the reaction is the same in cancer, for instance, in heart failures, in schizophrenia, and in all these cases, very likely, also in schizophrenia, is disturbed function of mitochondria. Therefore, somehow that system that supply energy to oscillating system in the cells, which belong to biological activity. Thank you.
Okay, thank you. Any more questions?
Let me just say that Jerry's work is a huge help to us. Number one, showing the 8 megahertz coherence, and also showing where the energy comes for the excitations from mitochondria without requiring GTP, because that was a critical issue. Is what's driving. I mean, Froelich said the heat bath, but that's a little bit vague. But showing that it's coming from mitochondria is very, very helpful. And I think a great discovery.
Thanks. It's always nice to hear a tour de force, and that was really well done. And I had a question. If you think, I like to think of a cell as a 4-bit microprocessor or 8-bit, because it's hard to do much more unless you quantum. And if you're a cell and somehow something signals you that you have to now be differentiated to a certain task, there's a complex set of subroutines you have to know somehow how to extract if you're going to do liver work, for example.
I think, we've made this point, but it's worth sort of stating directly that many individuals with autism have great talents and talents that may be the result of the same thing that is causing their disabilities, but sort of this intense attention to detail and enjoyment of repetitive activities, and sometimes just seeing the world in a very different way from the way that normal more conventionally brained people see it. So that the idea that they could be employed is not crazy, but in fact they could provide some great benefit to society if we were able to better absorb them into the workplace.
So for a long time, I wondered, well, if I'm going to discover I have to do a subroutine, I need a bit to store to know that I need something that works with the rest of the complex informatics, which what you've shown with the CAMK2 sounds like the perfect kind of a cellular memory.
Yeah.
So that's I remember in 1999, you and Jack and Porter published a paper that also suggested, with some fascinating diagrams, that the microtubules of a cell can form electrical circuits also. And I just am thinking, in addition to all the quantum discovery, if you're not showing us how there is almost a perfect microprocessor memory state in cells.
Yeah, well, thank you. Yeah, as I said, I worked for 20 years on the idea of microtubules as classical computers. I didn't even think about quantum. And I only went to the quantum business when somebody stymied me with a question, okay, wise guy, how's that going to explain, how we have feelings and feel joy and redness and, the heart, what's now known as the heart problem in consciousness research. And at that time, I read Roger's book, The Emperor's New Mind, which was beautiful for many reasons. And he had a mechanism, but he didn't have a structure. I had a structure and didn't have a mechanism. So I wrote to him, and he immediately got it. He immediately saw that microtubules could be, what he needed, and we teamed up. And we're kind of an odd couple. We're very different in almost every way. But he's a wonderful guy, and he's still very interested. He's gone off to worry about the origin of the universe and stuff like that. But he's still very keen on this stuff, and we stay in touch. And he'll be dabbling back into this.
My son loves elevators, and he just loves elevators. And I don't know what the scientific reason behind it is, but I sort of suspect that part of it is he's curious about how they work. I think his mind kind of works that way. You want to try to figure things out and understand them. And I think he's very visual and also sort of thinks in pictures, and that kind of goes along with the same thought, that just kind of wanting to understand what's going on to make this work that I can't actually see. But it's a phenomenon.
I'm Susan Page, and you're listening to The Diane Rehm Show. We're taking your calls. Our phone system's back. Let's go to Keith. He's calling us from Little Rock. Hi, Keith.
Hi. How are you today?
Good, thanks.
I was calling in. I'm shocked you put me on the air, but the The thing I was thinking about as I was listening to all these women speak is these are experiences that you described that are autism or within the range of autism that I would characterize as being typical of what I would describe as my lineage. Men older than me in my previous generations, my son included, we have these behaviors that you describe as autism, and we might describe several of you as just crazy. But the more precise thing to describe as I'm listening to you all describe how you're dealing with your children is that generally that's not how I deal with my son. There are certain behaviors that I nip in the bud before they get out of hand, and there are other behaviors that I would take the time to guide him through, perceive other people's activities and how they behave, demonstrate how they're feeling to other people, and communicate that in a rational way that they will understand. I don't know, it's child rearing from my point of view. From your point of view, it appears to be something much more serious.
Visual thinking was a tremendous asset in my work designing cattle handling facilities. And I've worked really hard on improving how cattle are treated at the slaughter plant. I'm not going to go into any gucky slaughter slides. I've got that stuff up on YouTube if you want to look at it. But one of the things that I was able to do in my design work is I could actually test run a piece of equipment in my mind, just like a virtual reality computer system. And this is an aerial view of a recreation of one of my projects that was used in the movie. That was like just so super cool. And there were a lot of kind of Asperger types and autism types working out there on the movie set too. But one of the things that really worries me is where's the younger version of those kids going today? They're not ending up in Silicon Valley where they belong. Now, one of the things I learned very early on, because I wasn't that social, is I had to sell my work and not myself. And the way I sold livestock jobs is I showed off my drawings, I showed off pictures of things. Another thing that helped me as a little kid is, boy, in the 50s you were taught manners. You were taught you can't pull the merchandise off the shelves in the store and throw it around. Now, when kids get to be in 3rd or 4th grade, you might see that this kid's going to be a visual thinker, drawing in perspective. Now, I want to emphasize that not every autistic kid's going to be a visual thinker. Now, I had this brain scan done several years ago, and I used to joke around about having a gigantic internet trunk line going deep into my visual cortex. This is tensor imaging, and my great big internet trunk line is twice as big as the controls. The red lines there are me, and the blue lines are the sex and age-matched control. And there I got a gigantic one, and the control over there, the blue one, has got a really small one. And some of the research now is showing that people on the spectrum actually think with primary visual cortex. Now, the thing is, the visual thinker is just one kind of mind. You see, the autistic mind tends to be a specialist mind, good at one thing, bad at something else. And where I was bad was algebra. And I was never allowed to take geometry or trig. Gigantic mistake. I'm finding a lot of kids that need to skip algebra, go right to geometry and trig. Now, another kind of mind is the pattern thinker, more abstract. These are your engineers, your computer programmers. Now, this is pattern thinking. That praying mantis is made from a single sheet of paper. No scotch tape, no cuts, and there in the background is the pattern for folding it. Here are the types of thinking. Photorealistic visual thinkers like me. Pattern thinkers, music and math minds. Some of these oftentimes have problems with reading. You also will see these kind of problems with kids that are dyslexic. You'll see these different kinds of minds. And then there's a verbal mind. They know every fact about everything. Now, another thing is the sensory issues. I was really concerned about having to wear this gadget on my face. And I came in half an hour beforehand so I could have it put on and kind of get used to it. And they got it bent so it's not hitting my chin. But sensory is an issue. Some kids are bothered by fluorescent lights. Others have problems with sound sensitivity. You know, it's going to be variable. Now, visual thinking gave me a whole lot of insight into the animal mind. Because think about it, an animal's a sensory-based thinker, not verbal. Thinks in pictures, thinks in sounds, thinks in smells. Think about how much information there is there on the local fire hydrant. He knows who's been there, when they were there, are they friend or foe? Is there anybody he can go mate with? There's a ton of information on that fire hydrant. It's all very detailed information. And looking at these kind of details gave me a lot of insight into animals. Now, the animal mind, and also my mind, puts sensory-based information into categories. Man on a horse and a man on the ground, that is viewed as two totally different things. You can have a horse that's been abused by a rider. They'll be absolutely fine with the veterinarian and with the horseshoer, but you can't ride him. You have another horse where maybe the horseshoer beat him up, and he'll be terrible for anything on the ground with the veterinarian, but a person can ride him. Cattle are the same way. Man on a horse, a man on foot, they're two different things. You see, it's a different picture. So I want you to think about just how specific this is. Now, this ability to put information into categories, I find a lot of people are not very good at this. Like when I'm out troubleshooting with equipment or problems with something in a plant, they don't seem to be able to figure out, do I have a training people issue or do I have something wrong with the equipment? In other words, categorize equipment problem from a people problem. I find a lot of people have difficulty doing that. Now, let's say I figure out, is an equipment problem, is it a minor problem with something simple I can fix, or is the whole design of the system wrong? People have a hard time figuring that out. Let's just look at something like, solving problems with, making airlines safer. Yeah, I'm a million-mile flyer. I do lots and lots of flying. And, like if I was at the FFA, what would I be doing a lot of direct observation of? It would be their airplane tails. 5 fatal wrecks in the last 20 years. Tail either came off or steering stuff inside the tail broke in some way. It's tails, pure and simple. And when the pilots walk around the plane, guess what? They can't see that stuff inside the tail. Now as I think about that, I'm pulling up all of that, specific information. It's specific. See, my thinking's bottom up. I take all the little pieces and I put the pieces together like a puzzle. Now here's a horse that was deathly afraid of black cowboy hats. He'd been abused by somebody with a black cowboy hat. White cowboy hats, that was absolutely fine. Now the thing is, the world is going to need all of the different kinds of minds to work together. We've got to work on developing all these different kinds of minds. And one of the things that's driving me really crazy as I travel around and I do autism meetings is I'm seeing a lot of smart, geeky, nerdy kids. And they just aren't very social. And nobody's working on developing their interest in something like science. And this brings up the whole thing of my science teacher. My science teacher is shown absolutely beautifully in the movie. I was a goofball student when I was in high school. I just didn't care at all about studying until I had Mr. Carlock's science class. He was now Dr. Carlock in the movie. And he got me challenged to figure out an optical illusion room. This brings up the whole thing of you got to show kids interesting stuff. One of the things that I think maybe TED ought to do is tell all the schools about all the great lectures that are on TED. And there's all kinds of great stuff on the internet to get these kids turned on. Because I'm seeing a lot of these geeky, nerdy kids, and the teachers out in the Midwest and other parts of the country, when you get away from these tech areas, they don't know what to do with these kids. And they're not going down the right path.
And maybe that's because, I've got many generations ahead of me that know what this looks like, and so, when we have a young son who behaves this way, nobody hesitates to know just what to do and move on.
Okay.
Have you found in your research any kind of generational things going on with this, where people have adapted within their own families how to handle this kind of situation?
Dr. Insel, what about that question and the issues that Keith raises?
Well, these kinds of questions, which come up often, reflect the sense that autism isn't really a serious issue, and that these are just kind of maybe cultural or sometimes family-based variations on a theme. The reality is that many of the kids who get this label are severely, severely disabled. These are children who will spend much of their life in institutions because they cannot be managed in a family. Many of them have self-injurious behavior. They will bite themselves. They will bang their heads until they bleed. And we're talking about a disorder which, in its more severe forms, is really profoundly disabling. And that's the piece of it that's also increasing. So there is every reason to take this very seriously.
I just want to start by saying it's really, truly an honor for me to be here speaking at MIT.
in the McGovern Institute. So today I'm going to talk about a subject that's been in the media a lot lately. You can't turn on the news and hear a report about autism and not hear them talk about autism prevalence. And how it's increased over the years. What we've seen in the recent literature is that autism affects 1 in 110 children in the United States today. These are numbers published by the CDC. That's about 1% of the children in this country. This also represents a 57% increase in just 4 years of data collection. You may remember it was 1 in 150 before it became 1 in 110, and that is quite an increase in a short amount of time. But if you look at the data over 20 years of research publications, you actually see that autism prevalence has increased about 600% over 20 years. Again, these are the numbers published in the data. So about 20 years ago, it affected approximately 1 in 2,500 children. And again, today it's almost 1% of the population. But the question that we keep hearing is this a true rise in autism prevalence? Is it a true increase? Is it real? Over time, the change in diagnostic criteria for autism may have accounted for some of this increase. More specifically, it was the change in diagnosis from mental retardation to autism. So those two circles, I mean, this is taken a little bit out of context, but this picture appears in the report. And what it shows is that that overlap is the new autism cases actually resulting from that shift in diagnosis from mental retardation. And to look at it a little bit differently, what you can see here is that dark slope at the bottom is the expected change in autism prevalence over time due to that shift from mental retardation diagnosis to autism diagnosis. But what we saw here was that extremely large increase, so that gray area is the unexpected rise. And what the researchers from this investigation said was that about 26% of the increase in autism prevalence over that time period in California could be attributed to changing, broadening diagnostic criteria. Also coming from that research lab, what we saw was this idea, we've heard of this idea of maybe the rise in autism prevalence could be due to an increase in awareness of autism. And so what this paper demonstrated was that actually the proximity of a child living to a previously diagnosed child with autism actually increased that child's odds of being diagnosed themselves. So the theory here is that there's some kind of social mechanism taking place where there's this information diffusion or sharing of information within the community that's actually increasing a child's odds of being diagnosed with autism. And the investigators in this study estimated that 16% of that rise in autism prevalence could be attributed to this increased awareness or information diffusion within the community. Also, recently in the literature, we've heard about parental age. In general, parental age is a risk factor, and it can account for 11% of the increase. And parental age is a social component, right? Parents are choosing to have children later in life, so it's a social factor that's contributing to the increase. So just to review what I went over and what the research literature is showing us today is that, again, 26% of the increase in prevalence can be attributed to changes in diagnostic practices, that broadening criteria. 16% is due to greater awareness, and 11% is due to increase in parental age. Well, if you add that up, there's still about 50% of that increase in autism prevalence that is due to unknown factors. And so the question is, of course, well, what then is causing the increase in autism prevalence? Well, I wish it was a simple answer, but it's not. What we do know is that genetic susceptibility is likely involved in most cases, but then environmental factors also contribute to one's genetic susceptibility. And so what we know is that it's a complex interaction between genes and environment that are likely causing the rise in autism prevalence, but we need to identify those factors and understand exactly how they're contributing to the increase. Right now, the research suggests that about 1% of the global population has autism. However, there have been no studies conducted outside of these high-income developed countries that you can see in blue. We have no idea what the autism prevalence is in the developing world or even middle-income countries. So what does it all mean? Well, the autism crisis is real and growing. It's clear that regardless of whether or not autism prevalence has increased over time, 1% of the population is huge. There are more children today diagnosed with autism than ever before. And half of that increase that we saw over time is still unexplained. It's not caused by just better diagnosis, greater awareness, and social factors alone. There are genetic and environmental factors at play, and we need to understand those environmental factors.
So anyway, this is equigenetics. It's the study of genes that interact with environmental factors to lead to health and disease, and it's also the study of the environmental factors that interact with those genes. Now, so remember, so autism is kind of interesting. It's a moving target. If you go back and you plot the prevalence of autism dating back to 1990, and you can actually create a very nice exponential curve that goes through about 2005. With 18% growth per year. Okay, and then it starts falling off a bit. Okay, it starts falling off a bit from there. And so whether that means that we're kind of coming to a new equilibrium with our environment, or our environment is getting better, or what's happening, it's hard to say. But I've been told, and the next slide tells me this, from Autism Research Institute statistics, that 80% of the patients in the U.S. with autism spectrum disorders are under the age of 22. Okay. And if there anybody with better statistics than that, I asked them to come tell me to correct this, but this is the number that I have, and it's really kind of a shocking number. Okay. So what about the ecogenetics of mitochondrial DNA? So we evolved in Africa, and then our ancestors moved to the Middle East and Northern Europe and Asia, and crossed across the Bering Sea into the Americas. That all occurred tens of thousands of years ago. Okay, but our ancestors dwelled, like Moses will dwell in this land. We dwelled in a land. Our ancestors dwelled and became part of that land. A thread in the web of Chief Seattle and Chief Seattle's web. We learned to live with the nutrients in that environment. We learned to survive in the presence of the different microbial environment. In the cases where there was malaria, we developed resistance to malaria, and where tuberculosis was common, we developed resistance to tuberculosis. So, but what happened recently in the last 300 years is that we had this massive exodus from Northern Europe and from Africa to North America, and that brought in genes that had all co-evolved with their environments, for thousands of years earlier, into a new environment with new food sources and new viruses and bacteria and fungi to evolve with. And then, just as we get good at that, then we change the game again and start, with dramatic changes in the way that we do farming, in the way that we do. That we do our fishing, where concentrated animal farming operations, really are producing more and more of our food supply, and we're, using the powers of our brain to generate chemicals that we've, that our environmental history, our evolutionary history has never encountered before. Okay, and so we're having to readapt, okay, to this changing environment. Something that's really interesting that's put this in sharp relief for me is I do some collaboration with investigators in India, and India is dominated by this so-called M haplogroup of mitochondrial DNA. But before about 30 years ago, so in fact, as little as 20 years ago, when I first went to Bombay and just was sitting in the airport, fewer than 10% of the people were obese. Last year I went there and 30% of the people in the airport were obese. Now it turns out there's an epidemic of diabetes and cardiovascular disease in India. It's also happening in China. This is ongoing ecogenetic disease that is occurring because our environment is changing faster than our genes.
It had been speculated for many years that autism may be arising due to common genetic variations in the population. But in fact, what we found are several rare genetic variations, what we call copy number variations of DNA found in autistic individuals. The genes that we're finding to be involved, they all seem to work together in a connected pathway. So they encode proteins that are communicating and working together. We've identified about a half dozen genes, perhaps 100 more that may be involved.
Right around the time of the separation, or just before the time of separation of human, chimp, and gorilla, and we think shortly thereafter, there was a burst of duplication activity. So we have on the order of 3 times the number of megabases that were duplicated in this ancestral branch before the separation of chimp, gorilla, and human. This is interesting because if you look at texts that have been written for the last 20 years on this subject, most people have had this paradox: is why is there so few genetic changes over the millions of years that exist between humans and chimps and gorillas? And that is because most of the studies have been done really on single base pair changes and small insertion deletions. In terms of duplication, it appears we have an episodic burst of activity at a critical time, I would argue, during evolution. All right, so why do I show you all this? Well, this architecture, which is having all these duplications that are spread out, that are large and highly identical, creates problems for our genome. Because they're interspersed, everything that's bracketed by these duplications gets taken along for the ride. And now you have gametes that now have additional copies of genes A, B, and C, in addition to duplication, or have lost. So this creates a huge amount of genetic diversity in our population. And as a result, it also creates disease. And so years ago, we identified these 130 regions, and we systematically have shown by studies of human disease that about 45 of them are important in terms of causing sporadic mutations as well as inherited mutations as a result of this process. And these affect diseases such as autism, intellectual disability, developmental delay, epilepsy, and schizophrenia. So our genome is predisposed to these diseases because of our architecture, essentially, that has evolved.
Specifically, there are regions of sustained increased density that suggests there may have been a copy number difference between the Neanderthal genome that we have sampled and the reference human genome sequence.
These copy number polymorphisms, all of us carry about 10 of them. You can look at families where you have more than one autistic child, and where you think that the parents probably are carrying some genes which predispose the children to autism. You can also do it when 2 seemingly absolutely normal people have an autistic child.
So both of types of differences between humans and chimps, or humans and other non-human primates, and in fact most of the chimp-human differences aren't in proteins. They're going to be in these parts of the genome that used to be called junk DNA. Much of it is doing important things, and so slowly science is starting to understand this non-coding or dark matter part of our genome that used to be called junk. And one of the important things that the non-coding genome does is to control expression of nearby genes. So they're things called regulatory elements, and they can turn nearby genes on and off.
I just want to make a remark. You drew the analogy of the sense of smell, and what a poor sense of smell we have. It's a fascinating fact that although dogs, for example, have a much better sense of smell than we have, as you mentioned, we have the genes that would once enabled our ancestors to have as good a sense of smell as dogs. But the genes have mostly been turned off. And so we have vestiges, we have historical relics of those genes. And it's like your hard disk on your computer that's cluttered up with remains of old chapters you've written here and there and things that have now been cut off. Those genes have been turned off, but they're still there.
Isn't that the premise of X-Men?
I don't know.
They're human, but they have a genetically different genes are turned on and off within them, giving them special powers.
There is a population of different people in the general population, and as conditions change, these people will be seen to have adaptive advantages.
Being social beings, we need to recognize each other, and we do so in all sorts of ways, by the way people move, the way they dress, their voices, where they are, but in particular we are very good at recognizing each other's faces. Well, when I say we, I mean the majority of people. There are some people who are not so good at recognizing faces, and they are called face blind. They may see a face perfectly clearly, but it doesn't convey identity to them. And the technical term prosopagnosia, prosopon is the Greek for a face, and an agnosia is not recognizing. So the term prosopagnosia was introduced in 1944.
We may take facial recognition of our fellow humans for granted, but not all species have evolved such a specialized trait. Indeed, a duo of scientists at University of Michigan, Ann Arbor has zeroed in on two closely related species of paper wasp, one that possesses specialized face learning and another that doesn't. A series of experiments involving photos of wasp faces as well as general shapes and patterns indicates that while one species does recognize faces much more readily than the other, recognition of faces develops separately from other visual and cognitive abilities. The researchers also argue that the capability evolves independently across varying animal lineages. Lead author Michael Sheehan spoke with me about the work.
So the research shows that one particular species of paper wasp, Polistes fuscatus, which we have previously shown recognizes individuals, does so through a process which is relatively similar to how people recognize individuals using their faces.
Although one talks about face blind as if the face blind are a species apart from the face normal people, in fact there's a whole population, really a continuous population, with the 80% of the people in the middle, and the poor recognizers at one end, and the super recognizers at the other. The super recognizers are people who have indelible memories of faces, who will say, yeah, I remember you. You served us in that cafe in Naples 27 years ago.
Now, Nancy Minshew did another brain scan, and she found I was more interested in things than I was in looking at pictures of people. But the thing is, we need to have people in this world that are interested in things.
If you look at the birth of Apple, the Apple computer, we tend to associate Apple with Steve Jobs, who was this dazzling showman. But really, the person who invented the Apple computer was a different Steve. It was Steve Wozniak, who was a self-identified introvert. And he created this amazing thing by sitting by himself in a cubicle at Hewlett-Packard, where he was working at the time, late at night and early in the morning before anybody was at work. He would work by himself for months, and then he produced this amazing thing that he then shared with his friend Steve Jobs.
I'm not a big fan of Steve Jobs, personally.
What are you talking about?
I don't know. I just don't understand what the big deal was with that guy.
I don't get it. He's like Edison. I don't know. He invented all this stuff that everybody. What are you talking about?
But did he? Did he sit down and I'm going to invent the iPhone and just sat there soldering? Why, when he went to those nerd fests, didn't he have like a chorus of scientists behind him who helped him out too? He walked out like he was Tesla, like tapping into electricity.
Without Steve Jobs, none of it ever would have come to pass. So it was this combination of letting the solitary person go off by himself to think in his deep way, and then having a partnership between the two. And in fact, in companies, it's been found that the most effective teams are the ones that are a combination of introvert and extrovert. And the two types are really drawn to each other and really need each other.
So this one species of paper wasp has specialized face processing. They learn faces differently than they learn other types of images. But closely related species of paper wasp, for example, Polistes metricus, is unable to do that, and they don't recognize faces at all. In fact, have a very difficult time telling faces apart from each other. So what we show here is that specialized learning in wasps and people have evolved in parallel in these really different taxa. But in closely related wasp species, we find really different abilities for learning.
I think my mother was probably bad at recognizing faces. She was very shy. She was ill at ease with large numbers of people. My father was the opposite. My father was a sort of super recognizer. I think he recognized thousands of people, and he was highly sociable.
When we look at someone, most of us take it for granted that we either do or don't recognize them. Incredibly rapidly, our brain has analyzed their face and figured out if we've seen that particular combination of eyes, nose, and mouth before. And the invention of brain scanners allowed scientists to see that when we look at faces, a special part of our brain lights up. Aha, they thought, this area must just be for facial recognition, and they named it the fusiform face area. But new findings show that bird spotters and car fanatics use the same area when identifying species or makes. So, is this a face recognition area, or is it more widely useful?
You find that there are a number of areas in the brain that respond much more strongly to faces than they do to objects. This is one example here. This is the most well-known of these areas. It's called the FFA, the fusiform face area. So it's an area in the fusiform gyrus.
It is known to be really very responsive for faces, and so there's been debate for a long time about why that is, whether it's only used to recognize faces. But other people, including myself and my colleagues, have argued that it may actually be specialized for face recognition because we're experts at face recognition.
So this is the idea that you wanted to test with some of your studies, whether being experts in faces could be matched with being experts in other things. Tell us what you actually did.
So a long time ago, we've studied people who were experts at car recognition, and we also had studied birders who spent a long time identifying birds. And back then, we had found that the fusiform face area activated more for objects of expertise when they looked at a car than vice versa for a bird expert.
This is actually in the right hemisphere, and it's usually much stronger in the right hemisphere than in the left. These are areas that are often compromised in prosopagnosics.
Your mouth is getting tired.
Meet Terry Sweeney, a professional photographer. She was a firefighter until an injury damaged part of her social brain, the circuitry she uses to recognize faces.
Okay, if you had to guess, which looks to you the most like your mother? Just looking now, you can't tell which one of these. None of these really look like your mother to you. No. Okay. If you just cover up the face and I just look at the clothes, I can tell you. Okay, do you want me to uncover them? Okay, why don't I do that? I'll uncover them so you can see what they're wearing and other parts of the picture. And see, that's her, because the pink and purple shirt. The shirt. You recognize the shirt.
When Terry looks at these slides of famous faces, she can't recognize them, although other cues like hairstyle prompt a guess.
Is that Madonna? Because her hair, look at her hair. It's Marilyn Monroe. Oh, really? Can you tell who that is? No. Okay, I said Bruce Springsteen. That's not Bruce Springsteen, is it? Why do you say that? This guy's ugly.
Anyone or anything that reproduces sexually is constantly thinking to itself, who am I gonna mate with? We spend a lot of time thinking about mate choice because passing on your genes early and often is how you win at being alive. From an evolutionary standpoint, it's the most important thing you will ever do if you do it. And due to its extreme importance, it is also very complicated, you may have noticed. Our general understanding of it comes from Charles Darwin, who proposed that some individuals get more action than others because of sexual selection. You've heard of it. One gender of a species consistently prefers mates with specific traits, so individuals with those traits pass their genes on more often and spread their genes and the traits throughout a population. Old Charlie was certainly on to something. Take a look at this peacock. Some would consider this overkill, but to the ladies, a big frothy rack of feathers shows that a dude is healthy and has good genes. So as a result of sexual selection, male peacocks have evolved to look like 1970s Las Vegas showgirls. Humans, like peacocks, have evolved to like some traits more than others, and these preferences date back to a time when those traits gave an individual huge survival advantages. So in most cases, beauty is actually a language that conveys information about health and fertility. But if you're thinking that it's all about boobs and big muscles, think harder. You know what really turns us on? Bilateral symmetry. Humans are attracted to people whose bodies and faces look the same on both sides. How am I doing? Anybody? Symmetrical imbalance can mean someone was exposed to some kind of stressor during early development that they weren't tough enough to deal with. Similarly, a low waist-to-hip ratio drives both dude and lady humans wild. Where fat is deposited on a body is determined by sex hormones, testosterone in men and estrogen in women. Women who produce the ideal amount of estrogen generally have waists that are about 70% the width of their hips. Same goes for men and testosterone. People with this ideal ratio are often less susceptible to cardiovascular disorders, cancer, diabetes, and women in this range also have less difficulty conceiving and giving birth. Now you might be wondering, why will an asymmetrical guy with an ideal waist-hip ratio make you feel kinda meh, but he's got your friend driving by his house 3 times a day? Well, one reason could be in our genes. Everybody gives off subtle chemical signals called pheromones which give potential mates a clue to our genetic profiles. Crazy, right? Studies have shown that men and women are generally attracted to pheromones of individuals that are genetically similar to themselves, with one major exception. They prefer mates with a different kind of immune system gene called major histocompatibility complex, or MHC. The combo of two variations of the MHC gene helps a couple's offspring fight off disease better, and our pheromones basically tell mates which version of that gene we have. But even after you account for pheromones and symmetry and ratios, it's complicated, and people don't make rational decisions, so really don't bother with those hair plugs or that boob job. It's complicated.
Professor Parham's team has been comparing the genomes of those prehistoric people with the DNA of modern humans. They found that the Neanderthals and Denisovans had particular gene variants, or alleles, that play a big role in immune defence.
So from both of these archaic samples, it looked as though there were alleles that came into the modern human population in Asia and in the Middle East, and then spread out as human populations migrated and increased in size.
He says it was gaining those alleles through mating that would have helped our ancestors thrive. But Professor Parham warns there could also be a downside.
The downside of having this new haplotype that came from somewhere else was that it gave a greater risk of not being able to control the end of the response to infection and leading to autoimmunity.
He says that could explain the increasing prevalence of diseases like lupus, celiac disease and autoimmune hepatitis, where the immune system actually starts to attack the body.
Researchers studied the medical histories of children born in Denmark over a 10-year period. Children with mothers who had celiac disease, a digestive disease where people cannot tolerate gluten, were nearly 3 times as likely to be diagnosed with autism. A family history of juvenile diabetes was also associated with a higher risk of autism. The risk doubled for children whose mothers had this form of diabetes. And children with mothers who had rheumatoid arthritis were also at a 70% increased risk for autism. This suggests that prenatal environment may be affected by certain maternal autoimmune diseases.
Dr. P, whom I described, had overwhelming problems with agnosia of many sorts. He didn't recognize people. Although interestingly, he recognized cartoons, because in a cartoon there is an exaggerated nose or an umbrella. There are particular marks by which one can recognize a cartoon.
Big advantage that a human has is they can look at a complicated thing like a big protein, sort of zoom in on the regions that probably most need to be reworked. And we give them visual cues. The regions that are high in energy locally are red, and so they sort of stand out that, well, you need to do something here.
What we came to understand over the last 50 years about how this works is in terms of things that we call energy landscapes.
You know, the way I work is to make this kind of Brobdingnailian world in which I make the face into a landscape. And I journey across that landscape like Gulliver's Lilliputians, crawling over the face of a giant. Not knowing that they were on the face of a giant, but knowing everything about that face.
To start with a protein that is so misshapen, it's ugly and it's red, and to work through that to a beautifully streamlined structure where it's symmetrical and things are tucked in and nothing is hanging out of the sides. Yeah, that is sort of the goal, and that's what I like doing, to sort of help it in some ways, to sort of be what it should be.
And then what I do is I put all that information together, or the kind of nose, the nostril, the corners of the mouth, whatever, and I can commit it to memory. So I know that it's no accident that I was driven to make portraits of people who matter to me.
I think it's important to say, and you know, I portrayed myself as sort of as withdrawn or helpless, but I think I also have a vivid love of humanity, as Chuck has. But for me, the portraits take the form of narratives, of stories.
Yeah.
Although I'm not very good often on details of what people look like. The first time I took a piece into the New Yorker, the then editor, Robert Gottlieb, this was about an Italian painter. He said, well, what does Franco look like? And I said, I said, the piece is about his work,
Well, your words paint the most specific portraits of people's lives, and I always have identified your characters as vivid a portrait as anything anybody could do in any other art form. And you celebrate your connectedness with humanity in a really important way. I mean, it's a way that we can identify with, even if it's a problem we don't have. Empathy is the basis of, I think, the mortar that holds society together.
I'm going to start with a rather depressing image. It illustrates one example of 0 degrees of empathy. So this is an image of 2 scientists working in the Nazi concentration camp, Dachau, and they were performing an experiment on one of the inmates in the concentration camp. They called it the freezing water immersion experiment, and these 2 scientists were interested to see how long a human being could survive in freezing water. And like good scientists, they took measurements, and they measured the person's physiology and obviously duration until they died. Now, the thing that strikes, I'm sure, all of us is how was this possible? How is it possible that human beings could treat another person with no empathy, purely in the pursuit of their own interests in science? The fact that these were educated people makes it all the harder to understand. It's not the only example of human cruelty, and actually we only have to open any newspaper or turn on the news any day of the week to hear examples of human cruelty, but it raises the same question about how we understand human cruelty. Well, the old theory to explain human cruelty is to talk about evil, that people do awful things to each other because they are evil. As a scientist, I find this not very useful as a term. I don't think it helps us understand what's going on. It's not just not explanatory, but it's dangerously circular. Because if we take the word evil just to mean the absence of good, then effectively all we're saying is he did something bad because he is bad. It doesn't really take us any further, and if anything, it just takes us back to where we started. The alternative that I'm proposing is that we should explain human cruelty in terms of the erosion of empathy. So, what is empathy? Well, there are lots of definitions of empathy. My definition recognizes 2 components. The first is the cognitive part. That's the recognition or the understanding part. And I've defined that as the drive to identify what another person might be thinking or feeling. So it's all about putting yourself into someone else's shoes, to take their perspective and to imagine what's going on in their mind. The second component is what psychologists call affective, which is another word for emotional. And it's the emotional reaction to somebody else's thoughts and feelings. And you can see my definition there as the drive to respond with an appropriate emotion to someone else's thoughts and feelings. And I'm going to argue that you need both components to talk about somebody having empathy, that if you had one without the other, arguably that wouldn't be empathy at all. The psychopath might be able to do the first part. They might be able to recognize that their victim is in pain, but not have the appropriate emotional response of wanting to alleviate another person's distress. So arguably, the psychopath does not have empathy. The other new idea that I want to introduce at the outset is the idea of empathy being on a spectrum. Here's the familiar bell curve that we see time and time again in nature when we look at individual differences that differs in the population. Most of us are going to be somewhere in the middle, but you can see that there'll be a minority of people who have very high empathy, and again, a minority who have very low empathy. And what I want to look at is what are the different routes that we can end up at this extreme left-hand tail of the distribution. Well, here's a way to measure empathy, because I've just shown you a sort of idealized model, that bell curve. This was a questionnaire called the empathy quotient, which attempts to try to identify where people lie on that empathy spectrum. How this works is that you read each statement and you say whether you agree or disagree with each statement as a description of you. There are lots of these questions. And what you can see is, sure enough, it does produce that nice bell curve. So now we're looking at real data from thousands of people who've used the questionnaire in the population. As we expected, most people are in the middle, so we've got average empathy, but there are people down at this low end. You can also see, just as an index of individual differences, that if we just cut the population in terms of gender, males and females, that females are scoring slightly but statistically significantly higher than males on this measure of empathy. Here's another way that you can measure empathy, which is what we call a performance test, how good you are at recognizing what someone else might be thinking or feeling. So you look at the photograph of someone's face, in this case just the eye region of the face, and you're asked to pick which of these 4 words best describes what she's thinking or feeling. This is just one example from the test, and the correct answer here is that she's dispirited, a little bit sad. So we're well aware that we all make a lot of eye contact. We tend to look at people's faces, particularly look at their eyes. We're not necessarily consciously aware of why we're doing it, but this sort of experiment is telling us that actually there's a lot of rich information around the eyes as a cue to what someone else might be thinking or feeling. And what you can see just at the bottom of that slide is again that women, on average, are scoring slightly but significantly higher than men on this test of empathy. But back to the whole question of cruelty, the philosopher Martin Buber was also very interested in this question, and he identified that the point at which you start treating a person as an object is when you become capable of cruelty. And he distinguished 2 different ways that you can relate to a person. You can either relate to them as a person, what he called I-you relationships, where you recognize the person's subjectivity, or you can treat a person as an object, no different to this piece of furniture, what he calls I-it relationships. And the moment that you shift from one mode to the other is the point when your empathy has been switched off. I work in a department of psychiatry in the university, and so one perspective into how people can end up with low empathy is to look at specific psychiatric conditions. We've already mentioned psychopaths, but I'm going to be showing you 3 different personality disorders which can, I think, involve low empathy. And I call these zero negative because people can end up with literally 0 degrees of empathy. And it's negative in the sense that it's not good for the person, and nor is it good for people all around that person. So these are the 3 personality disorders. The top one is borderline personality disorder. People with this condition have very unstable relationships and extreme mood swings. They tend to switch from one moment expressing affection to, within seconds, expressing anger. And they can lash out on people that are close to them, either physically or emotionally close to them. They often also threaten suicide with no intention of carrying it out, but also with no real consideration of the impact that such a threat has on the other person. The second personality disorder is psychopathic personality disorder. It's also sometimes known as antisocial personality disorder. And these are individuals, I think, also have low empathy, but in a different way. So they're diagnosed on the basis of being superficially very charming. They lull you into trusting them, but it soon turns out that almost everything they say is a lie. They'll use deception to get what they want. The last one, less well known, narcissistic personality disorder. You can see an image here of the Greek mythological figure Narcissus, who was only in love with himself and his own reflection. It really just describes individuals who are self-preoccupied, who don't really think about others all around them. So I think that although these are personality disorders, in the sense that they are enduring personality characteristics, Another way to conceptualize these is in terms of low empathy. But what's led to this outcome? John Bowlby, who worked at the Tavistock Clinic up in Swiss Cottage here in London, he argued that early experience plays a major role. So he studied delinquents. So he was looking at teenagers who'd got in trouble with the law, and he was able to trace back that a lot of their antisocial behavior was because they had been brought up in children's homes, in institutions where they didn't have the opportunity to form caring relationships with a parent figure, but instead they had multiple caregivers. Many of them had had as many as 50 by the time he interviewed them. So he argued that attachment is key in the formation of empathy. These are individuals who, by their teens, were quite willing to do what it takes to get what they want, but also had great difficulty in getting close to other people and trusting other people, forming stable emotional relationships. So he argued that insecure attachment in childhood, either through neglect or even worse, through abuse, could lead to this outcome of delinquency. But that can't be the whole story, because here we see another study from London, the Institute of Psychiatry down in Camberwell, by Avshalom Caspi, who looked at a particular gene. So this is a gene that we all carry, but there are several versions of this gene. It's called the MAOA gene, and you can see the two variants in red and blue here. But he looked at the likelihood of developing conduct disorder or delinquency in your teens, depending on whether you had one version of the gene or the other, and also as a function of whether you'd experienced maltreatment. And what you can see is that the worst combination is in individuals who've experienced severe childhood maltreatment, but also carry this particular version of the gene. So this is suggesting that environment is important, but it interacts with your genetic makeup. Back to that questionnaire that we used earlier, the empathy quotient. When people filled it out, we also asked them to give us a bit of their DNA. And we looked at a whole bunch of genes, but these ones here showed a significant statistical association with the scores on the empathy quotient. A couple of these genes are involved in hormones, particularly testosterone. And we thought that was interesting, given the sex difference that we came across earlier, that women seem to have better empathy than men, given that men have more testosterone than women. So we've been looking at testosterone produced by the fetus to see whether the hormones that the baby is producing in the womb might have any effect on how the brain develops, and indeed postnatally, whether it's got any link to how much empathy the child shows. The way we do this is by asking women who are having amniocentesis during pregnancy, where a needle is introduced into that fluid that surrounds the baby. We're asking to analyze that fluid for how much testosterone is in the fluid. And then we wait for the baby to be born and test the child later on for their empathy level. So what you can see here is that these same children whose hormones were measured during pregnancy are now 8 years old. They're taking the child version of that empathy test. Here, the correct answer is that he's interested in something. And what we see in the graph down below is that there is a negative correlation with the amount of hormone that the child was producing in the womb. So the higher the child's testosterone prenatally, the more difficulty they're having reading faces to decode someone's facial expressions 8 years later. So although early experience is important, so are genes, and as it looks now, so are early hormones. The earliest sort of case study from neurology that gave us the big clue as to where empathy resides was from this man called Phineas Gage, who was working on the railroad track in the 1840s in the States. And his job was to use a metal pole to push the dynamite down before they laid the railway track. And one day the dynamite went off a bit too early and blew that pole right up underneath his eye and through his brain. A horrific accident, but the reason it made medical history in neurology was that he didn't die. Indeed, he lived for another 12 years. They removed the pole, But what was striking was that his intelligence, his reasoning, didn't seem to be affected by this brain damage, nor was his memory or his language. Indeed, much of his psychological functioning was as it was before, except that his empathy seemed to be affected, that prior to the accident he was described as a very courteous, polite individual. After the accident he was described as very impulsive, very rude, unable to judge what was socially appropriate. More than 100 years later, the neuroscientist Hannah Damasio was able to obtain Phineas Gage's brain, which had been preserved in a vat, and put it into a modern MRI scanner to see exactly where the location of the damage was. And she inferred that it was in this left ventromedial prefrontal cortex. So if anyone asks you, where is empathy in the brain? It's in the left ventromedial prefrontal cortex. Well, that seems to be well confirmed by modern neuroscience. But what you can see here is that actually that's not the only region involved in empathy. By my count, there are at least 10 different parts of the brain. So the ventromedial prefrontal cortex is up there. It's been well confirmed by other studies, but so are many others, other regions, and that they're all highly connected, so that we can talk about an empathy circuit, that when we empathize with another person, this network of regions are activated. And when individuals who have personality disorders or very low empathy have brain scans, we can also see that different parts of this network, this empathy circuit in the brain, are underactive or haven't developed in the usual way. I'm going to ask a sort of almost unthinkable question now, which is whether 0 degrees of empathy is necessarily always bad. There's at least one condition in psychiatry where individuals struggle with empathy, but it doesn't necessarily lead to acts of cruelty, and that is people on the autistic spectrum. So here we can see people with autism and the related condition of Asperger's syndrome. They have difficulties in social relationships and communication, and they too struggle to empathize. Their low empathy tends to lead them to avoid other people because they find people confusing, to withdraw from the social world rather than to commit acts of cruelty. So this is telling us that, that low empathy may be part of what happens when someone commits a cruel act, but it's not a symmetric relationship, that if you have low empathy, it doesn't mean you're necessarily going to commit a cruel act. People with autism process information very differently to other people. In particular, they've got strengths in certain ways of seeing the world. They tend to notice small patterns, small details that other people miss. And the reason that I call them seropositive is that alongside their difficulties with empathy, their unusual attention to detail often leads them to giftedness. I'm going to finish just by talking a little bit about empathy outside of the human species, because having identified that genes play a role in empathy, it raises this idea that empathy may be the result of evolution, and that those genes may have been selected, positively selected, during evolution. The only experiment that I've come across which has tried to systematically test empathy in monkeys was by Jules Masserman at Northwestern University in the 1960s. And what Masserman did was train these rhesus monkeys to pull a chain every time they wanted food. And the monkeys soon learnt that if they did that, they got the reward. And then Masserman changed the contingencies so that when they pulled the chain, yes, they got the reward, but they also saw another monkey getting an electric shock. And what Masserman observed was that the monkeys soon stopped pulling the chain as soon as they learnt that in getting a reward for themselves, it was also causing pain to another member of their species. So this certainly suggests that simpler forms of empathy may predate human beings, which should come as no surprise.
Hello, my name is Jim Vieira. I'm a stonemason, writer, researcher, and lecturer. Like Rona said, about 20 years ago, I started to find odd stone structures in the woods, and it really piqued my interest, and I tried to figure out what it meant, because they didn't fit the colonial context. So, my normal presentations are several hours with hundreds of slides. I will do my best to give you a taste of what I've been researching for about 20 years. I've written a series of articles for Ancient American Magazine. I also write for The Independent here in Shelburne Falls. The gist of what I'm going to talk about is my understanding that what we're told about ancient America seems to be clearly wrong, that there was a racist paradigm created to push Native Americans off the land in the 1800s, led by institutions like the Smithsonian, political and religious motivations. So Native Americans needed to be portrayed as nomadic, savage, disorganized, and unsophisticated, so you could justifiably wreak havoc on them and create manifest destiny in the United States. I don't want to go too much into that, but that I have to express that because that is what we have, that is the legacy that we have now with things like this not properly understood. So I will talk about the ancient cultures and their level of sophistication in ancient America. This is a stone cairn, that's a stone chamber oriented to the equinox in Goshen. That is a ceremonial mound with a niche and quartz, one of a dozen in Washington, Mass. Here we have Cahokia. When the colonists showed up, there were over 200,000 earthen pyramids, geometric forms, conical mounds, and effigies of astounding proportions. It was like a geometric blackboard in ancient America. This is at Cahokia. It still exists. These structures are so staggering that people don't even think they exist still. So this is what the colonists encountered. 100-foot high, 14-acre base. That's 1 acre larger than the Great Pyramid of Giza. 22 million cubic yards of soil taken from over a mile away to build this structure. And it looks like, many researchers think that actually the mound builders, which started 3400 BC in Louisiana, came up from the Yucatan, avoiding the death cults, to create a more harmonious civilization. And you see it has some air marks of a Mesoamerican structure. So instead of stone, which wasn't available, they built with earth. That's a wood henge right there. A lot of these sites are aligned to astronomical events. In Newark, Ohio, we have the most enigmatic earthwork on the planet. Right here, up in the corner, is the octagon and circle, 50 and 20 acres. Its researchers Lively and Horn in the 80s determined that it was a precise lunar calendar. That line right there, that road, is a 55-mile, 189-foot wide, the entire length, several foot high, earthen-walled corridor to another site in Chillicothe, Ohio, that is also a lunar calendar, measuring the Metonic 18.61-year cycle of the moon. Now, the astronomy that we find is Mayan-like all around ancient America, from the star cities of the Hopi and Anasazi to the mound builder creations. And the Athenian Meton in 432 BC was supposed to be the originator of the Metonic cycle. The mound builders might have beat them to the punch. Right down the pipe here. Actually, you find the 51.84 slope of the Great Pyramid embedded in this earthwork in the azimuth line, and you find a 187-foot grid pattern found at Teotihuacan, Mexico, in the earthworks of ancient America, or a vast number of them. It appears that a common school of mathematics and engineering exists all around the globe, which is a story for another time.
Well, it's true that some African fractals are, as far as I'm concerned, just pure intuition. So some of these things, I would wander around the streets of Dakar asking people, well, what's the algorithm? What's the rules for making this? And they'd say, well, we just make it that way because it looks pretty, stupid. But sometimes that's not the case. In some cases, there would actually be algorithms, and very sophisticated algorithms. So in Mengwetu sculpture, you see this recursive geometry. In Ethiopian crosses, you see this wonderful unfolding of the shape. In Angola, the Chokwe people draw lines in the sand, and it's what German mathematician Euler called a graph. We now call it an Eulerian path. You can never lift your stylus from the surface, and you can never go over the same line twice. But they do it recursively, and they do it with an age grade system. So the little kids learn this one, and then the older kids learn this one, and then the next age grade initiation, you learn this one. And with each iteration of that algorithm, you learn the iterations of the myth. You learn the next level of knowledge. And finally, all over Africa, you see this board game. It's called Awori in Ghana, where I studied it. It's called Mancala here on the East Coast, Bao in Kenya, Sogo elsewhere. Well, you see self-organizing patterns that spontaneously occur in this board game. And the folks in Ghana knew about these self-organizing patterns and would use them strategically. So this is very conscious knowledge. Here's a wonderful fractal. Anywhere you go in the Sahel, you'll see this windscreen. And of course, fences around the world are all Cartesian, all strictly linear. But here in Africa, you've got these nonlinear scaling fences. So I tracked down one of the folks who makes these things, this guy in Mali, just outside of Bamako, and I asked him, how come you're making fractal fences? Because nobody else is. And his answer was very interesting. He said, well, if I lived in the jungle, I would only use the long rows of straw, because they're very quick and they're very cheap. Doesn't take much time, doesn't take much straw. He said, but wind and dust goes through pretty easily. Now, the tight rows up at the very top, they really hold out the wind and dust, but it takes a lot of time and it takes a lot of straw because they're really, really tight. Now, he said, we know from experience that the farther up from the ground you go, the stronger the wind blows, right? It's just like a cost-benefit analysis. And I measured out the lengths of straw, put it on a log-log plot, got the scaling exponent, and it almost exactly matches the scaling exponent for the relationship between wind speed and height in the Wind Engineering Handbook.
So my thought is that the mound builders who built all kinds of structures may have made it into New England and be behind some of the ceremonial stoneworks that we find here. I read through the historical texts. I saw that the mound builders built walls and earthen and stone complexes that are carbon dated. Virtually every other part of the country has earth and stone structures dated thousands of years old, ceremonial structures. But there's a historical blackout because of the paradigm, I believe, in New England. So this is the Goshen Stone Chamber, one of hundreds in New England. Look at the fine work. It's all dry laid. Everything I'll show you here is dry laid. 12 interlocking stones for the roof. Half of these chambers are oriented to the equinox sunrise or winter solstice sunrise. So I went Indiana Jones a couple of years ago, and I'm in the chamber March 20th, right down the middle. And this, you find this at a lot of chamber sites. And we are told that these are colonial root cellars. And this root cellar has a 10-ton, 10-foot by 5-foot ceiling in New Salem, Massachusetts. That's me for scale. It's over 6 foot high. As a stonemason, that's quite a feat to get that up there. This is very interesting. Gunji Wamp. John Winthrop, founder of Springfield, Massachusetts, 1654, writes to John Winthrop, governor of Connecticut, asking, we just showed up at Pequot, Gunji Wamp. We found the stone complex with many strange stone walls and stone huts. Do you know anything about them? And it's strange indeed. 1988, David Barron, researcher, found that the stone-lined shaft created in the chamber allows the equinox sunset to come through twice a year, and only on those days. So another orientation, plus archaeologist Jim Whittle got many carbon-dated results out of this. Let me quickly, many of these sites around the country have, in the Northeast have carbon dates that came out of them. Right here from Geochron Labs, Cambridge, Mass. 2,995 years from the present date was one of the carbon dates that came back. Harold W. Kruger, Technical Director, Geochron Labs. The paradigm doesn't like this, so we're left with root cellars and farmers' clearing piles. There are hundreds of these all over the place, thousands, I'm sorry. And as a stonemason, that is not a farmer's clearing pile. That is. But in these sites, in these mounds, are in other parts of the country, and archaeologists acknowledge that they're old, that the Adena, the Hopewell, the Mississippian cultures, native cultures built these things. But in the Northeast, you have a different story. That's the Proley Dolmen in Ireland. And when you get to the United States, that is in North Salem, New York. But it's been transformed into a glacial erratic somehow because it doesn't fit the paradigm. I went to visit this. It's on 5 points. It's a pretty smart dolmen. And it's really absolutely man-made. But it shows you that it just doesn't fit the paradigm, so it just gets ignored. 1000 BC, Ireland, a national treasure. Root cellar in Vermont. So the colonial astronomers who built this knew their stuff because that's Harvard's Barry Fell right there. 9 14-foot-long, 3-ton stones for the roof. And Maver and Dix researchers who wrote Manitou, they determined that the doorway marks the 18.3 and 28.6 declination angles of the moon, the major and minor standstills. It's eclipse predictor, and it lets the winter solstice sunrise come right through the center, just like Newgrange, 3000 BC, Ireland. That's ancient English. I'm not saying that Europeans built these structures. What I'm saying is that they exist all around the globe, and you find the same ceremonial structures in New England, but somehow they're colonial remnants where we live. So, King's Chamber, New York, massive granite blocks. I visited, there's 150 of these chambers in Putnam County, New York. This is interesting. Somebody who read one of my ancient American articles sent me these pictures. He found this 25 years ago in the woods. He's a stonemason. He said it plagued his mind. And it's arched. It's all dry laid. Beautiful construction. And as a mason, I would imagine I would have to build a false work to create this. It's just a mind-numbing amount of, work behind this. And it just doesn't make any sense. So, gets a little strange here. I ask you to bear with me. I'm trying to, the mound builders had trade routes through New England, and that is known. But I was trying to tie up, I'm saying, are the mound builders to be found in New England? Did they make it here? Did they build any of these structures? Did they, what was going on? There's not much known about the history of New England, for instance. So I started to read through historical texts, and I found some strange things. History of Deerfield. This is eminent historian George Sheldon. One of these skeletons, this is on page 78, monstrous size, head as big as a peck basket with double teeth all around, examined by Stephen Williams, who said the owner must have been nearly 8 feet high. 8-foot skeleton, double rows of teeth. Like, what the hell is that? And I just felt compelled to dive into the historical texts. So I spent countless hours, tens of thousands of pages, and I found similar things. Middleborough, Mass., 7-8, double rows of teeth. Up in Rockingham, Vermont, the jawbone was of such size that a large man could easily slip it over his face, and the teeth, which were all double, were perfect. Double rows of teeth again. Here we go. Martha's Vineyard, 7 foot, an unusual feature, a complete double row of teeth in both the upper and lower jaws.
Here are some pictures of some unusual mammalian hybrids. So we're still talking about hybrids now, like mules. Up here we have a what? That's a zorse, yeah, or a zebroni or something. It's a horse family crossed with a zebra. In this case, it was a spotted horse, and so you get a very unusual color pattern where only the back half of this hybrid is striped like a zebra, and it's a really beautiful animal. That's one kind. These two down here are cat family hybrids, which are also very unusual. This one down here is a lion-tiger. And the lion-tiger cross is a bit like the mule. It's larger than both the lion and the tiger.
So I went to the Pecumtuck Museum. I said, yeah, here you go. Sheldon talks about an 8-foot skeleton with double rows of teeth. Do we know anything about this? He said, oh, here's his archaeological scrapbook. This is my Da Vinci Code moment. I open it up, and he has giant skeleton reports pasted in there with mound builder stuff. And Sheldon was basically, in his collaging saying that it looks like he believed the mound builders were in New England and they had race of giants interspersed with them.
So the most common animal hybrid is the mule, and that is really it's my favorite animal, and it's what I spend most of my time thinking about and working on. And you can mate a horse with a horse, and you get an animal that is like a little horse comes out. If you mate a mare horse with a jack donkey, you get an animal that looks sort of like a horse and sort of like a donkey, but it's really a blend of the two. It has long ears like a donkey and a body like a horse, and that's called a mule. But the outcome of these crosses depends upon which way you do the cross. So if you take a male donkey, breed it with a female horse, you get an animal that's called a mule. But if you do the opposite cross with a stallion mated with a female donkey, that animal's called a hinny. And that's actually a very profound observation that these two animals might be different because they have half their genes from their mother, half from their father, but they get them in opposite directions in this interspecies cross. The mule has made a number of really important contributions to scientific thought. It was the first genetically engineered animal, and there have been mules around for about 2,000 years at least. People have been breeding them starting in the Middle East, and it's a real ideal animal for for an agriculturalist to breed because the offspring is sterile. So if you breed a mule and sell it to someone who wants to use that mule, they can't go off and breed that mule again. It's like selling them hybrid corn these days that's sterile. You have to, that mule breeder can sell another one the next year because that fellow who bought that mule can't breed it. And it blends the genes of two different species, and the outcome is better in many ways than either parental species. And that defines the term hybrid vigor, which we all know about, and it was defined in light of the observations made about mules. They're stronger than the donkey, and they're more resistant to disease and injuries than the horse is, and they live for about 40 years, whereas the horse lives maybe 30 and the donkey maybe 35. They live longer than each parent species and have fantastic capabilities for work. They also provided evidence against Aristotle's seed and soil hypothesis. And this was the idea of homunculus, that inside the sperm there was a little person, and that the female only provided sort of the seed bed where the seed would grow. But when you look at a mule, you know that it's not just like the seed that came from the donkey. It's a blend of both parent species. So that debunks that old idea about seed and soil. A lot of the ideas that I've learned about mules come from this gentleman, Professor Roger Short, who was an A.D. White visiting professor for several years here. He's an Englishman now in Australia and a veterinary scientist and a really fantastic guy. So, and of course, mules made great contributions to work and warfare over many, many centuries. Harry Truman was a great fan of mules. They have a fantastic, fantastic history and probably not much of a future, but some of us still like them. Now, really, this is going to sound silly, but this is really, really important cutting-edge genetics. One of the areas I'm really lucky I'm blessed to work in three distinct areas of biology: immunology, genetics, and reproduction. And on the genetic side, I get to go to conferences and hear about advances in genetics in all species. And I was just at one a couple of weeks ago down at the Cold Spring Harbor Lab in Long Island, and I learned a bit about what's being known about the genome of Neanderthals, the genetic makeup of Neanderthals. The genome sequencers, led by Svante Pabo, who works in Germany, has taken tiny little fragments of Neanderthal bones, isolated DNA, and determined the genome of the Neanderthal, and used that information to determine, using genetic methods, how long ago Neanderthals and humans were a single species, where the common ancestor was. They've also been able to compare human genomes and ask the question of whether there's any evidence of Neanderthal genes in the human genome. And they found that there is. And the amount is quite significant, upwards of 5 to 7%. Neanderthals used to live in the Neander Valley. You could have called it the Cayuga Lake Basin, but that's where they lived. And out of Africa came the modern humans, and the word the geneticists use is admixed. They admixed with the Neanderthals. Came out of Africa, admixed with the Neanderthals. This was the Neanderthal territory. There was another group of Neanderthal-like creatures called the Denisovans. They lived up here in Siberia, and they have their genome has been sequenced. They were distinct from the Neanderthals. And so you can find in people of European and Asian ancestry evidence of about 7%, 5 to 10% of your genome is common with that of Neanderthals. We've been separated from them for 30,000 years or so. And in some of the tribes in Papua New Guinea and those islands out there, there's evidence for a different kind of genome, which is probably the Denisovan genome. And they might have 7% Neanderthal and 5% Denisovan. So they might be 12 or 15% different from us.
So I've been studying what parts of the genome do human populations derive from Neanderthals, and can we make any sense out of what they do? And I will say that this work is really just beginning, and we're learning new things almost every day about it. One of the things that's highly significant about Neanderthal genes in human populations now is that different populations of people outside of Africa, for example, Europeans and Chinese people, have different Neanderthal genes. There's some overlap. There are a few things that are relatively common in Europe and in China and in India and in Japan and in other places. But for the most part, things that are relatively common in Europe are rare in China, and things that are common in China are rare in Europe. It seems that when the mixture took place between humans and Neanderthals, that mixture was before a time that human populations began to separate and become isolated from one another. So the mix that they ended up with is about the same fraction. Look at any person, and he's likely to have about 3% Neanderthal, but the fraction is representing different genes. Most of the genes that came in from Neanderthals are vanishingly rare. Only in 1% of people or fewer. And there's only a few things that are common. So we're beginning to understand the paleobiology that gave rise to our current distribution of Neanderthal genes. Still doesn't tell us what interesting things we might have gotten.
Now I'm going to show you two graphs here. One that shows you how much the heterozygosity drops as you leave Africa and get to the Americas, and we can see that it's dropping very precipitously. In fact, the correlation is 80%, and that's a function of what happens after 70,000 years ago, say, the out of Africa groups slowly move over the next 40 or 50,000 years into the Americas, by which time each colonizing group is quite a bit smaller in terms of its genetic variation than you had in the founding groups that left Africa, which, as you've heard today, are the most genetically variable on the planet.
And when we think about empathy in all of us, one of the double-sided issues of empathy, of course. You talked about selection. We're not hardwired to show strangers the same empathy as we show family members, and indeed conflict sometimes arises, therefore, as a consequence of empathy for those around us, which is then expressed as hostility towards those who are deemed to be threatening them.
Yeah, and some people have talked about this in terms of in-group, out-group relations as well. So it could be that the in-group is your kin, because you share genes with them, or it could just be that it's your local culture, and that people who don't share your culture are the out-group. And it's certainly true that we find it easier to empathize with those who are nearer to us, whether they're nearer genetically or culturally. And that may also have some important lessons for social causes to low empathy. I tried to argue that the way that you can lose your empathy is through many different routes. It could be a genetic route, could be early experience, but it could also be these cultural routes of how we define ourselves in relation to other groups.
Here is a graph that shows the same distance from Africa, but it's now in terms of linguistic diversity, phonemic diversity. And what we see is, although it's much noisier, so the correlation is less, you still see this drop in phonemic diversity as you move out of Africa to the Americas. A cultural trait which is showing a similar pattern over the same period as our other genetic character. Again, if we take the data that we showed earlier from the Human Genome Diversity Project, and we just break it down into the East Asian populations, we see that if you ask how similar are the populations across East Asia, we find those populations from Japan to Mongolia, which are along the northern Mongolian border of today's mainland China, and compare them with all of the southern Chinese populations. All of these populations are classified as having languages which belong to the Altaic family. These are not. These are Sino-Tibetan populations. The languages, what we've plotted here, are genetics, but the groups which have a natural break here are the two linguistic groups. Up here, is Pakistan, and here we see this very strange group called the Kalash, who believe that they're the descendants of Alexander the Great's armies, and the famous Hazara, the subject of the book The Kite Runner, which are discriminated against in Afghanistan and Pakistan because they have so much East Asian ancestry compared to the rest of Pakistan and Afghanistan.
It's clear that humans are not like other creatures, especially in two areas. One is the importance of culture. The second is the importance of language, so you might argue the two are the same. And this tremendous variation in behavioral norms across groups, as illustrated in the picture. So Aristotle noted memorably many years ago, ho anthropos phuse politikon zoon, which translates into English as man is by nature a social animal. Politikon here means social, not political. And I've taken the definition of culture from E.B. Tyler, who is regarded widely as one of the founders, if not the founder, of cultural anthropology. So it's really important to notice that though there are other creatures that have some form of culture, humans are, the diversity of culture in humans is just tremendous. This is from one of my kids' favorite websites called Hats of Meat, if you're interested. It's been around for a very long time. Now, the same is true not just of cultural diversity, but of language diversity. So just like every human community has a culture, every community has its own language as well. And despite what you may have heard from some well-known linguists, at least on the surface, languages differ from one another much more than they resemble one another. We could argue about that for a long time, but as I say, at least on the surface, that is true. So one question you might ask is whether this linguistic diversity, this great diversity among languages, is due to genetic diversity. We know that there is some connection between the human ability to acquire a language and at least one gene, and that's FOXP2. When FOXP2, when the human variant was first discovered, people thought it was the gene for language. People have, of course, now, in the 20 years since, they've discovered that FOXP2 has to do with lots of aspects of human behavior, but it is still true that it has something to do with language. It is also true that genetic differences between individuals within a community do correlate with linguistic abilities. And a lot of this work was done by Karen Stromswald in her work looking at twins. So question is, if you look at population-level genetic differences, are they related in any way to linguistic differences between these populations? This is the kind of thing that Greg Ray talked about when he talked about the notion that you have a gene and then you have a trait, right? So the question is there a genetic difference that manifests itself in a linguistic difference? And there's one study, one suggestive study, that suggests that, yeah, there may be something there, and that has to do with what we call tone languages. So tone languages are languages like Chinese. Now, every language makes use of tone. If you don't make use of tone, you sound like Hal, the computer from the Space Odyssey. So in all languages, people use tone as a kind of a speech melody. But in tone languages, individual words can be distinguished in terms of their pitch. And I'm not going to try and show that to you because I'm really terrible at it, in part maybe because of my genetics. But Chinese is the standard example, where in Mandarin Chinese you have 4 tones, and you can get the same syllable ma with each of the 4 tones, and in one case it means mother, and in another case it means horse, etc., etc. Interestingly, these tone languages are concentrated in Africa, East Asia, and the Americas. So here is a map from the World Atlas of Language Structures, which is a wonderful resource, showing you those red dots are what we call complex tone languages, and we don't need to worry about exactly what that means. But you'll see that they're all concentrated in certain areas. Somebody suggested to me that it might have something to do with climate, because a lot of them are around the equator. But as you'll see, that doesn't seem to be the case. It seems to be more genetic. All right, now how do you get a tone language? Very briefly, the way you get a tone language is by losing a consonant distinction. So if I say s and I say z, you can hear that s has a much higher frequency than z. So consonants just inherently have differences in their frequency. And if you lose the distinction between the consonants, that distinction can migrate onto the vowel preceding them, and that's basically how you get tones. And we know that this is true. This is called tonogenesis. So the question is, well, why doesn't that happen all the time? So, for example, German and Russian don't distinguish final consonants in terms of like s and z. Only s occurs at the end of a word. So what happens? The answer, this is somewhat speculative, but the answer is that this may have to do with people's ability to actually make these tone distinctions, to hear those tone distinctions, and that may have to do with genetics, and in particular with certain alleles of two brain size genes, ASPM and microcephalin. And the idea is that these conservative alleles predispose people to actually encode these finer distinctions. And here is the graph that attempts to show you that. And if you look at the lower corner there, you'll see all of those little white squares concentrated. Those little white squares are the tone languages, and they're also the area where people have the lowest frequency of the adaptive haplogroups of ASPM and microcephalin. So those are the genetically conservative populations. So the idea is that there's a correlation between whether you have a tone language and whether you are genetically conservative with respect to these two genes.
When you talk about the hybrid, the horse and the donkey, or the horse and the mule, get the
horse and donkey make a mule, right?
And the donkey make a mule. Does that translate to humans? Even though humanity is just one race, hybrids in different ethnic cultures, for example, do they produce like a stronger human? Could we associate that or no?
Well, I mean, we've always thought that close inbreeding is bad. So in that sense, it does translate. And outbreeding is often good because we all carry a certain number of genetic mutations. And in individuals who are closely related to us, they probably carry those same kind of mutations. And for many of those, if you have 2 copies of that mutation, you'll show a genetic disease phenotype. You'll express that disease. And if you marry someone from outside of your genetic group, it's less likely that they will carry the same set of mutations. So you're more likely to be genetically robust.
I make a very short summary of a study we made in the south of Sweden. According to risk factors for autism and Asperger's syndrome. The study was designed to investigate pre- and perinatal risk factors. The study group continued of 376 people diagnosed with autism or Asperger's syndrome.
Is your theory primarily a theory about pathology, or is it a theory about empathy across society as a whole? Because it seems to me that these are 2 very different types of phenomena.
They may or may not be. So it's a theory about all of us. And so I don't draw a hard and fast line between pathology and the rest of the population. And that was inherent in that bell curve I showed you, that it's a seamless bell curve. It's not that at one point there's a discontinuous, a point where you could separate those who've got an illness or a psychiatric condition from the rest of us. So in that respect, it's a theory about all of us.
We have in Sweden a great many people coming in migration, and Malmö is a town that represents much of these. But as you can see here, odds ratio for migration should be 1 if that was the same in these different ethnic groups, but it wasn't. As you can see, we have 7 times as many people coming from sub-Saharan Africa that had autism. And it was not the only country. You see, the rest of the world, there is an odds ratio that is much higher than expected. So this we don't know. We have tried different hypotheses. Why is this like this? We can see it in many other studies made in Sweden, in Stockholm and Gothenburg. We have the same. And sometimes we have heard in the Somalian group in Stockholm that you shouldn't go to Sweden, you get autism. They call it the Swedish disease. So we don't think it's that hard. But we haven't done any studies in Somalia. Is it the same? Or why is it like this? We have tested D vitamins, if that's that have been hypotheses, if that's the reason. If you come to the north of Sweden and northern countries, you get not so much sun as expected. Or is it that people coming from another country, the mothers are especially vulnerable for infections, that they come to another country where they haven't got that immunity for that. But that is, we try those hypotheses, but we got no support for those reasons. So that is still very much to do in this research, if it is the migration itself, or what is it? Is it special ethnic groups that come from Sweden? We know that from some countries you have a relation, and many people are they married inside their family. So that can sometimes be a reason, but not always.
Now, more than half of today's human populations are involved in consanguineous marriages. That's a huge number of people. Where do they live? Well, you can see the concentration is largely through South Asia and the Middle East. Largely through this area, you have this very high concentration of cousin marriages. And in such populations, they can account for up to 10% of the human population being mated as close as second cousins. This has tremendous health consequences. It's not just there. In North America, by the middle of the 19th century, first cousin marriages were actually quite frequent within the USA. Today in Britain, among the 2 million Pakistani immigrants who reside in Britain, the frequency of genetic diseases is 100 times greater than the frequency among Britons who are not from South Asia. That is a big public health problem. Now, can we say how much of that is around the world outside of those people that we know as being inbred? Well, we'll get to see some of the consequences in terms of DNA variation. What we're going to look at is 1,839 unrelated individuals representing 64 worldwide human populations. Among those populations are the group, the Human Genome Diversity Project, that Luca Cavalli-Sforza and I helped form in the late 1990s, this set of 53 populations. We incorporated an additional set of populations that has now called the HapMap populations. And these have all been studied with respect to 650,000 single nucleotide polymorphisms. That's the total number of populations. And what I've done here is to look along the genome of all of those individuals and ask, where is the genome homozygous? At more than 5 million bases. So we have a string of bases, and we ask, how long are the strings that are homozygous? Now, there are two features of this that I'll draw your attention to. The first one is that the most homozygous people on the planet are the indigenous Americans. This is the rate of homozygosity, and every one of these dots here refers to an individual in a specific population. And the indigenous Americans are here. The reason for their extreme homozygosity has got nothing to do with inbreeding. It has to do with their population bottlenecks. As they moved across the Bering Bridge and expanded into the Americas, the population sizes were decreasing. This is a consequence of population size. This is the Middle East and South Asia. This is homozygosity, which is a consequence of the culture of marrying your cousins for generation after generation.
1883 catalog of curiosity and relics at the museum shows that an over 8-foot skeleton was actually on display there, parts of it, and a giant skeleton from Gill. And I talked to the physical anthropologist who was part of the team who reinterred that for the Native American Repatriation Act. So on display in Deerfield, they had giant skeletons. And it's right at the top, they're over 8 foot, or it says at least 8 foot. So I'm like, I'm trying, I thought I had credibility with all the stuff I was doing. I'm getting into this twilight zone of research, and I'm like, I just have to follow. I'm compelled to report what I find. And I find that there are other researchers who encountered the same thing and have hundreds of reports in their books. Fred Zimmerman, Ross Hamilton, right here, Philip Reif. I'll just read you quickly. Chapter 5 of his book is called Anatomic Anomalies. At least some of the giants who once inhabited the United States differ from modern humans in ways other than their tremendous size. Judging from the number of their remains, they also possess some unique anatomical features. One of these features that keeps cropping up repeatedly in reports of giant skeletons from a variety of geographic areas and time periods.
A mummy 3 times older than King Tut has been discovered in the Nevada desert. It was found in 1940, about 12 miles east of the town of Fallon. It's a discovery that could possibly unlock some of humankind's early mysteries.
Outside of Fallon, Nevada, the curious have come to learn more about an ancient society of people who once called this cave home. Not far from this cave, a mummy has been discovered. A mummy that may reveal the secrets of an even older society, one that dates back to the dawn of civilization.
This is extremely significant. This is unprecedented. We haven't had a find of this importance in my lifetime.
One thing that makes the mummy, known as the Spirit Caveman, so important are these fine hand-woven fabrics discovered at the burial site.
These textiles represent an extremely sophisticated ability to weave fabric by hand in a time where we didn't realize that people were doing that before.
The mummy was discovered tightly bound up in this matting. Out of respect for the dead, this photograph and this drawing are the only 2 pictures scientists will allow to be publicly displayed. Recent tests reveal that the mummy is 9,000 years old. That's 3 times older than any other mummy yet discovered in North America. That news has stunned archaeologists because a mummy can tell scientists how people back then lived, what diseases they had, even what food they ate. Scientists can get that information by studying the mummy's DNA. Scientists claim that the mummy is so old that he couldn't possibly be related to the Paiute Shoshones, that the mummy's tribe was here thousands and thousands of years before anybody else.
They do not appear similar to any living Native American in North America. They have receding cheekbones, narrow face, long face.
So, Abraham Lincoln, the eyes of that extinct species of giant whose bones fill the mountains of America have gazed on Niagara as our eyes do now. Abraham Lincoln, 1948. Washington uncovered giant skeletons in 1754, working for the Virginia militia. There are many historical accounts. Honest Abe. New York Times, hundreds. Scientific American, American Antiquarian, New York Times. This was known at the time and then eventually buried. Right here, Chief Justice McKean, Judge Bryan, and others found two 11'3" skeletons. 9 foot out of one of the burial mounds in Wisconsin. 10'9", Wheeling, Virginia, the sheriff found it. On and on and on. Charles Huntington, this is at the Cattaraugus Museum in New York State. He found, when they unearthed these two skeletons, a 9-foot male and a 7-foot female, took the measurements, the bones crumbled away like many did because they weren't mummified, although some bones survived and went to places like the Smithsonian. So he made this. I talked to his granddaughter, and she said he was driven to do this by what he saw. I should have somebody that picture for scale, but that's 9 feet tall. Not like, Boston Celtics, 6'2", 9 feet. So Warren K. Moorhead, the Dean of American Archaeology, found giant skeletons when he unearthed them all around the country. Tioga Point, Pennsylvania, 68 of them. Over 7 foot tall, many much larger. Many specimens went to the American Investigating Museum and they were stolen. And there's all these reports over and over again. I know, it's pathetic. Skeleton in copper armor, a giant he found in Illinois at Chillicothe. Connecticut, giant skeleton. Warren K. Moorhead, the Dean of American Archaeology. And I found a curious thing in the secret text of the Freemasons and Rosicrucians. They also talk about this. They have, right here in my newest article, I have pictures of the skulls of almost 10-foot skeletons. The Rosicrucians and the Freemasons in their secret texts talked about this and had matter-of-fact reports from like Town Histories in the New York Times, and they use it to connect it to the lost continent of Atlantis right in the text. So I'll just lay that out there, whatever that means. I know it's a freak show. So the Smithsonian, we're told that it's the height of science, and honestly, I don't want to go down the rabbit hole any further, but there appears to be a lot of misinformation and corruption all around the Smithsonian, what they're doing. Right here in their own reports, 7'6", there's giant skeleton reports in their ethnology reports. Right here, this front skeleton over 7 foot. That's a Smithsonian burial find, Nelson Mound. 8'4", Professor McGee on the left from the Smithsonian. They bought this skeleton, $500 from San Diego, took a tissue sample, and it's down at the warehouse and not to be seen again. Here we go. Thighs and skulls sent to the Smithsonian. Smithsonian Institution to determine the age of the skeleton. Yeah, they might determine it. They're not going to tell us. So, the David H. Koch Hall of Human Origins at the Smithsonian. If you think there's no political or any kind of influence going on, Koch brothers, billionaires, horrendous track record of environmental abuse, and David Koch gives $15 million in the Smithsonian to create this whitewashing exhibit that has global warming scientists outraged. And this is the only exhibit that portrays global warming in such a ridiculous light. So Koch funds this. It's a permanent installation. The moral of the story is, I'm going to wrap it up now. There were cultures in ancient America that lived together. Tens of thousands of people in cities. They lived with connection and love and care and respect for all life forms. And right now, we've mastered fear and separation in our society. And we have organizations and institutions keeping the truth from us and just, telling us to go back to sleep. And, personally, I'm pissed, you know what I mean? I'm sick of it. And I've got to talk to thousands of people, and they agree with my sentiment. Enough is enough. Corporations are not people, okay? Corporations do evil stuff all around the globe. We're people. We care.
It's like bookstores. A bookstore is not just a place where you can buy books. It's a place where somebody expresses themselves by deciding what books to put out there and what books they want to offer their community.
Right.
And that gets replaced by Barnes & Nobles, which means you get the same fucking books that every place in the world gets. I mean, not just America.
Right.
Every bookstore has exactly the same books now. I mean, that's people don't realize what a massive. It used to be. You go to that bookstore, you're going to get some weird off-color books of this kind, or you're going to get maybe a right-wing bookstore, a left-wing bookstore. That used to be how people. And then so Barnes & Nobles comes, and the difference is a family business will hang on through the tough years if they have half a chance.
Yeah.
But a corporate business will go, oh, we're making we're not making it $10 trillion. Just pull up stakes, and they're gone. Right. So now there's no more bookstores.
So you're thinking the whole loyalty thing should outweigh the convenience?
Absolutely, because you're supporting somebody who is, there's a human being and a family who's living off that business, and they give a shit about you.
Isn't the danger that if one thinks about empathy as this, which has this kind of organic quality to it, genetic quality to it, that by talking about empathy, which is something, as it were, which is something which we feel, as against a metacognitive process in which we come to treat other people with empathy regardless of whether we feel empathy for them, for example, as we respect human rights. So is the path of enlightenment one which, as it were, seeks through a variety of therapeutic or pharmacological changes to make us more inclined to a wider world of empathy? Or is it simply to accept that as human beings we have a certain amount of empathy, more disposed to show it towards people that we like, and in a sense we have to use other cultural regulators to ensure that we behave empathically on a global scale?
It's a really interesting question, but you started off by saying empathy is primarily emotional. My definition was that actually empathy is a sort of umbrella concept with several different components, and I identified an emotional component, but also this cognitive one, what you called the metacognitive one. But there may be more than two components. I don't think of this in a reductionist way as being purely biological. It's a psychological process with lots of components. But in that way, it's no different to other psychological processes like language or like memory, which again have many components to them, and which may be partly biological, but as we've seen, are partly influenced by your culture, your surroundings. And just like language, how we end up speaking is going to be strongly influenced by our society. So our empathy is.
There was a place in Harvard Square called the Coffee Connection, and this was a place that was obsessed with coffee, and they had coffees from all around the world, and they'd have stuff like you'd get like a cappuccino, and they'd shave chocolate onto it, not like a canister of chocolate powder.
It took time. I mean,
they had a cheese grater and a block of chocolate, and they'd shred chocolate onto the thing for you. That's like how good it was.
You sound like my grandfather. My grandfather talking to me. You don't even understand the old days.
And
I know the point he's about to make.
You'd go to the Coffee Connection and you'd sit there like trembling, and they'd bring you this thing that would just change your life. Or they'd go, "Hey, you want to try Turkish? We have a new Turkish coffee today. It's a weird thing.
Sounds good.
Never tried it." So then Starbucks opens down the street, but this Coffee Connection hangs on. So Starbucks opens another one, like on the other side of them. Starbucks isn't doing so great that they can open another one. They're just trying to kill.
Oh, shit.
So they open like 5 within a block of the place until Coffee Connection goes, "This is getting hard." And they sell themselves. They go, "Let's just be a Starbucks."
Yeah.
So then Starbucks buys them and then closes the other ones, and then you're just left with just one choice. You get Starbucks.
And the quality of Starbucks is horrible.
It's okay. And the instant
was
Starbucks
right
isn't making a profit, they'll give up, and then there won't be a place to even get coffee.
So we all know that for-profit companies kind of suck. Like, we dislike them, even though we like many of the things they make, like iPads and Dr. Pepper.
Mass media. Mass media is newspapers, books, paper money is mass media. Radio and television. They all work this way. Usually there's only one source of power. To run a TV station, radio station, a newspaper, or to be able to print money, you have to be somebody very, very special. Usually you have a monopoly. So mass media is produced from a center that dictates orders to the people who are down here. That's how it works. Its information is flowing almost always in one direction only. That's what mass media looks like. That's how it's structured. Mass media looked like this from the 1450s onwards. What happened with radio and television when mass media became electronic is that it became only more efficient.
And isn't that then the issue, the problem with focusing on empathy, or the importance of empathy, is that for most of people on this bell curve, we can go to incredible extremes in terms of our behavior as a consequence of those cultural factors. You're not, for example, suggesting that everybody in 1930s Germany had a deficit of empathy, or that everybody involved in the Rwandan massacres had a deficit of empathy. They were more towards the middle of your bell curve, but nevertheless they acted in ways which would be associated with a profound lack of empathy.
To be honest with you, television slightly sort of sobered us up, because the radio society was the worst society we ever invented and the most dangerous one. That was Adolf Hitler in Germany in the 1930s, and that was Rwanda in the early 1990s, and that was Yugoslavia in the 1980s. Typical examples of radio societies where a dictator speaking on the radio, we can't even see how evil he is, can really make you go out and kill your neighbor. Thank God for television. It sobered us up a little. Radio was a really dangerous thing. What happened was that we all of a sudden had computers in our hands. And the computers were also communicating directly to us from the very beginning. We all got access. We all had TV and newspapers and all those things on our computers too. But the computers also enabled us, when they were interconnected with each other, which is what the internet is, we could communicate directly with each other. So what happened was that slowly but steadily, from the 1980s onwards, people started to communicate directly with each other, commenting on what mass media did to them. And this commentating grew and grew and grew. And it became Wikipedia, and it became Google, and it became Facebook. It became all kinds of phenomena that no longer needed this. And finally, this relationship was cut off. This is the world today. And this is the world that's dead. Don't tell Angela Merkel, she hasn't found out yet. This is where we live now. We have moved, all of us have moved to an entirely different world compared to where we used to live before. By the way, how much time do I have left? 10 minutes. Okay, great. So we have a brand new world that we live in, and we have to look at it that way. And it's only when we do this radical change, when we move from one world to the next and live it fully, that we completely understand it and we start to make the right decisions. I became known in the late 90s as a really foul guy who predicted the dot-com crash. That wasn't a very popular idea, but it was actually very easy to see, for the simple reason that the dot-com phenomenon was built on the idea that you could take the new technology and tame it like you would tame iron, bronze, or stone, and then turn it into money. Well, when I studied the internet, I only saw shortcuts. To me, the internet was all about shortcuts, getting rid of the old companies and making shortcuts between producers and customers everywhere. And that's exactly what the internet does. Not a single person in here has gone to a travel agency to get your flight ticket to Berlin. Not a single one. Do you even have cards any longer? Who has cards in here? You're either German or you're over 40 years old if you still have a card. The rest of the world doesn't have cards anymore because you don't live in physical space any longer. So, let's look quickly at these two paradigms. Oh, this should really take 3 hours. I've got 5 minutes. We have the mass media society here, and we have the internet society here. How are they radically different? They're radically different in every aspect.
In 2006, I met that guy. His name's Zay Frank. I didn't actually meet him, just on the internet. Zay Frank was running, at the time, a show called The Show with Zay Frank, and I discovered this show, and that was my way back into being a community learner again. Here's Zay talking about Las Vegas.
Las Vegas was built in the middle of a huge, hot desert. Almost everything here was brought from somewhere else. The sort of rocks, the trees, the waterfalls. These fish are almost as out of place as my pig that flew. Contrasted to the scorching desert that surrounds this place, so are these people. Things from all over the world have been rebuilt here, away from their histories and away from the people that experience them differently. Sometimes improvements were made. Even the Sphinx got a nose job. Here, what you see is what you get, and there's no reason to feel like you're missing anything. This New York means the same to me as it does to everyone else. Everything is out of context, and that means context allows for everything. Self-parking, event center, shark reef. This fabrication of place could be one of the world's greatest achievements because no one belongs here, everyone does. As I walked around this morning, I noticed most of the buildings were huge mirrors reflecting the sun back into the desert. But unlike most mirrors which present you with an outside view of yourself embedded in a place, these mirrors come back empty.
It makes me nostalgic for the days when you could see the pixels in online video. Zay isn't just a great public intellectual, he's also a brilliant community builder, and the community of people that built up around these videos was in many ways a community of learners. So we played Zay Frank at chess collaboratively and we beat him. We organized ourselves to take a young man on a road trip across the United States. We turned the Earth into a sandwich by having one person hold a piece of bread at one point on the Earth, and on the exact opposite point of the Earth have another person holding a piece of bread. I realize that these are silly ideas, but they are also learny ideas. And that was what was so exciting to me. And if you go online, you can find communities like this all over the place. Follow the calculus tag on Tumblr, and yes, you will see people complaining about calculus, but you'll also see people reblogging those complaints, making the argument that calculus is interesting and beautiful, and here's a way into thinking about the problem that you find unsolvable. You can go to places like Reddit and find subreddits like Ask a Historian or Ask Science, where you can ask people who are in these fields a wide range of questions, from very serious ones to very silly ones. But to me, the most interesting communities of learners that are growing up on the internet right now are on YouTube, and admittedly, I am biased. But I think in a lot of ways, the YouTube page resembles a classroom. Look, for instance, at Minute Physics, a guy who is teaching the world about physics.
Let's cut to the chase. As of July 4th, 2012, the Higgs boson is the last fundamental piece of the standard model of particle physics to be discovered experimentally. But you might ask, why was the Higgs boson included in the standard model alongside well-known particles like electrons and photons and quarks if it hadn't been discovered back then in the 1970s? Good question. There are two main reasons. First, just like the electron is an excitation in the electron field, the Higgs boson is simply a particle which is an excitation of the everywhere permeating Higgs field. The Higgs field, in turn, plays an integral role in our model for the weak nuclear force. In particular, the Higgs field helps explain why it's so weak. We'll talk more about this in a later video, but even though weak nuclear theory was confirmed in the 1980s, in the equations, the Higgs field is so inextricably jumbled with the weak force that until now we've been unable to confirm its actual and independent existence.
Or here's a video that I made as part of my show Crash Course, talking about World War I. The immediate cause was, of course, the assassination in Sarajevo of the Austrian Archduke Franz Ferdinand on June 28, 1914, by a Bosnian Serb nationalist named Gavrilo Princip. Quick aside, it's worth noting that the first big war of the 20th century began with an act of terrorism. So Franz Ferdinand wasn't particularly well-liked by his uncle, the Emperor Franz Joseph. Now that is a mustache! But even so, the assassination led Austria to issue an ultimatum to Serbia, whereupon Serbia accepted some, but not all, of Austria's demands, leading Austria to declare war against Serbia. And then Russia, due to its alliance with the Serbs, mobilized its army. Germany, because it had an alliance with Austria, told Russia to stop mobilizing, which Russia failed to do, so then Germany mobilized its own army, declared war on Russia, cemented an alliance with the Ottomans, and then declared war on France because, you know, France. And it's not just physics and world history that people are choosing to learn through YouTube. Here's a video about abstract mathematics.
So you're me and you're in math class yet again because they make you go like every single day. And you're learning about, I don't know, the sums of infinite series. That's a high school topic, right? Which is odd because it's a cool topic. But they somehow managed to ruin it anyway, so I guess that's why they allow infinite series in the curriculum. So, in a quite understandable need for distraction, you're doodling and thinking more about what the plural of series should be than about the topic at hand. Series, series, and seri? Or is it that the singular should be changed, one seri, or cirrus, or serum, just like the singular of sheep should be shoop? But the whole concept of things like a half plus a fourth plus an eighth plus a 16th and so on approaches 1 is useful if, say, you want to draw a line of elephants, each holding the tail of the next one. Normal elephant, young elephant, baby elephant, dog-sized elephant, puppy-sized elephant, all the way down to Mr. Tusk's and beyond, which is at least a tiny bit awesome because you can get an infinite number of elephants in a line and still have it fit across a single notebook page.
And lastly, here's Destin from Smarter Every Day talking about the conservation of angular momentum, and since it's YouTube, cats.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So you've probably observed that cats almost always land on their feet. Today's question is why? Like most simple questions, there's a very complex answer. For instance, let me reword this question. How does a cat go from feet up to feet down in a falling reference frame without violating the conservation of angular momentum?
So here's something all 4 of these videos have in common. They all have more than 500,000 views on YouTube. And those are people watching not in classrooms, but because they are part of the communities of learning that are being set up by these channels. And I said earlier that YouTube is like a classroom to me, and in many ways it is, because here is the instructor. It's like the old-fashioned classroom. Here is the instructor, and then beneath the instructor is the students, and they're all having a conversation. And I know that YouTube comments have a very bad reputation in the world of the internet, but in fact, if you go on comments for these channels, what you'll find is people engaging the subject matter, asking difficult, complicated questions that are about the subject matter, and then other people answering those questions. And because the YouTube page is set up so that the page in which I'm talking to you is on the place where I'm talking to you is on the exact same page as your comments, you are participating in a live and real and active way in the conversation. And because I'm in comments, usually, I get to participate with you. And you find this whether it's world history or mathematics or science or whatever it is. You also see young people using the tools and the sort of genres of the internet in order to create places for intellectual engagement instead of the ironic detachment that maybe most of us associate with memes and other internet conventions. You know, got bored, invented calculus, or here's Honey Boo Boo criticizing industrial capitalism. In case you can't see what she says. Yeah. I really believe that these spaces, these communities, have become, for a new generation of learners, the kind of communities, the kind of cartographic communities that I had when I was in high school and then again when I was in college. And as an adult, refinding these communities has reintroduced me to a community of learners and has encouraged me to continue to be a learner even in my adulthood, so that I no longer feel like learning is something reserved for the young. Vi-Heart and Minute Physics introduced me to all kinds of things that I didn't know before.
Because we live online today. 5 years ago, you would still pick up your cell phone and you would go, you know what, this is really funny, but I'm actually on vacation in Bali, in Indonesia. Isn't it ironic we can talk to each other in real time? And these days, if you tell that to somebody, they just go, I don't care where the fuck you are. I'm just care if you're close to your cell phone or not. Because geography is now reduced to the human body and the cell phone and how far they are from each other. That's what geography is. We moved on to cyberspace. We live there. We moved there. We build our identities there. So this world used to run on money. It was all about capital. It was all about whoever owns the most money when he dies is the winner. That has now become irrelevant because the new world is operating according to the principle of attention. Attention is awareness times credibility, reputation. That's a multiplying relationship. You can read more about it in the Futurica trilogy if you like. Principally speaking, it's this. Awareness is, do people know that you exist? If they don't know that you exist, they're never going to find you anyway. You're just going to be somewhere in the haystack and they're never going to find you as their needle. People have to know that you exist. So creating an awareness, making people aware that you exist is one part of attention. The other part of attention is that when they find out that you exist, they have to be attracted to you, they have to find you credible. They have to think of you as a serious person or a serious company that can deliver something they really, really need and really want. That's credibility. If you don't have one of the two, you're out. The internet is all about the combination of awareness and credibility. And please note, there's not a single dollar sign in here because we're now moving towards society with zero cost. Everything now is about your ideas. It doesn't cost you a penny to open a Facebook page. It doesn't cost you a penny to develop an idea. Other people might throw money after you thinking they can make money out of your idea, but it's no longer of interest here. It's not the primary interest anymore. We moved from the countryside to the city, now we move from the city to cyberspace, and with that we move from capital as the driving force to attention as the driving force. And everything now is about people having attention, connecting with other people who have attention. Networks that have attention connecting with other networks that have attention. When Facebook and Spotify decided to do their thing together in America, I knew Spotify was going to beat iTunes in no time at all. And that's exactly what happened. A week later, 4 million Americans are paying for the Spotify subscriptions. Because Spotify and Facebook, two really strong attentional brands, connect with each other. It didn't cost them one penny to do it. They just realized that if they connected with each other and connected the two brands to each other, that both had attention, they would both be winners and they would gain even more.
But obviously in the human case, we see empathy blossoming into a much more flexible and complex ability. Empathy is a very valuable resource for humanity. I'm going as far as to say it's the most valuable human resource. And my reason for arguing that is that empathy has the power to resolve conflict. That when we have conflict, either between two individuals in a domestic situation, but even we could extend it to two nations, empathy can allow each party to take the other person's perspective or the other leader's perspective and to understand their point of view. And that as a resource, it may be much cheaper, but also ultimately more successful strategy for conflict resolution than either military strategies or legal ones.